R is a widely used programming language for data science. Hello everyone. Welcome to this video on R for Data Science full course. Today, we have our experienced instructors Richard, Ajay and Pete Ferrari who will help us learn everything from basics to advanced and master data science in R. We will start by learning data science from an animated video. You will then learn the essential concepts in data science and understand the important packages in R for data science such as dplyr and tidyr. You will look at some of the widely used data science algorithms such as linear regression, logistic regression, decision trees, random forests, including time series analysis. Finally, you will get an idea about the salary structure, skills, jobs, and resume of a data scientist.
Are you one of the many who dreams of becoming a data scientist? Keep watching this video if you're passionate about data science because we will tell you how does it really work under the hood. Emma is a data scientist. Let's see how a day in her life goes while she's working on a data science project. Well, it is very important to understand the business problem first. In our meeting with the clients, Emma asks relevant questions, understands and defines objectives for the problem that needs to be tackled. She's a curious soul who asks a lot of whys, one of the many traits of a good data scientist. Now, she gears up for data acquisition to gather and scrape data from multiple sources like web servers, logs, databases, APIs, and online repositories. Oh, it seems like finding the right data takes both time and effort. After the data is gathered comes data preparation. This step involves data cleaning and data transformation. Data cleaning is the most time-consuming process as it involves handling many complex scenarios. Here, Emma deals with inconsistent data types, misspelled attributes, missing values, duplicate values, and whatnot. Then, in data transformation, she modifies the data based on defined mapping rules. In her project, ETL tools like Talent and Informatica are used to perform complex transformations that helps the team to understand the data structure better. Then understanding what you actually can do with your data is very crucial. For that, Emma does exploratory data analysis. With the help of EDA, she defines and refines the selection of feature variables that will be used in the model development. But what if Emma skips this step? She might end up choosing the wrong variables, which will produce an inaccurate model. Thus, exploratory data analysis becomes the most important step. Now, she proceeds to the core activity of a data science project, which is data modeling. She repetitively applies diverse machine learning techniques like KNN, decision tree, naive Bayes to the data to identify the model that best fits the business requirement. She trains the models on the training dataset and tests them to select the best performing model. Emma prefers Python for modeling the data. However, it can also be done using R and SAS. Well, the trickiest part is not yet over: visualization and communication. Emma meets the clients again to communicate the business findings in a simple and effective manner to convince the stakeholders. She uses tools like Tableau, Power BI, and ClickView that can help her in creating powerful reports and dashboards. And then finally, she deploys and maintains the model. She tests the selected model in a pre-production environment before deploying it in the production environment, which is the best practice, right? After successfully deploying it, she uses reports and dashboards to get real-time analytics. Further, she also monitors and maintains the project's performance. Well, that's how Emma completes the data science project. We have seen the daily routine of a data scientist is a whole lot of fun, has a lot of interesting aspects, and comes with its own share of challenges. Now, let's see how data science is changing the world. Data science techniques along with genomic data provides a deeper understanding of genetic issues in reaction to particular drugs and diseases. Logistic companies like DHL, FedEx have discovered the best routes to ship, the best suited time to deliver, the best mode of transport to choose, thus leading to cost efficiency. With data science, it is possible to not only predict employee attrition, but to also understand the key variables that influence employee turnover. Also, the airline companies can now easily predict flight delay and notify the passengers beforehand to enhance their travel experience. Well, if you're wondering, there are various roles offered to a data scientist, like data analyst, machine learning engineer, deep learning engineer, data engineer, and of course, data scientist. The median base salaries of a data scientist can range from $95,000 to $165,000. So that was about the data science. Are you ready to be a data scientist? If yes, then start today. The world of data needs you. That's all from my side today. Thank you for watching. Comment below the next topic that you want to learn and subscribe to Simplilearn to get the latest updates on more such interesting videos.
Data Science with R, sponsored by Simplilearn. That's www.simplilearn.com. Get certified, get ahead. My name is Richard Kirshner and I'm with the Simplilearn team. What's in it for you? We're going to go through an introduction to R, why R, CRAN, Comprehensive R Archive Network, and cover installing R. Then we'll get into simple linear regression using R, line of best fit using error summation, correlation analysis in R, and then we'll get into classification using R. Use case, predict the class of a flower. Let's start with an introduction to R. First, it's an open source. R is completely free and open source with active community members. Extensible. It offers various statistical and graphical techniques. Compatible. R is compatible across all platforms, Linux, Windows, and Mac. Library. R has an extensive library of packages for machine learning. Easy integration. It can be easily integrated with popular softwares like Tableau, SQL Server, etc. This only touches a little bit on these different aspects of R. The fact that it's it's very extensive. It probably has one of the most extensive set of data analysis packages currently out. It has a compatibility that is continually growing, so it's integrated with everything from cluster computing to Python integration, which is now coming out. And its extensive libraries allows you to import the different libraries to use for whatever your needs are. It makes it a very diverse and easy to use coding source for analyzing data. R is more than just a programming language. As I just touched upon it, it has a worldwide repository system, Comprehensive R Archive Network, and it can be accessed at https://cran.rproject.org. It provides up-to-date versions of code and documentation for R. CRAN hosts around 10,000 packages of R. That is a huge repository focused on just data analytics. Let's install R to get started. You can easily download the executable file for R and install it from CRAN website. If you go under the downloads, in this case since I'm on a Windows machine, we'll walk through it from the R 3.5 version for Windows. So here we are at https://cran.r-project.org, and you can see down here we have the different options for the downloads. If we go under Windows, which is I'm on a Windows machine, if you're on a Mac machine you can do the Mac or Linux. There's install R for the first time. Just click on that and open and run it. The installation is pretty simple. Follow the default options to finish the installation. After the installation is complete, you'll see the R icon on your desktop. Alternatively, there are mirror sites, and so we can go into RStudio. Let's just take a quick look at that. If you're on the RStudio website, that's www.rstudio.com, you can go down under Products and RStudio Download. You'll see a number of options here. The first one is the RStudio Desktop Open Source License. That's the same thing, you just download it. So if you download that, that's what you're getting. There's also an open source server setup, which is also free, you can download from here. And then RStudio offers a number of paid packages, which includes all kinds of different supports for company and individual level setup. Whether you go through the CRAN site or the RStudio site, the installation is pretty simple. Just a quick note, if you're a Debian distribution, including Ubuntu, you can install R using its regular package management tools. And when you're using a Linux system, that is preferred because then it registers it properly on the setup system. Let's go ahead and open up our RStudio and take a look. Here we are, and I've opened this up in the RStudio version, which automatically opens up some extra windows, which is nice. Let's go ahead and take a look at that. We have our console on the left. This is your main workspace. So if I go in here and I do click the mouse, and I do a 4 plus 4, it'll come up and say the answer is 8. And you have some environmental information, and over on the right you have plots. Usually when you're working in here, let's do a script. We'll go up here to the plus sign in the upper left-hand corner and just add some script in here. In this case, it showed up on the top, but you can move these windows around. And let's say I do y equals 3 plus 4, x equals y plus 2, and then I'm going to do just x. And let's do a plot. We'll throw a plot in there. C is a notation that these are going to be Cartesian points. So we got 1, 2, 3. That'd be like your X, and then Y, 3, 4, 5 for just a standard call scatter plot. We don't have to memorize this. We'll go into some of this later on. And then I can take all of this. If I go under code, since I'm working in the code console, and I go down to run, region, and just run all, it takes this code and just runs it through my console. And you can see down here, it's executed y equals 3 plus 4, x equals x plus 2, and if you add 3 plus 4 plus 2, you get 9. That's what the x does. And then I did a plot. I threw the plot in there, where I'm plotting 1, 2, 3, 3, 4, 5. And if you use just a straight plot, it's a scatter plot, and you can see that this appears on the bottom right, where you have your plots coming in. So it's a very quick way to show data. And that's one of the wonderful things about R, is it's very easy and quick to go through and do different functions on the data and analyze it. So it's a very popular package. Before you start programming in R, you should install packages and its dependencies. Packages provide pre-assembled collections of functions and objects. Each package is hosted on the CRAN repository. Not all packages are loaded by default, but they can be installed on demand. Remember earlier we were talking about all the different packages available? You don't want to install everything from R. It would just be a huge waste of space. You want to just install those packages you need. So to install packages in RStudio, you go under Tools and Install Packages. When you click on the Install Packages, you'll get a dialog box. You'll see where it has a repository CRAN, because there's other repositories, and you can even download and install your own packages you can build. And then you'll pick out the packages you want and separate multiple with spaces or commas, so you can install numerous packages at the same time. In this case, we're installing the forecast package, and you can see down here I just type in forecast, install all the dependencies. So it uses other packages to build on. It has those, and then just click on install, and it's done. Before we cover the basic linear regression model, let's just take a quick look at some of the different parts of R, or parts of programming you'll need, or scripting. First, you need to know there are various data structures in R. We have vectors, we have matrices, we have arrays, data frames, and lists. Vectors is the most basic data structure. If you remember, vectors are a location and a direction is how they're generally defined. Although vectors, when you're talking about scripting, can contain numerous different values. You could have vectors with 4, 5, 6, 7, 8 different values in it. For example, a picture on the computer might have the location of the pixel and the number for the red hue and the green hue and the blue hue. So now you have something with 5 different numbers in it consisting of that vector. Matrices allow you to move stuff around. So you might have a 2 by 3 matrix that you switch to a 3 by 2. We looked at an XY plot earlier. It might be that you have everything you have 10 different numbers and each one has 2 values, XY, and you need to switch that matrix. So then you have 2 arrays of 5 numbers. Arrays are just that, a collection, and you can have arrays of arrays of arrays. Data frames have labels on them, which makes them easier to use. So usually we use a lot of data frames when we're working with data because they're just easy. You can have a column and you can have a row. So think of rows and columns when you see the term data frames. And then lists are usually homogeneous groups. So in R, you're usually looking at similar data that's connected in the list. So the first thing we do is, before we're even importing the data, you should have the data ready. So we need to look at the data and see what's going on. You can import data from various sources, including Excel, Minitab, CSV, table, text files. CSV is usually a text file, comma separated variables, tab separated variables. There's all kinds of different options here. And importing the table is very simple. We have table, read table, file equals data table, header equals true. And let's just take a closer look at what we're talking about here. Scratch the closer look. I didn't realize it was just for example. So importing a table file is pretty simple. You read.table, file equals data.table, so whatever the name of the file is, comma, header equals true, so if there's a header to it. In this quick flash they have name, age, gender. We'll actually do this in R with another data set in just a minute, but you can see it's very easy to read. A lot of people use R even in other programming languages so they can quickly look at the data before they even start analyzing it. CSV file, same thing, read.csv. File equals data CSV, header equals true, separation equals space. So in this case, even though CSV stands for comma separated variable, this one is separated by spaces, and they have the header, name, age, gender. So it's the same file saved as a CSV file. And there's also Excel. Excel has its own issues as far as making sure you know what the tables are and the headers are, but you can see that each one of these is easy to import. So, and just like it's easy to import the data, you can also export tables in R. So you can see here, write.table, myfile, see myfile.text, comma, separated. And the scoop T just means it's tab separated. So if you're using tabbed files on there. Example, Excel. So you can write a .xls to my file. In this case, they did a text. Separation equals scoop T, so it's a tab separated for Excel file. CSV, same thing. Very easy to write a CSV file to your computer once you've changed the data or altered it depending on what you're doing with it. And once we have our data imported, and we can save it afterwards and export it, graphing. Visualization in R is very powerful and it's quick. Love doing this before even exploring the data. Sometimes you just want to graph it to see what it is there so you have an idea of what you're looking for. So graphics in R cover a huge amount of different things. R includes powerful package of graphics that help in data visualization. These graphics can be viewed on screen, saved in various formats including PDF, PNG, JPEG, WMF, and PS, can be customized according to very graphic needs. You can copy and paste in Word or PowerPoint files. R supports various types of graphics including bar chart, pie chart, histogram, kernel density plots, line chart, box plot, heat map, word cloud. There's even some more obscure ones, but these are the main ones that most people use. I know I use a lot of heat maps, but word clouds are a lot of fun if you're doing websites and data and word analysis. And then histogram is very popular. All of these are very widely used. Let's look at the box plots, also known as whisker diagrams. Box plots display the distribution of data based on minimum, first quartile, medium, third quartile, and maximum. So right off the bat, we can use a box plot to explore our data with very little work. To create a box plot, we simply give a box plot and the data. Very straightforward. So we might have passenger numbers in the thousands. I guess this is exploring data dealing with airplanes. And you can see here they just have a simple plot. If you break it down, you have your, if we go back one, you'll notice we have like a minimum, a maximum, our medium, first quartile and third quartile. Let's just break that apart. You can see the line on the bottom is your minimum, your line on the top is the maximum. You have your medium and your first quartile right there. First quartile and third quartile. And the way a lot of times you read this is things that are above the box are outliers and things below the box are outliers, and what's in the middle of the box is usually the data you're looking at.
Let's learn about data manipulation in R, and here we will learn about dplyr package. And when we talk about this dplyr package, it is much faster and much easier to read than base R. So dplyr package is used to transform and summarize tabular data with rows and columns. You might be working on a data frame, or you might be getting in a inbuilt R data set, which can then be converted into a data frame. So we can get this package dplyr by just calling in library function. And this can be used for grouping by data, summarizing the data, adding new variables, selecting different set of columns, filtering our data sets, sorting it, selecting it, arranging it, or even mutating. That is basically creating new columns using functions on existing variables. So let's see how we work with dplyr. Now here I can basically get the package here. So I can just say install.packages dplyr. Now we already see the package here which is showing up. So I will just select this one. I can do a control enter, and that will basically set up the package dplyr successfully unpacked. So that is done. Now you can start using this package by just doing a library dplyr, and this was built. It shows me my version of R. So let's also use a inbuilt data set, that is New York flights 13. So we can do install.packages, and that will search and get that relevant data set. I can again call it by using library function. Now once that is done, we can look at some sample data here by just doing view flights, and that shows me the data in a neat and a tabular format, which shows me year, month, day, departure time, scheduled departure time, and so on. Now we can also do a head to look at some initial data which can help us in understanding the data better. So what is this data about? How many columns we have? What are the data types or object types here? It shows me how many variables we have. So this is fine. Now we can start using dplyr, and in that we can use, say, filter function if we would want to look in for specific value. Now here we have the column as month, so I will do a filter. Now I'm creating a variable f1. I'm using the filter function on flights, which we already have. And then what we can do is we can basically look at the month, where the month value is 07. So let's look at that. And this one, you can do a view on F1, which shows me the data wherein you have filtered out all the data based on month being 7. So this is a simple usage of filter. We can take some other example. We may want to include multiple columns. So we can say F2 filter flights, and here we will say month is equal to 7, day is 3, and then look at the value of F2 if you are interested in seeing this. And that tells you the month is 7 and day is 3. You could also look into a more readable format by using view on F2, and that gives me my selected result. So we are just extracting in some specific value. We can keep extending this. So here we can say flights is what we would want to work on. I'm using the filter function, so I can straight away, instead of creating a variable then doing a view, I can also do a view in this way. I can just pass in my filter within the view, and within this I'm saying filter. I would want to look at the flights, month being 09, day being 2, and origin being LGA, and then that shows me the value here. And obviously you can scroll and look at all the columns, and if you see the origin column, it shows the selected value. So now we have filtered our data based on values in 3 different columns. Now what we can also do is we can use and, or we can use or operators. So I could have done this in a little different way. So I could have said head, which shows me initial result. I will do a flights. So within my head function, I'm passing in this. And what does that contain? So you are saying flights, and in this flights data set, you would want to pick up the month being the column. So we use the dollar symbol here. We give in a value, and I'll say and I'll again say flights, wherein I will select the day being 2 and remember, when you talk about and, it is going to check if all the values are met true. So then you say flights origin LGA, and you look at the value. So in this way I can filter out specifically multiple values by specifying columns. Now we could have done it in this way. We could have created a view, or we could have assigned this to a variable and then done a view on that, where we could have selected month being day and origin. Or you can be more specific in specifying all the columns. It makes the code more readable. So let's look at the values, and here you are looking at head, which shows me based on month, day, and then you can look for further columns for other variables, that is origin being LGA. Now what we can also do is we can do some slicing here to select rows by particular position. So I can say slice, and I would want to look at rows 1 to 5, and I can do this. So you can always assign or look at the view of this. I can just do here. So when I did a slice 1:5, it shows me my entries for 1 to 5. Now similarly, we can do a slice 5 to 10, and now you're looking at 5 to 10 values. So you can always look at the complete data and then you can slice out particular data. Now mutate is usually a function which is used when you would want to apply some variable on a particular data set, and then you would want to add it to your existing data frame, or you would want to add a new column. So this is where you use mutate, which is mainly used to add new variables. So let's see how you work on mutate. So it's pretty simple. So you create a variable over delay. Now I would want to do a mutate so that it adds a new column. So I'm selecting my data, which is flights. I will call the new column as overall delay, and then basically I can look at overall delay being arrival delay minus departure delay. So let's create this and let's look at view of this, which shows me, or which should show me, my new column, which is overall delay, which was not in my original data set. So you can anytime do a head on this one to compare the value. So this one shows me arrival delay, and then there are many other variables. What you can also do is you can do a view, and you could have just look at flights if you would want to compare. So you can look at the flights, and this one would not have any overall delay column. So it basically shows me 19 columns only, what we see here. And if you do a view on overall delay, then that basically shows me 20 columns. So we know that the new column has been added to this overall delay. So if you would want to work with 20 columns, you will use overall delay. If you would want to work with your original data set, you will use flights. Now you can also use a transmute function, which is used to show only the new column. So we can do an overall delay, and at this time we will say transmute, we will say flights overall delay. The computation remains same, but at this time if I look at view on overall delay, it only shows me the new column. So sometimes we may want to compute result based on two variables or two columns and just look at the new value, and then we can decide if we would want to add it to our existing structure. Now you can also use summarize, and summarize basically helps us in getting a summary based on certain criteria. So we can always do a summarize, and what we can do is we can look at our data and we can say on what basis we would want to summarize this particular data. So we can do a summarize function. Now summarize on flights, I will say average air time, and I would want to calculate an average. So for that I'm using an inbuilt function called mean. I will do that on airtime column. So let's look at flights once again, and here we can see there is arrival time, not airtime, sorry, arrival time, and we would want to do some average on this particular data. We would want to summarize this. So what I'll do is I will use the summarize function. I will say average airtime, and this one I will look at mean of airtime. So let's see if there is a airtime column. I might be, let's look at this one, arrival delay, and yes, we have an airtime. So we were actually looking at summarizing based on airtime, not the arrival time. So airtime is how much time it takes in air for this particular flight, and we will want to use the summarize function, not the transmute. So summarize flights average airtime, and this one we will calculate the mean of average airtime, and I will also do a NA removal, which is I'm saying true. So let's do this, and that basically shows me the average airtime is 151. I can also do a total airtime where I'm doing a summation of values, or I can get the standard deviation, or I can basically get multiple values such as mean. I can say total airtime where I'm doing a summation, and then I can look at other values, which is if you would want to put in standard deviation here, you could do that. So let's look at the result of this summarize, and this basically allows me to get some useful information which is summarized based on a particular function such as mean, sum, standard deviation, or all three of them. Now let's look at grouping by. So sometimes we may be interested in summarizing the data by groups, and that's where we use the group by function. So we can always use the group by clause. Now here we are taking a different data set. So we will say, for example, let's look at head of empty cars, and that is basically my data set on empty cars. Now that shows me the model of the car, it shows me mileage, cylinder power, and your horsepower and various other characteristics or variables in this particular data set. So here we can say let's do a grouping by gear. So there is a column called gear, so I will call it by gear. I will look at my data set, and then what I'm using here, which you see with these percentage and greater symbol, is called piping. So that basically feeds your previous data frame into next one. So this is sometimes useful, and you can get this by just saying Control Shift and M, and you can then use this. So we are going to have piping. So I'm saying empty cars. Now this is my original data set where I did a head, or I could have done a view on this one if you would want to see it in a more readable format, and that basically shows me the data. So we are using a different data set, so I want to group it by the gear column. So I'm going to call it by gear, and this one takes my data that is empty cars. I'm using the piping, and then I'm saying group the data based on gear column. That's done. Now let's look at the value of by gear, or you can always do a view. So remember, whenever you're doing a group by, it is giving you a internal object where your data is grouped based on a particular column. So we can look at the values here. You can do a view that shows you your data grouped based on a particular column. Now I can again use the summarize function, where I would want to now work on the new one where it was grouped based on gear. So I'm doing a summarize, and here I'm going to say gear 1, which will be having the value of summation on the gear column, and then I'm saying gear 2, which is mean. Well, you could give some meaningful names to this, and let's look at the value of this one, where we are basically now looking at the values, which is sum and mean values based on the gear. Similarly, we can look at different example. So we can say by gear, and I'm again using piping, but earlier we had taken gear, we had grouped the data, and we called it by gear. So we took our original data set empty cars, but now within this particular data, which was grouped by gear, I will take this data set, I will use the piping, and I will summarize it, where I am saying within this particular data set, I would want to get the sum, or I would want to get the mean, and then you can look at the values. So what you're doing is you are either looking at your original data set, or you're looking at the data which was already grouped, and then you can look at the values. Now here what we can do is we can group by cylinder. Say might be you are interested in looking at data which is summarized based on the cylinder column. You can do that, and then for this by cylinder, I'm doing a piping where I'm using the summarize function, and summarizing will then be done based on the mean values of the gear column or the horsepower. So let's do this, and then you can basically look at the value. At any point you may want to look at the data set again, so just do a head, and you can look at what does the value contain, and by cylinder or by gear, and do a head, and it gives you the value. So you can always do some summarizing or grouping in these ways. Now here we are going to use sample underscore n function and sample underscore fraction for creating samples. So for this, let's take the flights data set again, and we would want to get 15 random values. Now that is done, and it shows me 15 rows with some random values from the data. What you can also do is you can do a portion of data by using sample underscore fraction, and here I'll say flights, I'll say 0.4, which will return 40% of the total data. So this can be useful when you're building your machine learning, where you would want to split your data into training and test. Might be you are interested in some portion of the data, so you can do this, which is very useful function, and then you can look at the value of that. Now, what we can also do is we can use a range function. So like we were doing a grouping by, or we were trying to pull out a particular column. So in the same way, we can use a range, which is a convenient way of sorting than your base R sorting. So for a range function, let's do a view based on a range. So we will work on the flights data set which we have, and here what we would want to do is we would want to arrange the flights data set which is based on year and departure time, and we are doing a view out of it. So that basically gives me the data which is arranged based on your year and departure time. Now I can do a head to give me some highlighting of that data. Now the piping operator, what we are using, can be used in these ways also. So here I will say df, I will just assign the data set empty cars to it. Let's look at the df, which has basically your different models. You can obviously look at the head or view of it to look at useful information. We can also go for nesting options, which can be useful. So we are creating a variable called result here. Now that has the arrange function. So what does this arrange function do? So when we would want to use arrange to sort the data, so I would want to sort the data, but what data would I sort? So I will use sample n, which will give me some portion of the data or some sample data. Now what is that sample data? So here we are using nesting. That is, earlier when we did a sample, we just said data and how many random samples we want. But instead of giving that, what we are going to do is we are going to use filter here. Now this filter will work on df. So filtering will happen based on the mileage, which is greater than 20. I will say size is 5, and I would want to basically arrange this in a descending order. So I'm using the des on this particular mileage column. By default, it is always ascending. So let's get the result out of this, which will basically show me the mileage details in a descending order. So this is my data frame, and now we can look at the result, what we have created. So just do a view or do a head and look at the view. So here you see mileage, where the highest value is on the top, and we were only interested in 5 values in our random sample. So that's why when you did a view, it shows your 5 values and it shows in a descending order based on mileage. So we have not only used an inbuilt function, we have not only arranged the data, that is, we have sorted the data, but we have sorted the data based on a descending order on a particular column. We have said the value should be greater than 20, and we have also said we just need 5 random samples. Now let's look at some other examples. So you can always do a multi-assignment. So I can say filter, wherein I'm going to use df, which was assigned empty cars. I'm going to say mileage should be greater than 20. Then I say B, which is going to get a sample out of A, and I just want 5 random values. So let's look at that. So we have B, which is going to get a set of 5 values from A. Now I will create a result variable which will arrange B, which is sample data, in a descending order. Now let's look at the result of this, and that basically shows me what we were seeing earlier. So you can do a multi-assignment where you can create a variable, get a sample out of it, and then basically whatever is that result, you can arrange that or sort that in a descending or by default ascending order. So same thing, we can do it using pipe operator. So piping, so here I will say result, I'm passing in my DF, that's the data set. I'm using piping, and which basically tells what you need to do on this particular data set. So I'm going to filter out the data based on mileage 20. Then I'm going to push that or forward it to get the random sample, and whatever is this random sample is going to be pushed. So you are arranging this in a descending order. So this is one more way of doing it, and then basically you can look at the result. So these are some simple examples where you can use your dplyr with multiple assignments, or using your nesting to filter out the data. You can also do a range, which is to sort the data. You can get some random samples out of it. You can summarize the data. You can also summarize the data based on one or two or multiple columns, and you can use some inbuilt functions to summarize the data based on some functions which are applied on the variables or on the columns. You can transmute it, where you would be interested in only looking at one column. You can mutate it, where you want to add a new column. You can slice it, and you can give the conditions where you can say and or to filter out the data. So what we can also do is, on this particular data set which we have, say for example DF, where I have my data, let's look at this one. And if I just do a DF at this point, it shows me my data set. And if you would be interested only in particular column, then your dplyr also allows you to, either we can do a filter or we can simply do a select. Now for selecting, we can choose our data. So for example, I'll say df underscore, I'm interested in mileage, I'm interested in horsepower, might be I'm interested in your cylinders in this. And for this one, what I can do is, when I would want to do a select, I can basically say selected df, let's call it some name. I can say Control Shift M, which is for piping. And then basically what you can do is you can do a select, and you can choose your columns. So I was interested in mileage, I was interested in horsepower, I was interested in cylinder. And here what I'm doing is I'm using a select, where I can look at the new data frame. So let's do this. And I'm sorry, here we will have to give it df. This is where you are passing in your data. Yeah, now this one is done, and we can look at the value of this one by just doing a df or head on df underscore mileage horsepower cylinder, and look at the selected result. So you can be looking at selective columns. I could have done this filter, but filter will always look for a condition. Say your mileage is greater than 20, or might be your cylinders are more than 4, or something else. But when you do a select, you are selecting specific columns. So view always gives you all the columns, head gives you highlight, but then select can be useful when we are interested in looking at only specific data. So this is how you can use dplyr for manipulation, for your data transformation, for basically filtering out the data by selecting particular data and then working on it. So similarly, there is one more package called tidyr, and we'll see how we can use data manipulation done using your tidyr package.
Let's learn about the tidyr package, which makes it easy to tidy your data. And this basically helps you creating a more cleaner data, so which is easy to visualize and model. Now this comes with mainly 4 functions. So you have gather, which makes your data wide, or it makes wide data longer. So that is basically used to stack up multiple columns. You have spread function, which makes long data wider, that is stacking the data together, or stack if you would want to unstack the data to data, and you are talking about data which has same attributes. And then your spread can spread the data across multiple columns. You have separate, which is function which splits single column into multiple columns. And to complement that, you have one more function, which is unite, and that combines multiple columns into single columns. So these are four main functions which are used in your tidyr package. So let's look how we work with this. So let me bring up my R Studio here. Now for this, first is, let me just clean up my screen here, doing a Control L. So I will install the package. It is already installed, but we can just do a Control Enter, and then I can say, do you want to restart R prior to reinstall? So install, I'll say okay, and it is basically going to get the package. Now it says package TIDYR, that is tidyr, has been successfully unpacked. Let's use that package using our library function, and that was built under R version 3.6. Now I can basically start using these functions. So for example, here we are creating a data frame. So let's say n is 10, and then we basically would say we will call it wide. Now that's the variable name. I'm using the data.frame function. I'm saying id, which will be 1 to n, so that will take the values from 1 to 10, and then these are the values which have 10 entries. So this is a vector, phase 1, phase 2, phase 3. Let's create a data frame out of it. Now that's done. We can have a look at our data frame by just doing a view wide, and that shows me the ID column, and it has phase.1, phase.2, and phase.3. Now we can use our function. So for example, we can work with gather, that is reshaping the data from wide format to long format. And basically you can say stacking up multiple columns. So let's see how we do that. Here I'll call it long. I'm working on wide. I'm using the piping functionality, and then I'm using gather. So this one, I will say what will be the data which I will use. So we are using wide as a data frame. Then I'm saying response time. So that will be basically one more column. And then you have your columns which you would want to basically stack. So I'm saying from phase 1 to phase 3. So let's do this. And once this is done, let's have a look at our variable long. So this one shows me that I have an ID column, I have the response time column, and I have the phase column, which we mentioned. And that basically has all the values stacked in. So you have phase.1, phase.2, and phase.3. So all the columns are being stacked here. So all my data, so now I have totally 30 entries in this one. So this is basically using your gather function. Now sometimes we may want to use a separate function. Now separate function is basically splitting a single column into multiple columns, so which we would want to use when multiple variables are captured in a single variable column. Okay, so let's look at an example of this one. So let's say long separate, that's what we will call. We will work on this long, which has all the data stacked in as the columns we selected. Then I'm saying separate, I want the phase column, and then I would say when I separate the columns, what are my column names. Now I could also give a separator by giving a comma and then mentioning the separator if that is required. So let's do this. Now once this is done, let's have a look at our long separate. So what we see here is the column which we used. So we were doing a phase column, and that was to be split, and we wanted to split it into target and number. So that's what we see here. So you have phase being split into target and number, and then you have the response time. So this is how you use the separate function. Now there is also something called as unite function, which is basically a complementing of separate function. So it takes multiple columns and combines the elements to a single column. So for example, here we will call it long unite, and we will take long separate, which was separating the data. We want to unite, so we will take phase, target, number, and we want to have a separator between them. So let's basically do this. And now let's look at the result of this unite. So you see, you have the phase and target merged together. So you have phase.1, the separator is dot as we have mentioned, and we have united multiple columns. So this is one more function of your tidyr, which helps you basically tidy up your data or put it in a particular way. Now, then you have your spread function, and this is basically for unstacking. So that is, if you would want to convert a stack to data, or if you would want to unstack the data which is of same attributes, spread can be used so that you can spread the data across multiple columns. So it will take two columns, say key and value, and spread it into multiple columns. So it makes long data wider. So we can look at this one. We will say long unite. I'm using the piping. I will use the spread function. I'll work on the face column and response time. And let's do this. And then let's do a view on this. So it tells me our data is back in the shape as it was in the beginning. So these are four functions which are very helpful when we work with tidyr package.
So let's learn about visualization. And here we will learn about R, which can be used for your visualization. Now, one thing which we need to understand is because of our ability to see patterns, which is highly developed, we can understand the data better if we can visualize it. So the efficient way or effective way to understand what is in our data or what we have understood in our data, we should or we can use graphical displays, that is your data visualization. So there are actually two types of data visualizations. So you have exploratory data visualization, which helps us to understand the data. And then you have explanatory visualization, which helps us to share our understanding with others. So when you talk about R provides various tools and packages to create data visualizations, and which can be used for both kind of data analysis or both kind of visualizations. So when you talk about exploratory data visualization, the key is to keep all the potentially relevant details together. Now, the objective when we talk about exploratory data analysis is to help you see what is in your data. And the main question is how much details can we interpret? Now, when you talk about different functions which we see here, such as plot, which is more for a generic plotting. You have bar plot, which is used to plot data using rectangular bars, or you can say creating bar charts. You have histogram or hist function to create histograms, where you look at the frequency of the data, or basically used to look at the central tendency of the data. You have box plot, which is used to represent data in the form of quartiles. You have ggplot, which is a package which enables the user to create sophisticated visualizations with the little code using the grammar of graphics. And then you have plotly or plotly. It creates interactive web-based graphs via the open source JavaScript graphing library. Now, before we see some examples here, let's also talk about, when you talk about plotting, let's also try to understand what kind of plots you can have and what kind of techniques you have. So let me open up my RStudio here. Now, for example, I can pull out a particular data set, and let's look at this one. So here I can look at all the panes, and that shows me the information. Now what I can do is I can install and get the inbuilt data sets, and then I can simply do a plot wherein I am doing a plot on chick-weight data set. So let's see what does that show. It summarizes the relationship between four variables in chick-weight data frame, which is in R's built-in dataset package. Now from these plots, we can see, for example, weight varies systematically over time. You can also see that chicks were assigned to 4 different diets. Now, when we talk about explanatory data analysis or visualization, that shows others what we found in the data. This means we need to make some editorial decisions, what features we would want to highlight for emphasis, what features are distracting or confusing and you want them to be eliminated, right? So there are different ways of doing it. Now, when you talk about your graphics or visualizations, you have, I would say, 3 different types, or you can say 4. So you have the base graphics, which is easiest to learn. Now here we are having an example of base graphics where I can use the base graphics. I can get a data set using library. Then I can simply create using plot function to generate a simple scatter plot of calories with sugar from US serial data frame in the mass package, and then I can give it a title. So this is basically a simple example of base graphics. Now you also have what we call as grid graphics, which is powerful set of modules for building other tools. Now you also have lattice graphics, which is general purpose system based on grid graphics. And then you have your ggplot2, which implements grammar of graphics and is based on grid graphics. So you have different ways. Now here, since I already have used library and I have the data set, I can just do a X. So I can assign the sugar related values to X and calories related value to Y. Then I can use one more, which is library function and calling in grid. Now I can basically use functions such as push viewport if I would want to create a plot using your grid graphics to create the similar kind of plot which we created using base graphics, but this will give you much more power than base graphics. It will have a steep learning curve, but it is usually useful. So I can do this where I'm saying push viewport. Then I can basically say I would want to have a data viewport. I would say different functions of your grid package. So I'm saying rectangle, you have x-axis, y-axis, given some points here. And then basically you can add details to the graph by giving the names to the columns, and you can basically create a simple grid graphics based plot here. Now there are different other options which we can use to create plots. Now before we go into understanding how you create plots, let me just give you a brief on what are the different kind of plots and how they can be used. So here we will look at these different plots. Now for example, we have a bar chart, which is a graph which shows comparisons across discrete categories. So you have x-axis, which will show the categories being compared, and y-axis, which represents a measured value, and height of the bars are proportional to measured values. Now to create different kind of charts, you can use ggplot, which is a package for creating graphs in R. It is basically a method of thinking about and decomposing complex graphs into logical subunits, and that is a part of tidyverse ecosystem. So it takes each component of graph axes, you can give scales, you can give colors, you can give the objects, and you can build graphs on particular data. You can modify each of those components in a way that's more flexible and user friendly. You can, if you are not providing details for the components, then ggplot will use sensible defaults, and this basically makes it a powerful and a flexible tool. Now here are different options when you use your ggplot, such as you can use geom, or what we call as geometry objects, to form the basis of different type of graphs. For bar charts, you have for line graphs, you have scatter plots, that is underscore point, you have underscore box plot for box plots, you have quartile for continuous x, violin for richer display of distribution, and jitter for small data. So here is some simple example where I would not go into too many details here, but you can just have a look at this one where we are using library function to get the ggplot2 package. Then basically we would want to look into the mileage data. We would want to look at the structure of it. And then we can basically get the tidyverse package. Finally, we can create a bar chart using geom underscore bar. And we can basically also mention what would be in x-axis. Now you can also give different colors to basically add more meaning to your data. You could also go for stacked bar charts. So here we are actually telling ggplot to map the data in the drive column to fill the aesthetic. So here I am giving aesthetic access class, and I'm saying what is the data we need to have, and then we are using geom_bar. So you can also have dodged bar in your ggplot, that is not bar charts which are stacked but next to each other, and you can create that by using your position as position_dodge. Okay, now you can obviously use your different packages which are inbuilt, and you can create your bar charts. And you have other kind of graphs such as line graph, which is basically a type of graph that displays information as a series of data points connected by straight line segments such as this one. And for this one we are using, if you see, geom_line. Now you can also create a scatter plot, which is a two-dimensional data visualization that uses points to graph the values of two different variables, one on an x-axis, one on y-axis, like what we saw in base graphics example. And they are mainly used if you would want to assess the relationship or lack of relationship between two variables. And you also have histogram, which I mentioned is mainly to look at the distribution of a data, to look at the central tendency of the data, basically looking at your large amount of data or for a single variable. You would be interested in saying where is more data found in terms of frequency, where is lesser data found in the graph, how close the data is towards its midpoint, or what we call as mean, median, mode. So you can use histogram where you can categorize the data in what we call as bins. So these are some basics on different kind of graphs. Now we can look at some examples and see how that works. So what we were seeing is some quick examples of base graphics or grid graphics. Now here, let's do an example of pie chart for different products and units sold. So you want to create a graph for this. First, let's create a vector and pass in the value here. Now I can also create labels which I would want to assign to these values. And then basically I can plot the chart by saying pie. So that's the kind of chart which I would want to create. And I would say the data would be X and labels. So let's do this, and that shows me a simple pie chart. Now I can also give main details here. So instead of just doing a pie X comma labels, I can say what is the main and then what kind of coloring it should follow. So this is the way you can create a simple plot. Now I can also find out what is the percentage, and then basically I would be interested in plotting the pie chart which takes X, which takes the labels, which will be the percentage which we are calculating here by doing a round function. And then you can basically give details to your graph. You can say what color it follows. You can basically look at the legend where it needs to be in your chart. What are the values? And then basically fill up the colors. So let's run this one, and that shows me the percentage which was calculated, and it gives me the details, and we can always have a look at our plot. Now if you would want to go for a 3D pie chart, then you can get the package which is Plotrix. Let's use that by calling in the library function. Let's pass in some data to X, and let's give some values or labels which will make more meaning to the data. And then let's plot the 3D graph. So I'm saying pie 3D here, where I'm using X and labels. Then I'm basically doing an explode, which will basically control how your graph looks like and basically give the values. So it also takes the title when you say main and pie chart of countries. Now let's create data for graph. So again, we are having a variable here. We are using the C function, creating a vector, and then let's create a histogram for this one, where I would say X lab, what would be your data around x-axis, what is the color, what is the border, and here I'm creating a simple histogram, which, as I discussed earlier, will always show your values on the x-axis, and y-axis is more of frequency, and then you can look at the set of values and what is their frequency. And we can basically use this histogram for exploratory data analysis, look at the data, try to understand what is the central tendency of your data values. Now we can also give some limits by using the xlim and ylim, and then I can also specify what is the limit. So we have given some values here wherein we have said your x limit is 0 to 40 and y limit is 0 to 5. Now if you compare this with the previous one which we had created, this one based on the frequency had taken the limits, but we can assign limits explicitly by giving this and then create a histogram which makes more meaning. Now let's take another data set, that is air quality. Let's view this to see what does that data contain. So you have ozone, solar, wind, temperature, month, and the day. So this is the kind of information we have in the air quality. Now let's use the plot function to draw a scatter plot, where, as I mentioned, you would be interested in analyzing variables and see what is the relationship between them. So to plot a graph between ozone and wind values, so we will say plot, we will say the data which is air quality. From that I would be interested in the ozone column or ozone field and the wind field. I can create a plot based on this. Now I can also be saying what should be the color, what is the type of the data which you would want to create, and you can look at the information. So you can create a histogram, you can create a scatter plot to basically understand the data better and then infer some information from that data. So let's take the air quality data set itself without specifying any particular column, and you can create a plot which shows me all the different values which you have in the data, and it basically shows you the difference. This is more of an example like what we did for chick weight, where we did a base graphics. Now you can assign labels to the plot. So that is when you are creating a plot, you can say air quality, you will say ozone, and then that's your ozone concentration. You have your YLab, which is the number of instances. You have what is the title, ozone levels in New York City, what is the color. So these are the details what we have given with our plot function. And let's look at the data. So it just tells me that this is the ozone concentration, the number of instances what you have, and you are looking at the data. Now we could also create a histogram by picking up a particular column, that is such as solar, from your air quality, and that basically shows me the frequency of solar values, and we can then try to find out what is the mid, what is the mean, what is the standard deviation, and so on. You can also look at your histogram and try to understand if it is left skewed and right skewed. So we can do that. Now here, let's get the temperature out from this particular data set. Let's create a histogram on temperature, and that basically shows me the frequency of the temperature values and what values have the most frequency or most occurrence. Now you can create a histogram with labels. So let's do that with the limit, and then let's also use text to basically give in the values, which also takes the values, and for each set of frequency or each set of values it gives me the labels. Now you can have a histogram with non-uniform width, so you could do that by doing a hist function and then passing in your temperature. You can say what will be the main, what is the title, what will be your xlab. It will tell you a limit around x-axis, what is the color, what is the border, what are the breaks you would want to have for your bars, and you can simply create a histogram using this. So this basically takes the breaks which we have given, such as 55 to 60, 60 to 70, 70 to 75, and so on. So this is basically creating a histogram with non-uniform width, and it purely depends on the kind of values what you have. Now you can also create a box plot, which sometimes helps us in understanding the data quartiles, also understanding our outliers. So you can create multiple box plots based on the data from air quality. So we'll select all the data and then we'll do some slicing on the data. So let's create a box plot which tells me the values. And if you look at these points here, like single dots, these are basically your outliers. We can learn about that more in later sections. So you can use your ggplot2 library to analyze a particular data set. So for that, we will first use the install.packages and get ggplot2. So it says, do you want to restart R? And I can say yes. So let it get the package. I think the package was already there. And now let's look at using ggplot2. So for that, I have the library function. And let's do a attach where I'm getting a data set which is empty cars. Now then I will create a variable p1. I will use ggplot. I will pass in my data. I'll give the aesthetics. What is the columns which you would be interested in? And then you are using geom_boxplot to basically create a plot which gives me the box plot for the values here. And this is based on the cylinders which is there in your data. So we can always look at what does our data contain and what kind of values or features are available in the data. Now let's create a box plot. We will also use the coordinate function, and that basically gives me based on the data. So I've changed the coordinates. Now if you look at the previous one where we created a plot, we had mileage on the y-axis and cylinders on the x-axis. Now I did a coordinate flip, and that's like your transpose function. So you have created the box plot, but you have just flipped the coordinates. You can create a box plot and then say fill, which is the factor of cylinder. So that can be used to fill up the values in your box plot. Now what we can also do is we can create factors. So we have learned about factors earlier, which is usually used to work on categorical variables. So here let's create a factor which is empty cars gear. You have AM, you have cylinder, and if you look at the factors which we have created, we have passed our data. What is the field or the column we are interested in? What is the level of values there, and what are the labels for those values, right? So we have learned about factors. You can always look into the previous section and learn more about factors. Now let's create a scatter plot by using the ggplot function. Again, we will use the data as empty cars. I will go for mapping option, and then I will give my aesthetics. That is what would be X, what would be your Y, and you also would want to use what kind of function you are using. So let's go for geom point, and that basically helps me in creating a scatter plot. Now you can create a scatter plot by factors. So here we will say ggplot. So notice in all of these cases, depending on the kind of data you have, depending on the kind of plot you are interested in, you will use the ggplot and then basically a function with that or the inbuilt package. So here I'm saying data is empty cars. I'm going for mapping, which basically will take the values for your X and Y. What is the color? And the coloring will be done based on the factor values. Now, if you remember, factors will obviously have some levels, and those levels will basically help you in differentiating between your categorical variables. So I'm saying as.factor on cylinder, and then I'm using geom point to basically create this scatter plot. So let's do this, and I can look at the values of this one. So it says must be, there is an error which says must at least one color from the hue palette. So let's look at that one. So the error which we were facing when we gave color as the factor values was because when you look at these factors which were created with some labels, if we look at the values of these, it tells me there are NA values in that particular column. Similarly, your gear, or similarly, you can completely look at the complete data set. It tells me cylinder, you have AM, you have gear. Now these have some, we have created some labels, but these have NA values. So what we can do is we can create a scatter plot as we did earlier by giving the aesthetics, and that's a simple scatter plot wherein I'm also using geom point so that I can have these points by defaults or with defaults. You can also give a color specific, basically if you would want to have different kind of data in the same plot, or I can create scatter plots by different sizes by giving a size, or I can give a color and size, and that's again one way in which you can create your scatter plots. Now let's also see how you can visualize one more data set, which is MPG. So I can also do it in this way where I set ggplot2 and then pass in, look at the data set what we have here. You can just do a view on this to see what my data contains, if the fields have any NA values, if that's going to affect your plotting. So now what we can do is we can create a bar plot or a bar chart. So I'm saying ggplot, the data would be as we have given in previous lines, that is ggplot2 mpg. Then I will say what should be in my aesthetics and what kind of chart are you going to create. So I'm saying geom underscore bar. So that's my bar chart, and that has basically your class and count. Now you can create a stacked bar chart where your information is stacked in the same bars, and we are still using the same data. We are going for aesthetics, which is class, and then when you say geom bar, which creates your stacked bar, we will use fill, which is drive. And we can always go back and look at our data. For example, you can always look into this. So you have the drive column here, and you are also working on this complete data set. So let's go ahead and create a stacked bar chart. And that basically gives me the information where you have the drive information, which is stacked here. Now you can do a dodge by giving the position as dodge. So we are still going to go for a stack chart, but this time the bars will be next to each other, and that can also be done, which is very useful. You can use this by using geom point where you are mapping and you are specifying what are your aesthetics. So we were creating a scatter plot. Now you can also use or give more details where you can say color can be based on the class, and we have different classes, and based on that my points have been colored. Now you can also use a plot ly or plotly library. So let's install this one. I will say yes, for example. Let it basically restart so that all my packages are updated. Then I can access that package using library function and then create a variable to which you are assigning your plot underscore ly plot. So data is empty cars. What will be your x-axis, what will be your y-axis, and details on your marker, which we have given, wherein I will give a list which is size, color, which is a combination, and then you have your line, what kind of color it will have, and what will be the width. So this is where I'm going to use plot ly, and let's look at this plot. So it basically gives me some information. Now we see some warnings which are getting generated, but you don't need to worry about that. So you can look at the packages, what you have, and what options you are using. So similarly, we can create one more plot using plot ly and look at the values of those. So that's a plot with a trend which explains me about my data. So this is a simple small tutorial on understanding or how you can have your graphics or visualization used to understand your data. Obviously, there are much more examples, much more ways in which you can pass into your plot functions or your ggplot and the inbuilt packages which are available in R for your visualization. Now that could be for exploratory data analysis or explanatory data analysis. So try these graphs and see if you can change these options and try or create new visualizations.
Let's dive into why linear regression. Now that we have come this far, I'm planning to take a closer look at our cells so that we can estimate cells in the future. How about we hire a data scientist? You can see our two corporate individuals. It looks more like they should be agents or secret agents someplace, discussing how to better forward their company. And so they're going to come in and ask the data scientist to come in. Good idea. This will help us to keep a constant track of our sales. So why do we need linear regression? Let's assume that we need to predict the number of skiers based on snowfall. So this happens to be, we've kind of jumped one business to the next. So we're looking at the skiing business, very popular in a lot of areas. And it's based on snowfall a lot of times. You figure you don't have snow, you don't have skiers. But can we actually use something more specific instead of, look, it's snowing? And instead of saying, hey, look, it's snowing, we can actually start drawing graphs. And the graph shows that with an increase in snowfall, the frequency of skiers also increases. So, and there's a pretty direct correlation. If you've ever been up to the ski areas, when there's a lot of snowfalls, the skiers all show up because they know it's going to be better skiing right afterward. So it's kind of easy to see why skiers and snowfall would go together. And it usually draws a nice straight line. And you can easily predict how many skiers, and that way you can also predict how many people you need to service them, how many lifts to have up and running, and all the stuff that goes with running a ski area. Thus, we see that the number of skiers are directly proportional to the amount of snowfall. Regression models a relation between a dependent y and an independent x variable. This is real important to understand regression, because when we talk about linear regression, it's the basis of almost all our machine learning algorithms out there, and it's usually an underlying part of the math in our deep learning. So it all starts here with linear regression. And when we talk about a dependent y and an independent x variable, these are numbers. We're usually talking about floats. So we want to have an actual number value coming out. And that's different than something that's categorical, where we want to know yes or no, true, false. So regression means we're looking for a number. The independent variable is known as predictor variable, and dependent variable is known as the response variable. So we have one predictor variable, the amount of snowfall, and one response variable, how many skiers are going to show up. And then we can take this relationship, and it can be expressed as y equals beta. We're going to use the Greek letter beta, and we have beta naught plus beta 1 x1. And if you continue out, it'd be plus beta 2, x2, and so on till the nth degree. In this case, snowfall is an independent variable, and skiers is a dependent variable. So we kind of had a little quick overview. Let's go ahead and talk a little bit more about what is linear regression. So we're going to go from y, predicting a number of skiers for snowfall, and we looked at the formula a little bit, but let's look a little bit closer at what exactly is going on with linear regression. And the question is going to come up in an interview. What is linear regression? Linear regression is a type of statistical analysis that attempts to show the relationship between two variables. Linear regression creates a predictive model on any data showing trends in data. The model is found by using the least square method. There are other methods. The least square method happens to be the most commonly used out there, and we usually start with the least square method since it's the most common and usually works the best on most models. And we're already looking at how linear regression works, but let's dig deeper into it and let's take a closer look. How linear regression works. I will provide you with a data set which has rent, area, other information in it. It looks like our secret agents have put on their casual wear for this one. You need to predict rent accordingly. We are given area and rent here. So you can do linear regression with more variables, but we're just going to look at the area and then from that try to figure out what the rent should be. We plot the graph. And if you look at it here, you can see that the graph is kind of a linear pattern with a little dip in it. So the rent seems to be based on the area. In most of our work as data scientists, we usually try to start with a physical graph if we can. So we can actually look at it and say, hey, does what I'm fitting to this graph look right? You can solve a lot of problems that arise by looking at the graph and saying, no, that doesn't look right at all. Or, oh, I should be looking over here for this. Then we find the mean of area and rent. So the mean just means average. And if you take 1, 2, 3, 4, 5 and add them all together and divide by, in this case, there's 5 areas, you get 3. And the rent is 2, 4, 6, 5, and 8. If you add them all together and divide by 5, you get 5. And we plot the mean on the graph. So you can see right here, here's the mean of the rent and the area. It's kind of a very central point, which is what we're looking for, the average of everything in there. The best fit line passes through the mean. This is real important. When you're eyeballing it, as humans, we can do this fairly easy if it's a straight line through a bunch of data. It gets more complicated mathematically when you start adding multiple variables and instead of a line you have a curve. But for basic linear regression, we're going to draw a line through the data, and the line should go through the means. That's going to be part of the best fit for that line. But we see there are multiple lines that can pass through the means. So depending on how you look at it, you can kind of wiggle the line around back and forth. So we keep moving the line to ensure that the best fit line has the least squared distance from the data points. And this is, you can see right here, residual. We have our data point, and then we look at this distance between them, and we square that distance. And that's what they mean by the least squared distance. We want all those distances to add up to the smallest amount we can. When we talk about that distance, we call it the residual. It equals the y actual minus the y predicted. Very straightforward. We're just looking at the distance. You can accidentally switch these, and it'll come out the same because we're going to square it. But when you're working with other sets of linear regression, you want to make sure you do the y actual minus the y predicted. The value of m and c for the best fit line, y equals mx plus c, can be calculated using the mentioned formula. And you can see here we have m equals the number of points, that's what n stands for. Then we have the sigma, the Greek symbol is there, which is a summation of x times y minus the summation of x times the summation of y over the number of the summation of x squared minus the summation of x squared, of x, all of it squared. That can be a little confusing trying to say that. And then of course your c value is going to be the summation of y times the summation of x squared minus the summation of x times the summation of x times y over the total count of the summation x squared minus the summation of x squared. That's a mouthful. Normally we don't worry too much about these formulas other than to know they're there. Now if you're a mathematician, you might go back in there and work on those. And those people who originally started to put together the different models in R, of course, had to know all this math to build them and had to test it out. That's one of the nice things about R. What is important is that you know about these formulas so that you know where it's coming from. So if you're using one linear regression model, this is how this one works. There's other linear regression models based on different math. And so you'd have to be aware when that math changes and how that changes the model. We find the corresponding values. So in this case, if you're going to break this up and you're building your own model instead of using the one in R, you would have your rent, you would have your area, you would find your rent squared, your area squared, and your rent times area. And if we go back one, we can see that that's all the different little pieces in this model. We have x times y, we have x squared, we have the sum of x, which is going to be squared, we have the sum of x, the sum of y. This is the same. These are all the little pieces in here that we see for m equals and c equals. And so once we compute all these, we have 15, 25, 55, 145, 88. Very easy to do on a computer, thankfully. You could have millions of these points and it would do it in a very short period. We can then plug in those values very easily into this formula and get a final answer. And we'll see that m equals 1.3 and c equals 1.1. And then when we take this for the y predicted equals m of I, x of I plus c, we can take these and actually run the data we have. So we're going to see how it predicts. So now we find the value of y predicted. So we have our xn and we want to know what we think y will be based on our formula we generated, the linear regression formula. And so when we come in here, we have our x, we have our actual y, then we have our y predict, what we think it's going to be. And then we have, we take y minus y predict, and we get those values, minus 0.4, it's off by 0.3, this one's off by 1, this one's off by minus 1.3, by 0.4. And we go ahead and square that, and then we can sum that square and average it out, and we'll get a value. This is just a summation down here of y minus y predicted square is 3.1. And we call that the least square value for this line is 3.1, and we go ahead and divide that by 5. So when we plot the y predict, and this is the best fit line, and you can see that it does a pretty good job going right through the middle of lines. And in something like rent versus area, if you're trying to figure out how much rent to charge or how many people are allowed to be in the area that's going to work. But if you're looking for the rent value compared to the area, this gives you a good idea based on the area of what you should rent the place for. It's close enough that in the business world this would work. You're not computing something down to the millimeters or micrometers or nuclear physics. We're just charging people. And so if you're off by a couple of dollars, it's not a big deal. You'll be pretty close to what you think it's worth and get the right value for your property. Use case. Predicting the revenue using linear regression. Now that you have a good idea of how linear regression works, and we're kicking back on our lounging sofa today, let's work on a real-life scenario where you have to predict the revenue. So we're going to take a data set, and we'll pull this up in just a minute. We'll have paid, organic, social, and revenue. There are three attributes we'll be working on. The first one is our paid traffic, so all the traffic through the advertisement that comes in. The non-paid traffic from search engines. So these are people coming to the website and are doing so because they did a search for something specific, so it's pulling it from your website. All the traffic coming from social networking sites. So we want to know what's coming from Twitter and Facebook, and somehow they've linked into your website and coming into your marketing area to buy something. And we'll use this to predict the revenue. So we want to know how all this traffic comes together and how it's going to affect our sales if the traffic's coming in. We're going to make use of the multiple linear regression model. So you'll see that this is very similar to what we had before, where we had y equals m times x plus c. But instead we have y equals m1 x1 plus m2 x2 plus m3 x3 plus c. M is the slope. So you have M1, M2, M3, the three different slopes of three different lines. Y is the revenue, so we're only looking for one variable. And remember, this is regression, so we're looking for a number. X1 is going to be the paid traffic, and of course M1, the corresponding slope. X2, the organic traffic, and X3, the social traffic. We will follow these steps to create the regression model. We'll start by generating inputs using the CSV files. We'll then import the libraries, splitting the data into train and test. Very important whenever you're doing any kind of data science. Applying regression on paid traffic, organic traffic, social traffic. So we're going to apply a regression model on them. And then we're going to validate the model. That's the whole reason we split it to a training and testing, is so we can now validate to see just how good our model is. Now before we open up R, I always like to just take a quick look at the data itself, and we're using the rev.csv file. And this is a .cs file, or a comma separated variable file. We'll just open that with WordPad. Any kind of text editor would be nice to show you what's going on. And you can see we have paid, organic, social, and revenue across the top. So those are your titles for your columns, and the values going down. And this is the same as what we saw on the slide just a minute ago. Paid, organic, social, and then the revenue from them. They probably have it in more of a spreadsheet than just a WordPad. And I'm using the newer version of RStudio, which already has a nice layout. It automatically opens up with your console and terminal window down and left. You have your script, and we'll run it in script, and then when I run it line by line in script, you'll see it show up on the console bottom left. I could type it straight into the console and it would do the same thing. And then on the right we have our environment, and under the environment we'll see plots. If you're in an older version, the plots will pop up, and you usually are running just in the console, and then you have to open up a different window to run the script, and you can run the script from there. This opens up everything at the same time when you use the new RStudio setup. And the first thing we want to do is we want to go ahead and generate a variable. We'll call it cells, and we want to load this with our data set. And so in R, we use the less than minus sign. That's the same as assigned to. It's like an arrow pointing at cells, and it says whatever it goes past here is going to be assigned to cells. And we want to read in our CSV file. And then I went ahead and fixed the CSV file up a little bit. When I say the CSV file, I mean the path to it. And we'll go ahead and just paste that in there. And this is my edited version. And you'll see I took wherever we had the backward slash, I switched it for a forward slash, because a backward slash is an escape character, and whenever you're programming in just about any scripting language, you want to do the forward slash instead. So like a good chef, I prepped this and copied it into my clipboard, and we can see the full path here, and the full path ends in our rev.csv file. So that's the path on my machine. And then I'm going to run that, and now we have down here, you see it appear right here. Uh-oh, must have an error in my path. It says object rev not found. Let me fix that real quick and run it again, and this time it does assign the cells the data set, and then we'll just type in cells, and this is the same as printing it. So if you work in other languages, you'll do like print and then cells, or maybe print cells.head if you're in pandas and Python or something like that. But in R, you just type in the variable. We'll run this, and you can see it printed out all those columns. So that's the same thing we just looked at. And it says max print, so it omitted 750 rows, so it has a total of 1,000 rows. And we can scroll up here on our console where the answer came in. And if I scroll up to the top, whoop, way up to the top, there we go. You'll see paid, organic, social, and revenue. So everything looks good on this. And then there's a lot of cool things we can do with it. One of the things we can do is I can summary it. So let's do a summary of cells, and we'll run that. And the summary of cells comes in. It tells you your min, first quarter, median, mean, third quarter, max for paid, organic, social. Breaks it up, and you can actually get kind of a quick view as to what the data is doing. You can take more time to study this. A lot of people look at this, and you can see from the median, the mean, that tells you a lot. And it's divided into quarters, so you have your first quarter value and your third quarter set up on there and max. It just gives you a quick idea of what's going on in the data. The summary is a really wonderful tool. One of the reasons I like to jump into R before I might do a major project in something else, or you can run everything in R. And let's take a look at the head of cells, and let me run this. And you can see it just shows the head of our data, the first 6 rows in this case, and it starts with 1. Important to know. Other different systems start with 0 and go up. R is one that starts with the first as 1. And then if we want to do a plot, I'll go ahead and do a plot cells. Another really powerful tool that you can just jump right into with R once you have your data in here. And you'll see that the plot comes over on the right hand side. And what it does is it compares them. So if I look at my paid and my organic, and you cross the two, you'll see there's a nice line down the middle, big black line where it plots the two together. Let me just widen this a little bit so we can see more of it. There we go. The same thing with paid and social, paid and revenue. So each one of these has a clear connection to each other. So that's a good sign. We have a nice correlation between the data, and you can just eyeball that. That's a good way to jump in and explore your data rather quickly and see what's going on. So we'll go ahead and I'll put a pound sign there. Hashtag, and splitting the data into training and test data. And we want to split it so that we have something to work with to train our data set. And when we do our data set, you do this with any data set because you want to make sure you have a good model. And then once we've trained it, we're going to take the other set of data we pulled off to the side and we'll test it to see how good it is. If you test it with the training data, it's already got that memorized and should give you a really good answer. In fact, when you get into more advanced machine learning tools, you watch those very closely. You watch your training set and how it does versus your testing set. And if your training set starts doing better than your testing set, then you're starting to overtrain it. Now that's more with deep learning and some other packages that are beyond what we're working with today. But this is important. It's very important to understand that that test and that training correlate with each other and gives you an idea of what's going on, and make sure that you're set up correctly. And we'll go ahead and set a seed of 2, and that's for our random generators, so that when we run them, you could seed them with just there's ways to randomize a number. You could do like date and stuff like that, but that way we always use the same random numbers. So we'll seed it with 2. And then we're going to need a library. In this case, we're going to import the library, and we want to import CA tools. And CA tools has our split function, so we're going to be able to split our data, along with many other tools we're going to need for this example. So they're all built into the CA tools. That's why we need to import that. A lot of times they call them library, or sometimes you hear them referred to as packages. So let's go ahead and run that line. And that brings the library in, so now we can use all those different tools that are in there. And then I'm going to do a split. And we're going to assign to the split, that's going to be our variable, sample split. Okay, so that's one of the tools we just brought in, is to sample is the actual keyword or the function word, sample.split. And we're going to take our cells and we're going to go ahead and do a split ratio equals to 0.7, and let's do 0.7 so we make sure it knows it's a decimal point or a float. And what this is saying is that we're going to take our cells data, the variable we created called cells that has the data in there, and I want to split it, and I'm going to split it so that 70% of it goes in one side. We'll use that for training, and 30% will go into the other side, which we'll use then for testing out our model. Let me go ahead and run that, and let's hold on one second. Got an error there. Spit is definitely very different than split. I don't think we want to spit our data out, which is actually kind of what we're doing, is spitting it out. But we want to split. We want to split the data. So let me get that spelled correctly. And then when I type in split, we can just run that because that's now a variable. You'll see that it has true, false, false, true. So it generates a number of interesting different statistics going across there as far as the way it splits the data. And right here, if you have not used R in a while, or if you're new to R completely, that line 1, that's what that little 1 means down there, and then true, false, false, true. That means that's how we're looking at the data. We're splitting all those different pieces of data in line 1 different directions. And so we now want to create our train set, and we're going to assign that. And when we take it and we assign to the train set a subset of cells, and then the subset of cells is going to be based on split equal, and I put this in brackets, true. So you can see the values down here is capital T, capital R, capital U, capital E. So I just want to reflect that on the train. And this is going to take everything where our split variable is equal to true, and it's going to set cells equal to that. And we'll go ahead and run that. And then we're going to set our test variable as a subset of cells. And if we assign the true to the train set, then we want to assign the false to our test set. So now we'll have, this will have 30% of the variables in it, and train will have 70%. We'll go ahead and run that. So we've now created both our training set and our test set. And we can just real quickly type in train, hit the run on there. And you can see our train set. If we scroll way up to the top, we'll have the column names on there, which should match what we had before. Paid, organic, social, and revenue. And then we'll type in test. When I hit run on there, that's going to do the same thing. It'll spit out all the test variables going out. So now that we have the test and train variables, we want to go ahead and create the model. And you'll see this in any of the machine learning tutorials. They always refer to them as models. We're modeling a function of some kind on the data to fit the data, and then we're going to put the test data through there to see how well it does. And so we're going to create the variable called models, and I'm going to assign that LM, that is our linear regression model. I love how simplified R makes it. Just LM, linear regression, and then model, M. I guess it dates back because the linear regression model is like one of the first major models used, so they kept it easy on there. And revenue happens to be the main variable that we want to track. So if you remember correctly from our formula, Y is the revenue, and then we have X is our paid traffic, X2 our organic traffic, and X3 our social traffic. So Y is what we want to predict in here. And then you'll see this notation where we have our squiggle and the period, which means we're going to match up the revenue lines with the lines of the data we're putting in here. And then I'll put comma, and then our data equals train. And of course that's the training data that we created. So when I hit the run, remember we did all that discussion about all those different functions and formulas to compute our model and how that's set up. When it comes down to it, we spend all our time setting up our data, and then I hit the run button on the single line, and our model's been trained. So we now have a trained model here. And we can do a summary of the model. Summary is such a wonderful command because you can do that on R. That works on all kinds of different things on there. Oops. And of course it does help if I remember that my model has a capital N when I run it. And you'll see right here, it tells you a little bit about the model. Use a summary on there. Comes down here, it has our residuals. This is all the information on there as far as like the minimum, the median, the max. It has all our coefficients in there. If you remember correctly from our formula, let's just go ahead and switch back over to that. We have M1, X1, M2, X2, M3, X3 plus C. Well, that's right here. Here's our intercept, and then we have our different values for each of these. So you have our intercept, our paid, organic, and social. And then it also shows us error and information on the error. And one of the really nice things about when you're working with R, you can come down here and you see where we have our stars down here, and it says 3 stars, really good. 2 stars, maybe. 1 star, probably no correlation. And we can see with all of these, it has 3 stars on them. So out of 3 stars, we get 3 stars on all of these. There's no 4 stars. 4 stars would mean that you have the exact same data going in as coming out. And then if we're going to do this, we want to actually run a prediction on here. And that's what we saved our test data for. So let's come down here, we'll do our prediction. We'll take this variable and we'll assign it predict model. And remember, the predict comes from when we imported that package, the CA tools. That's all part of the CA tools in there. So we're going to predict, we're going to use the model, and then we're going to use our test data. Pretty straightforward, quick and easy. We'll run this. And then if we go ahead and type in the predict, it'll print out what's in that variable. And you'll see down here the predicted values it expects to come out. It's going to say our revenue is. And it goes through and it gives it both the line number and the actual revenue value. So that's quick and easy. Boy, we got a prediction really fast. And this is also how you would do it if you had new data coming in after this. You could predict the revenue based on these other factors. So now that we have a training model, or we trained the data with our training data, or we trained the model with our training data, and we've done a prediction on our model with our test data, we want to look this up, and we took a quick glance from our training thing. Our training said it trained really well. But that's not the final word on it. The final word is going to be comparing it. So we want to go ahead and we're going to do comparing predicted versus actual values. What I'm going to do is I'm going to do a plot, and I'm going to do our test, and we're going to do test revenue.type equals. And we can put this in as a type 1 and then, or L, and then we have LTY equals 1.8, and we're going to set it up for column blue. That's a lot of stuff in there. Let's go ahead and just run that so we can see what that looks like and what's that's doing. It's going to generate this nice graph we see on the right. There's our graph. You can see the data comes up and down. We're plotting the prediction on there, so this is the values we predicted. And then let's go ahead and do lines. And I actually did this backwards, so let me try that again. And we'll start with the red one. We're going to do the first one in red. And I want to start with the actual test revenue. So here's our test revenue, and we'll go ahead and run this. And so we have our red plot over here in red. Go ahead and take a look at that. Pull that over, you can see how that looks. It goes up and down, hard to track there. And then we're going to do a couple things here. We'll plot our test revenue. And then we'll make it a little pretty, although it's kind of hard to see the way I have it scrunched up here on the right as far as size and sizing and everything. But we'll go ahead and have our columns in blue and run our prediction on there too. And you can see they overlap the two graphs. So we have our test revenue and our prediction. And then finally, what I started with is we'll go ahead and plot the prediction fully on the bottom and run that. And if you look over here on the graph, we put the blue lines over the red lines. And so you'll see a couple spots where there's red underneath there, but for the most part, our prediction's pretty right on. So it looks really tight. It looks like a good set of predictions for what we're working on. And this is what we were looking at the slide right before we started diving into the RStudio. We can see in the slide here, here's a red. This is a little bit better spread out than what I have on my screen for my RStudio. And the graph shows the predicted revenue. We see that the two lines are very close. So again, they're tight. It's right on. This is what we're looking for in our prediction model. But it's not good enough just having a graph. You always do both. And the reason we do both is you want to have a visual of it, because sometimes you look at these and you get to the graph, you're like, oh my gosh, what is that? And then sometimes you look at the graph and go, that's right on. How come my accuracy doesn't look right? And you realize that your accuracy might be off, or you're plotting it incorrectly. So let's go ahead and look at the accuracy. And we'll use RMSE. That's going to be the variable name we're going to give it. And SQRT, the square root of the mean, and mean just means average. And then we want prediction minus sales revenue, and then we're going to take this whole thing and we're going to square it. So what we've got here is we're going to go through, and let's just explain this formula we're using. Is I'm going to look at what I predict it for to be and what the actual sales, what's our prediction versus our sales, in comparison to the revenue. And when we compare those two, we're going to find the average, and then we're going to square each one of those values, and then we're going to average the square and then find the square root of that. And that's quite a mouthful. The reason we do it this way, the reason we square the value and then we find the means, is to generate an answer based on, doesn't matter whether it's plus or minus. And there's a lot of other formulas you can use there to check your accuracy and all kinds of other things you can do. But a quick, straightforward way of doing it is just like this. And then let's go ahead and run this. And then we type in the RMSE, and that'll give us an actual printed value out. Let's just see what that looks like. And so we have 866.6338 for our accuracy. And so when we look at the 866.63 and we compare that to, say, 50,000, that's pretty close. That's actually a pretty good accuracy given this model. It takes a little bit more when you're playing with accuracies and start dividing out other different aspects of it to get something you can communicate better with. But you always start with the square root means. That's always a good place to start. Use case. We'll start with linear regression, and then we'll jump in and also do a decision tree, so you can see how they are same and how they differ in the way they function and what they're used for. And while we're going through the use case, you can start linking the theory behind it connected to the actual use. And as you connect those dots, you can see that by making changes in the model based on the theory, you can also fine-tune it. We'll talk about that briefly as we go through this. For this analysis, we'll use the default CARS dataset to find the correlation between variables. CARS is a standard built-in dataset that makes it convenient to show linear regression in a simple and easy to understand fashion. And we'll start with head CARS and string CARS. Now I've gone ahead and removed the script on here to make this easier to see, and we don't have to do any kind of importing of data because it's already in there. I'm just going to type in head and CARS and hit enter. And what you're going to notice is it's going to display the first 6 rows, 1, 2, 3, 4, 5, 6, and you'll see speed and distance. Now this is a little bit like a spreadsheet, so if you're using an Excel spreadsheet it should look the same, and this is a standard data frame kind of setup. In this case, whenever you say head, It usually lists the first number of rows, depending on your package. In R, it starts with 1, and then it does the first 6 rows. String, when we do string of cars, it's going to break it down and show us that it's a data frame. It has 50 objects, that's with the 50 OBS, of 2 variables. And then we have speed. The first variable is going to be a number, is what NUM stands for, 4477, it just starts listing the data there. And distance. Now I'm assuming the speed is the speed of the engine. Otherwise, if it's the speed of the car, then the distance should always be the same, and that would just be kind of silly. But this is the speed of the engine, and based on the speed of the engine, can we correlate that to the distance? Let us visualize the data using scatterplot to understand the relationship between predictor and response. And I want you to notice that in this slide, a line has been drawn through the data. Now when we first start with data, you don't have that line. So as we plot it, I want you to kind of visualize that line there and just kind of say, hey, does this stuff kind of scatter around a line or not? Before we actually create the model. And we simply do plot, and I'm going to do a shorthand here, cars, and I hit enter, and it comes over here to the right and plots our data for us. Now because there's only 2 variables, I don't have to do anything special. I'm going to expand this over environment so we can see it. And you can see you can just visualize a line right through the data, and it's all clumped along that line, which makes it really nice for doing a linear regression model. Now I did something a little tricky here because I'm very lazy. I typed in plot cars. A lot of times you don't want to do that because you don't want to plot all the data. We could do plot, in this case cars, $, speed, the first variable, cars, $, distance. When I do that, I get the same plot. All I'm doing is telling it to use just these 2 columns of data. And although the first one is quick and easy, if you only have 2 columns of data, the second one is what you really want to do when you're plotting data like this. You want to control which columns you're using. And then we want to do a correlation. Correlation analysis studies the strength of relationship between 2 continuous variables. It involves computing the correlation coefficient between the 2 variables. If one variable consistently increases with increasing value of the other, then they have a strong positive correlation, a value close to 1. And again, I can just type in correlation cars, the short form, and we can see we have a nice correlation going on there between the 2. What we really want to do though is we want to correlate cars, and then we're going to do the speed, comma, cars, and the distance. And so when you look at this, I actually hit the enter key in the middle of that, which is fine. You can, in R, do it line by line. So if you're trying to do a bunch of different columns, you might want to do that to make it easier to read. And you can see here I get the point 806894. The closer this is to 1, the more these correlate. So it's saying there's a pretty good correlation, positive correlation between the 2 variables. And if you look at it when I did just cars, which did the correlation over all the variables, you'll see that speed correlates with speed 100% because they're the same. That's just the nature of that. But when you look at speed versus distance, we get the point 806849. And if you do distance to distance, you get also 1 since they're identical variables. So now it's time to build our linear regression model on the entire data set to build the coefficients. Let's just take a look and see what that looks like. Back in our console, I'm going to type in linear mod, and in R, we want to do the arrow, kind of like an arrow in a line, or in this case, the less than minus sign. That's the same as assigning whatever we're going to put after it to this variable. So we're creating the linear variable. LM stands for linear module, and we're going to look at speed and distance. So we put the little squiggly bracket between them. This lets R know we're going to deal with these 2 columns, comma, data equals cars. And when I hit enter on here, we've generated our linear mod. Now we want to go ahead and summarize it. And we simply do a summary and then brackets, linear mod, and it generates all kinds of information on our model so we can explore just how well this model is fitting the data we have right now. Now if you've done linear regression in other packages and scripts, you're going to see that this is so easy to explore data in R. So even somebody who's working in, say, Python or Spark, Hadoop, coming back to the R console to do some basic exploration of the data is very beneficial. And if you use just R goes into all kinds of different packages, and you can even do cluster computations through H2OR. There's a lot of cool things. This is what makes R so wonderful, is how easily we can summarize something like a linear model. And to explore this data, let's go back to the slide. And we'll see here where it says the residuals, the first 1Q stands for first quadrant, median, third quadrant, max, coefficients. And we first want to do is look at the estimate standard deviation on here. and you'll see the intercept is at minus 17.5791 and speed 3.9324. So we can compute the distance equals to the intercept plus the beta times the speed, which just means that we can assign a distance equal to minus 17.579 plus the 3.932 times the speed. The value of p should be less than 0.05 for the model to be statistically significant. And this is one of the things I love about R. You can see right down here, we punched in the numbers and it even tells you the significant codes. So if you're trying to guess or remember, it tells you right away, hey, this 1.49 to the minus 12th is way below 0.001 on there. And it even puts 3 stars next to it, so you can see that that is a very high correlation. And you can see the 0.0123 gets 1 star because it is greater than the 0.05, or it's less than the 0.05. So this shows that there's a very high correlation. Statistically, it's very significant. So now we're going to go ahead and create a training and a test data set. And the first thing we want to do is we want to set the seed so the sample can be recreated for future use. Remember, in all these different regression models, they usually have some randomization going on in the back to kind of fit it and guess where it's going to go. And if you want everything to match, you want to start with the same seed in that randomizer. That way it recreates it identical every time you run it on a different computer. And just like working with data in any package, we're going to create indices for the training data, and we're going to model the training data, and then we're also going to do the test data and build our model on the training data. And let's walk through that and see what that looks like in R. And I actually mistyped that one. Let's type in set.seed to set our seed for the 100. Let's go training row index, and that's our name we're making up for our variable. And we're going to set that to sample. Now, sample is a command in R, so we're going to take a random sample of some of the data. And then we're going to do 1 colon in rows cars. So this is the number of rows in cars, and we're going to start with 1 and sample them. So row 1 of the data. We're skipping any of the titles on the top. And then in the sample, it has 2 variables that go in. The first one is the in rows of cars, and then we want to do 0.8 times in rows of cars. And this basically says that we're going to take 80% of all the rows in the car sample. And we'll hit enter to go ahead and run that. And we see here that I had an error, and that is because it's in row. Actually put an S on there. That's something I do a lot on. We'll just fix that real quick. Brings up a point that if you use your up down arrow, you can quickly paste through the last things you typed in, and then you can reuse them. So there we go. Now I have my training row index, which is basically a list of all the rows we're going to use. And now that we have a training row index, we'll go ahead and create our training data variable. And we'll assign that cars, and we'll put that as a training row index. And this is supposed to be brackets because we're dealing with a array type format. We want to do the training row index, comma. So we just need the index of the row, and as far as the columns, we want all the columns. So here we have our training data. And now we set up a training data, we also need our test data. And with our test data, we'll assign that also to cars. And because we use the training row index and we use the sample to create it, we can simply do a minus sign training index, comma. So it's identical to the training data, but the test data is going to be the rows that were not included in the random sample of 80%. So it's going to be 20% of the data. And of course, it's very easy to do mistakes on here. So we'll come back into this, bring back up the error, and then we have training index, training row index. There we go. Very easy to correct errors in R. So now we have our training data and our test data. So we have 80% in training data and 20% in test data. And let's go ahead and create our model. We'll call it LM mod. And this is identical to what we did earlier. Here's our linear model. We're going to have our 2 different columns. If you remember above, we had to tell it which columns we wanted. And we're going to do distance and speed. And then the data, we're going to set equal to training data. So as opposed to doing all of cars, we want to use just the training data on here. And now that we've created a model off of the training data, we need to go ahead and run our prediction off of our test data. We want to see how the test data, which has nothing to do with the model so far, how well it fits. And we'll go ahead and call it distance predict. There's our assignment, so we're going to assign the value to it. And with R, we type in predict, and then we called our model. We go ahead and pull up our model, LM mod. And so we're going to use that model, and then we want to put in the test data. Here's our test data. And so now we're creating the distance predict variable, and we're going to put all the information as far as predicting on our test data. And we'll run that. Just hit the enter key. And then, if you remember from before, we want to review the model diagnostic measures. And so we're going to go in here and do a summary. And you'll see in here we have a couple different things going on. But let's go ahead and take a summary of this and just walk through what this means. So summary, and then we call it LM mod, and we hit enter, and it pulls it up, and we have a nice summary of our LM mod. And the first thing we're going to note is that the data that's right now in our LM mod that we're summarizing is our training data. And let's go back to the slide and highlight this. So the data equals the training data. That's where the LM mod comes in. Residuals, we have our minimum, our first quarter, medium, third quarter, and the max, or quadrant, not quarter. You'd think I was doing a business analysis as opposed end of the year taxes in first quarter versus quadrant. We look at our coefficient. We can see where our intercept is and our speed is. And we note over here our significance codes, so they all match up. So a simple correlation between the actuals and the predicted values can be used as a form of accuracy measurement. So we take a look at the model we created, and now we need to take our predictions and just see how accurate it is on the data that we didn't use to program the linear model. So let's create a variable called actuals underscore predicts and assign it data frame. This is how we create a data frame, is we just assign data.frame, and we'll do a cbind. And in our cbind, we're going to take our data and we're going to create a column called actuals. So this is our choice, the name actuals. This is going to equal test data, and then we're going to use a $sign and distance. And we're running out of a little room there, so let me pull this over so we can see it better. There we go, distance. And then we also want to take and compare that to what we predicted for our other data. And we'll call this column predicteds, and that's going to equal our distance predict. And remember, distance predict is set to the predicted values of our test data. So what this is we're saying, hey, here's our test data, the actual data, and the distance, and then we have what we predicted that distance to be. And we'll go ahead and assign that. And we can do a quick head, actuals predicts, there we go. And remember, head shows us it's a data frame, so it's going to show us the labels and the first set of data. In this case, you'll notice that the rows have a different count. They're not 1, 2, 3, 4, 5, 6. Well, we randomly picked 20% of the data. So this is the first 6 rows of that random selection, which comes out as 1, 4, 8, 20, 26, 31. And we have the actuals, so the actual value is 2, and the predicted value on this first one is -5, so they're way off. 22, 7, 26, 20, 26, 37, 54 to 42, 50 to 50. So one of these is actually pretty right on, where a lot of them are really off at the beginning. Let's just see what that looks like though, because just eyeballing the first 6 rows does not tell us what's really going on. So let's create another variable, correlation accuracy, and we're going to assign this correlation, COR. Remember, we do a COR, and we have our actual predictions. So let's just see how our actual values versus the prediction correlate with each other. And we assign that one, actuals underscore predicts. There we go. Let it auto finish for me. And we can just go ahead and type in correlation accuracy and see what that looks like. So we have an actuals 1, a predicts 0.8, and you can see how they kind of correlate. We have the 0.82, and if you remember from before, we're looking for either 0.001, 0.01, 0.05, 0.1. That is the p-value, which we're not looking at here. This is not based on the p-value. This is based on what we looked at earlier with correlation, that the closer to 1, the closer the values are. And so 0.82 gets upwards of 1, so you see that there's a normal, pretty much a correlation in here. But we want to dig a little deeper, because this doesn't really tell us how accurate it is. For that, we're going to use another tool. For that, we're going to calculate the min-max accuracy and MAPE. And the min-max accuracy equals the mean value of the minimal actuals and predicts over the max value of the actuals and predicts. And then the mean absolute percentage error, or MAPE as it's called, equals the mean of the absolutes predicteds minus actuals over the actuals. That's a lot to follow as far as remembering all these different math and theory behind it. Cool thing though is it's all done pretty much for you. So you can compute all the error matrices in one go using the regress eval function in DMWR package. Since this is the first time I've used this install, I'm going to have to install the DMWR package. So we can actually install it two different ways. If you remember, we talked about installing package earlier. We can go under Tools and Install Packages, and I certainly could type in DMWR. It even comes up and lets me know that's one of the main packages up there. Well, that's a tool of the RStudio setup. You can also install this using the console. We simply type in install. You can even see here it comes up install packages and then DMWR. And when I hit enter, it should do the same thing as the other one does. It goes through and installs the DMWR package. It takes just a moment to zip through all the different package setup. And then the format for DMWR is DMWR. We're going to go : We are specifically looking at the regression.eval. And then we're going to do actuals _ predicts. And we'll go ahead and put in the individual columns on this one. So we have actuals. I love the auto typing. And then again, actuals predicts. And this time we want to do it against the predicteds. We'll go ahead and hit enter on here. And you'll see in here it comes up with our MAE, MSE, RMSE, and the MAPE values.
Today we're going to cover logistic regression in the R programming language. Logistic regression is kind of a misnomer in that when most people think of regression, they think of linear regression, which is a machine learning algorithm for continuous variables. However, logistic regression is a classification algorithm, not a continuous variable prediction algorithm. Logistic regression is also sometimes called logic regression. In this video, we are going to learn why we would use regression as a predictive algorithm, what is regression, the different types of regression. As I've already mentioned, some regression algorithms are classification algorithms, and some are continuous variable algorithms. Why use logistic regression? What is logistic regression? And then we'll look at a use case, a college admission using logistic regression. So why would we use regression? Well, let's say we had a website and our revenue was based on the traffic that we could drive to that website, whether through R&D or marketing, and we wanted to predict the revenue based on site traffic. And the website traffic would be related to the revenue we could generate. The more traffic driven to our website, then the higher our revenue, or at least that's what we would intuitively assume. And so we need to predict the revenue based on our website traffic. Here we have the plot of revenue versus website traffic. Traffic would be considered the independent variable and revenue would be the dependent variable. Often the independent variable or variables, if we had more than one, could be called the explanatory variables and the dependent variable would be called the response variable. However, we typically refer to them as independent and dependent variables. So our intuition tells us that the independent variable drives the dependent variable, and if there is some relationship between the two variables, then we would say that there is a correlation between the two variables. And then we may be able to use the independent variable to make predictions about the dependent variable. If you look at the chart on the right, you'll see there is a clear trend between website traffic and revenue. As website traffic increases, the revenue increases, and we could draw a line to show that relationship. And then we could use that line as a predictor line. So for example, what will revenue be if our traffic is 4.5K? And we see that when the traffic is around 4,500, the revenue is around 13,000. And if we could draw a perpendicular line from 4.5K on the x-axis, the traffic axis, up to the orange regression line, sometimes called the line of best fit, then we could draw another line over to the y-axis, the revenue axis, and we could see where it lands. And that would be the prediction. So in this example, when the traffic is around 45,000 hits, the predicted revenue is around 13,000. Normally, we wouldn't actually draw those lines. We would generate an equation, and we would call that equation a model, and we could plug the independent variable into the equation to generate the dependent variable output, which we would call our prediction. So what is regression? Regression is a statistical relationship between two or more variables where a change in the independent variable is associated with a change in the dependent variable. It's important to note that not all variables are related to each other. For example, a person's favorite color may not be related to revenue from a website. Here, the change in one variable, height, is closely associated with the change in the other variable, age. This makes intuitive sense. As you get older, from when you're born, you get taller. And it seems to make sense if we plot that data, we would see those green points on the graph, up to some certain age where growth would taper off. In the plot in the middle of the screen, we see the clear linear relationship between age and height, which is indicated by the solid red line. We sometimes call that line a trend line or a regression line, or the line of best fit. And we see that the height is the dependent variable and age is the independent variable. Of course, you might ask, doesn't height depend on other factors? Of course it does. But here we're looking at the relationship between two variables, one independent and one dependent, age and height. There are various types of regression: linear regression, logistic regression, multiple linear regression, polynomial regression, and there are others: decision tree regression, random forest regression. But linear regression is probably the most well known. And by definition, when there is a linear relationship between a dependent variable, which is continuous, and an independent variable, which is continuous or discrete, we would use linear regression. When the y value in the graph is categorical, such as yes or no, true or false, they voted, they did not vote, they purchased something, they did not purchase something, it depends on the x variable. Logistic regression is when the y value in the graph is categorical in nature. For example, yes, no, purchased, don't purchase, voted, did not vote, and it depends on the x variable. Notice the trend line for linear regression and the line for logistic regression. They're different. More on that later. And there's polynomial regression as well, when the relation between the dependent variable y and the independent variable x is in the nth degree of x. Sometimes we say an nth degree polynomial of x. In this picture, you can see that the relationship is not linear. There's a curve to that best fit trend line. So why would we use logistic regression? And we need to understand why we would use logistic regression and not linear regression. Picking the machine learning algorithm for your problem is no small task, and it really behooves us to understand the difference between these machine learning algorithms. Linear regression answers the question, how much? So in our earlier example, if website traffic grows, then how much would revenue grow? Whereas logistic regression would answer what will happen or not happen. Linear regression, in general, is used to predict a continuous variable, like height and weight. Logistic regression is used when a response variable only has two outcomes, yes or no, true or false. Often we refer to logistic regression as a binary classifier, since there are only two outcomes. So let's try to understand this with an example. Let's say we have a startup company and we are trying to figure out whether the startup will be profitable or not. That's binary with two possible outcomes, profitable or not profitable. And let's use initial funding to be the independent variable. Here we have a graph that shows funding versus profit, and it appears linear. Once again, our intuition tells us that the more funding a startup has, the more profitable it will be. But of course, data science doesn't depend on intuition, it depends on data. But this graph does not tell whether the startup will be profitable, yes or no. It only states that with an increase in funding, the profit also increases. That's not binary. If we wanted to predict how much profit, then linear regression would be useful. But that's not what we are being asked. Hence, we need to make use of logistic regression, which has two outcomes, in our case, profitable and not profitable. So let's draw a graph again. The x-axis will be our independent variable, funding, and the y-axis will no longer be the dependent variable, profit, but it will be the probability of profit. For example, if you look at a company with a funding of, say, 40, then the probability that that company will be profitable is around 0.8 or 80% based on the best fit line called a sigmoid curve. In the example, we plotted several companies, some with 10, 15, 20, some with 50, 60, or 70, or 65, and we indicated whether they were 0, not profitable, or a 1, profitable, on the graph, and this is how we should think of logistic regression. In this example, given the amount of funding, we calculate the probability that a company will be profitable or not profitable, and if we use the threshold line of 50%, then we have our classifier. If the probability is 50% or higher, the company is profitable. If the probability is lower than 50%, it's not profitable. So what is logistic regression? This is a linear regression graph. So let's compare linear regression to logistic regression and take a look at the trend line that describes the model. It's a straight line, which is why we call it linear regression. But using linear regression, we can't really divide the output into two distinct categories, yes or no. To divide our results into two categories, we would have to clip the line between 0 and 1. If you recall, probabilities can only be between 0 and 1, and if we're going to use probability on the y-axis, then we can't have anything that is below 0 or above 1. Thus, we would have to clip the line. And once we clip the line, we see that the resulting curve cannot be represented in a linear equation. So for logistic regression, we will make use of a sigmoid function, and the sigmoid curve is the line of best fit. Notice that it's not linear, but it does satisfy our requirement of using a single line that does not need to be clipped. For linear regression, we would use an equation of a straight line. Y equals b sub 0 plus b sub 1 times x being the independent variable, y being the dependent variable. But as we've said, we cannot use a linear equation for binary predictions, so we need to use the sigmoid function, which is represented by the equation p equals 1 divided by the quantity 1 plus e to the minus y, e being the base of the natural logs. Then taking the log of both sides and solving, we get our sigmoid function. And graphing it, we get our logistic regression line of best fit. The applications for logistic regression are endless. Here, we might have a couple of gardeners or farmers, and one farmer says, I am planning to grow plants in my backyard, and I want to know whether my trees will get infested with bugs, which I'm sure is a huge problem. And these days, the fewer pesticides we use, the better off we are for health reasons. The young lady says, I can use logistic regression in a model to predict it for you. And the other farmer says, well, how is logistic regression going to help? But we know that healthy versus not healthy is a binary classification, and we can use a binary classifier like logistic regression to solve this problem, which is what the young lady has in mind. If we have the data, we can model the data and generate a sigmoid function that best fits our data, and then use the probability of a healthy tree versus a not healthy tree or an infested tree. Once again, we see our sigmoid line of best fit and some points that represent healthy trees and not healthy trees. Once again, we plot our sigmoid curve, scratch that, and once again, once our sigmoid curve is plotted and our threshold is set almost always at 50%, we can use the sigmoid curve and calculate the probabilities, and here the independent variable of width, which I assume is an application of pesticides or no pesticides, to determine whether or not the probability of healthy is greater than 50%, the threshold, or less than 50%, the threshold. And now let's take a use case of a college admission problem. Of course, we can't solve anything using data science if we don't know what the problem is. So we need a problem statement. And here, the problem statement is simple. We are given a data set, and we need to predict whether a candidate will get admission in a desired college or not, based on their GPA and college rank. So the very first thing we need to do is import the data set. And if it's a small enough data set and it can fit into our computer memory, then we are golden. Otherwise, we have some work to do. The data set that we were given is in CSV format, comma separated values. CSV files are easily imported into our environment. Once we import the data, we next need to select and import the libraries that we will need. Although R is a great programming language with a lot of built-in functions, it is easily and powerfully extended by the use of libraries and packages. Then we need to split the data set into a training set and a test set. It's important to note that the data set that we've imported, that we were given, has the GPAs and college ranks for several students, but it also has a column that indicates whether those students were admitted or not. So what we're saying is that the data set has the answers. And if you think about it, it must. How could we possibly train a model, have a model learn, if we didn't know the answers already? That's why it's called machine learning. So we train the model, and then we test the model. Once we split the data into training and test sets, we will apply our regression on the two independent variables, GPA and rank, generate the model, and then run the test set through the model. Once that is complete, we will validate the model to see how well it performed. So now it's demo time. So here we have our studio, my favorite IDE, or Integrated Development Environment. And I have a script already composed to run our logistic regression on the problem at hand, which is our college admissions problem. So let's just walk down the script before I run it and talk about the various points in the script. So first, define the problem. Well, the problem was defined, and you really can't do anything in data science without a clear problem definition. Once the problem's defined, you can load your libraries, acquire your data, set the working directory. In my case, I'm on Windows. Explore the data, munge the data if necessary, and then prepare the data. Scale the data if necessary, split the data into train and test data sets. Then train the model using the training data and run the test data through the model, and then validate the model for accuracy and precision, etc. So here we are going to load our libraries. I'm going to use a package called CA Tools. And now that the library is loaded, I'm going to set my working directory. And if I come over here to the Files tab, you'll see that there is my working directory. In that working directory, there's a file called binary.csv, and that's the CSV, the comma separated value file that the college gave me. I'm going to ingest and then look at that data. And as you can see, it has 4 columns, GRE, GPA, rank, and then the answer column, admit, whether or not someone was admitted, which would be a 1, or not admitted, which would be a 0. And if we come over to the right, we can look and see some of the first few values of each of those 4 columns. Now let's split the data. We're going to take this my data frame and split it into 2, a training set and a test set. And the ratio we're going to use is 80-20. So 80% of the data will go into the training set and 20% will go into the test set. Now that ratio could be 60-40, it could be 70-30. Typically, it really depends on the size of your data, how much data you have. But this is, for our example and for our purposes, 80-20 is perfect. Next, we'll do a little data munging. In general, you munge the data early on after ingestion, and you really have to be careful. In this case, we don't have any missing values. We don't have any real outliers. Our data was pretty clean when we got it and ingested it. But in general, that's not the case. And a lot of work and a lot of attention needs to be paid to the munging process. Here, we're just going to take our data, the admission column and the rank column, and convert them to categorical variables. Right now, they're integers, as you can see on the right-hand side. And once I run these 2 lines, they will be converted to factors. And now the fun stuff. We're going to use the GLM function, the general linear model function, to train our logistic regression model. And the dependent variable is admit, and the independent variables are GPA and rank. And the little tilde sign here says the dependent variable will be a function of GPA and rank, the 2 independent variables. The data will be the training set, and the family will be binomial. And binomial indicates that it's a binary classifier. It's a logistic regression problem. There it is. We ran our model, and there's a summary of our model. You can see that there is some statistical significance in GPA and in rank by the coefficients and output of the model. So next, let's run the test data through the model. And once we have done all that, we can now set up a confusion matrix and look at our predictions versus the actual values. Again, this is important. We had the answers, and now we took and we predicted some answers. So hopefully our predicted answers match up with the actual answers. We'll run a confusion matrix. As you can see, the predicted values versus the actual values. And it's important here to note that if it was predicted false and it was actually false, and we see 189, or if it was predicted true and it was actually true, which is 27, we did well on those. But there are a few that were predicted incorrectly. Some were predicted true but were actually false. Some were predicted false that were actually true. And now we'll confirm what our percentage accuracy is, 72%. Not bad, but we could probably do better. How? We'll leave that to another video.
We'll be doing part 1 of a 2-part series, decision tree followed by random forest, because the decision tree is part of the random forest. What's in it for you? First, we'll cover what is a decision tree, what problems can be solved using decision trees, how does a decision tree work? And then we'll dive into a use case survival prediction in R. So we'll be using the R platform on this one. So what is a decision tree? And here we have kind of a new looking front panel of a car driving down the street. And we have left or right. So you come into an intersection, you got to decide which way to go. Are you going to go left or are you going to go right? Wait or go? So do you go right away? We have a green light, so probably want to go right away after you check for cross traffic and make sure no one is asleep at the wheel or talking on their cell phone. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So another example is we have a shopkeeper. Very nondescript shopkeeper. Kind of a little spooky without the eyes. So we have a shopkeeper, and he wants to organize his stall. So I must organize my stall, and he's looking around trying to figure out what the best way to stack all his goods are. And he has some broccoli, some oranges, and some carrots. This is kind of a nice example because we can see where some of the colors and shapes overlap where others don't. And so you can create a tree out of this very easily. You can say, is it colored orange? If it's not, well, it goes into one stack. Well, that happens to be all their broccoli. And if it is colored orange, then it goes into another stack. And you're like, well, that's still kind of chaotic. You know, people are looking at carrots and oranges, a very strange combination to put in a box. So then the next question might be, is it round? And if it is, then yes, you put the oranges into one box. And no, that means it's carrots, we put it in the other box. And you can see that a lot of stuff we do in life easily can fall into like a decision tree. How do you decide something? You know, does it go left? Does it go right? Yes or no? And even with this, we even have a number of different end choices: broccoli, carrots, and oranges. So what kind of problems does this solve? What problems can be solved by using a decision tree? Classification. We're dealing with a classification, identifying to which set an object belongs. And from our example we just looked at, a carrot is orange while broccoli is green. I guess it's nondescript day. It's kind of without the faces. I love it. Because a lot of times when you're looking at data, you really don't want to know what exactly the data is, but you're sorting it. So, you know, like this kind of represents data that you really don't know exactly where it's coming from. Just kind of a fun thing. Regression. Regression is another problem that can be solved. Regression problems have continuous or numerical valued output variables. Example, predicting the profits of a company. So we have two different primary problems we solve for. We solve for classification, is it green or is it orange? And we solve for regression, which is a continual number. So, you know, if you're doing stocks, this would be a dollar value that ranges anywhere from 0 to thousands of dollars. How does a decision tree work? Terms you must know first. So before we dive into the decision tree, let's look at some of the terminology for the decision tree. We have nodes. Each internal node in a decision tree is a test which splits the objects into different categories. And continuing with our vegetable stand example, we have broccoli, no, it's not orange, and oranges and carrots are, and so on. So you can see right there where it splits, that's a node, where the oranges split and the carrots split into each of their own groups. And each one of the splits is a node. The very top node of the decision tree is called the root node. So the very first one we started off where we split it is it colored orange. And you can see that pointed out nice and neatly there. This is a root node at the top. Each external node in a decision tree is called the leaf node. The leaf node is the output. And you can see down here we have our broccoli and we have our carrots and our oranges. Each one of those is a leaf node. So to quickly rehash our terms, we have anywhere there is a split, that's a node. And if it's at the very top of the tree, that's the root node. And if you're at the very bottom of the tree where you have a final answer, that is the leaf node. So you have a root node, a leaf node, and then everything else is just a generic node. So one of the most important terms or concepts that powers a decision tree is entropy. Entropy is a measure of the messiness of your data collection. The messier or more random your data, higher will be the entropy. So we can see here we have broccoli, oranges, and carrots are all mixed together, and it's very chaotic. And you could say this collection has high entropy. And if we sort out the carrots out of here, and I guess just one of the broccoli, I don't know where the other broccoli went. You could say if you have just the oranges and the broccoli, this is a lower entropy. They say this collection has low entropy, but really it's higher and lower. One is higher or lower than the other one. And from entropy, we get information gain. Information is the decrease obtained in entropy by splitting the data set U based on some conditioning. So we have our information 1, which we can actually, there's actual computations. And so we have our E1, which is put in there for our entropy value at the base node or root node. And we have A2, which is a leaf node. And so we can actually calculate, there's calculations for entropy. And we actually look at those two values, the entropy, and we take that, we have E1 is greater than E2. Therefore, the information gain equals E1 minus E2. So here we have another example, and we're actually going to attach some values to this one in just a moment. So we're going to move away from the fruit, and we're going to go to everybody's favorite thing, organizing a child's closet. And here we have a young lady waving at us, "Hi, my cupboard is a mess. I must organize my stuff." And we're going to classify the objects based on their attribute set using a decision tree. We can look at it, we have a shape, a size, and a label, and a number. And I'm going to go ahead and look at the labels, because that's really what's key on this one, is we have a couple balls in here, some books, cards, and blocks. And if you look at that, when you have something that's a ball, it's round, so it's a very different shape. The book, card, and blocks are all rectangular, but the books are a different size. So the books have like a size 6. I guess you think of them as very large. Cards a size 4, so they're not quite as big. And the blocks are little Lego blocks that looks like kind of fun to stack on there. And then we can actually quantify this, and we can actually say, hey, we have different numbers. We have 2 balls, 2 books, 1 card, 4 blocks. And we split at each level based on certain conditions on the attributes. So splitting aims at reducing the entropy. And we have a formula, our first actual formula that you'll see happens in the background when we're running these different modules in R. And it looks a little complicated, but we can break that up and simplify that for you. So we see this formula, the negative sum of I of x equals the probability of 1 value of x times the log of 2 probability value of x. The term probability value of x, it's probably easiest to understand if we go ahead and put the numbers in there so you can actually see what we're looking at. And so we plug the numbers in there, we look at the probability of the value of x. Well, if we do the number of balls, there's 2 balls, and the total number of items is 9. So we have a probability of any one object being 2 out of 9. So that's pretty straightforward math. When you look at the numbers, you can actually see that very easily. And so we can calculate our entropy of 2 over 9 times the squared log of 2 over 9 plus 1/9 the log squared of 1 over 9 plus 4 over 9 times the log squared of 4 over 9. So our whole group is the sum of all the entropies. And so when we look at that, we have the entropy of the balls, which is the 2 over 9, rectangles 2 over 9, books 2 over 9, cards 1 over 9, and the blocks 4 over 9. And we can just plug those numbers in there, and we get an actual value of 1.8282. So what the heck does a module do with that number? Well, now we must find the conditions for our split. Every split must give us the maximum achievable information gain. And so we have our first entropy value, 1.8282, and it turns out when you compare all the different individual entropy values for the balls, for the books, for the cards, for the blocks, rectangles, you find out that the biggest split is going to be in the shape. And it's going to be, our first split will be on the shape that will directly segregate the balls out. So they'll split up a huge group from one from the other. And so when we compute that, we end up with E2, which is all of our rectangles, and then we have a leaf node, which is the balls. And so with our E2, we see that 1.3784 is much less than the 1.8282. And so our second split will be on the size, as that will directly segregate the books. And so when we do that, we can see that if its size is greater than 5, all the books go to one side, while the cards and the blocks go to the other. And again, we have our E3, which equals 0.716, which is considerably less than 1.3784. So our entropy is dropping each time we do a split. And of course, our third split we look at, and we'll see that we're left with size again, and we split it with 4 and 2. In this case, if it's greater than 3, it's going to be a block. If it's less than 3, it's going to be a card. And at this point, each of our objects is looped into similarity, so they all look the same, and we end up with an entropy of 0. And so you can see as we go down, the entropy continues to get less. And because it hits 0, we can say all our objects are now classified with 100% accuracy. If it was only that easy to clean the kids' closets. And you can see we have a nice drawing that shows you where all the leaf nodes are on this, in which case we have the balls, the books, the blocks, and the cards are part of the leaf node. And the root node is our first split when we have all the objects and we're splitting them by rectangle by shape. So we're going to dive into the use case. And in this case, we're going to get a little morbid. There I am behind my desk. That's definitely not me. I don't have that big of a chin. But I do usually have a cup of coffee, and it looks kind of like that. It's sitting next to me on my desk. So the use case is going to be survival prediction in R, and let's implement a classification of data set based on information gain. This is going to use the ID3 algorithm. Don't let that scare you. That's the most common algorithm they use to calculate the decision tree. There's a couple different ways they can calculate the entropy, but the formula is all the same behind it. So ID3 is most common in R. And then we'll be using the RStudio for our interface, for our IDE. So the RStudio is free to download. There's the free version. Of course, there's an enterprise version, and there's all kinds of different choices in there. But one of the wonderful things about R is that it's been an open source for a very long time and is very well developed. And it's also very quick and easy to use on a lot of things. So this is going to be in the RStudio IDE. There's some other interfaces, but this is, I would suggest using the RStudio. It's the most common one. And if you remember, I said this is going to be a little morbid because we're talking about how many people survived and died on these ships. So in this case, we have a nice vacation cruise ship going on there, or I'm not sure what that is with the tugboat. So we have a ship, and it had 20 lifeboats. The lifeboats were distributed based on the class, gender, and age of the passengers. We will develop a model that recognizes the relationship between these factors and predicts the survival of a passenger accordingly. So we want to predict whether the person is going to survive or die in a shipwreck. And we'll be using a data set which specifies if a passenger on a ship survived its wreck or not. So we're going to look at this data. And if you open it up into a spreadsheet, and don't forget you can always put a note on the YouTube video down below. And we will be monitoring that, and you can request the data set sent to you or more correspondence. You can also go to www.simplilearn.com and request this data set too. And it's just a simple CSV file we'll send out. And you can see right here we have survived. So 1 indicates a person survived the wreck. 0, they didn't make it. They were under the water. And the luxury class of the cabin, so if they were in, what value is like 1, 2, 3, depending on what luxury class they were. And then we have, this is kind of interesting, how many siblings they had. So it's kind of an interesting added statistic in there. Number of parents on board, and disembark location, so where the destination is. So here we've opened up RStudio. And if this is your first time in RStudio, you'll notice that it opens up standardly in 3 panes. The upper left is for text documents you're bringing in, and then the bottom left is the actual commands as they're processed. And then on the right-hand side, you have your environment set up on there. Now, I've zoomed in with my font a little oversized. In fact, we can even take that up one more size and see if we can get a larger setup view. Here we go. So I've set the font for 18, probably a lot larger than you need to work on a project. And the first thing I'm going to do is on the right-hand panel, we're going to be working with plots. So I'm going to click on the little plot tab up there. And I'm just going to collapse that over to the side for right now. And then I'm going to open up the bottom one. And you'll see on the top, I actually have 2 different tabs. Team in the back was really nice to set up the whole package for what we're working on here. And we'll go through this line by line. And then you'll see as we execute the different lines, they're going to appear down below. So I'll be flipping between these 2 left panels. And let me go backwards just for a second here. We're going to do this part. So let's take a look at the installs. And if you look at the installs, and I'm not going to actually run the installs because I've already run them on my computer. So these are already installed in my R packages, and I don't have to rerun them. We have a number of packages we're bringing into R because that's how R functions. And the first number of packages are all part of our decision tree. So our F selector, our R part, our caret with the dependencies equal true, and our dplyr and our R part plot. Ooh, that's a mouthful. You'll need to import all of these in your setup. And the first one, which is your F selector, computes your chi-squared, your information gain, your entropy. All of those formulas are part of the F selector. So when you bring it in, that's what that package is. The R part is your partitioning of your decision tree. So these are your primary 2 decision tree modules that we're bringing in. The caret is a part for actually splitting apart the data, because we always want to do a test set, a train set. So they built a package caret to kind of handle all those. You'll see caret used in a lot of other machine learning packages when you're doing the R. The dplyr is for mutating your data, so you can sum it, you can classify it, you can filter it. That's all part of the dplyr. And then R part has another piece called plot, and that's for helping us plot the data as we sort out the tree, because the R part creates the tree, but you still want to be able to plot it. And then we come down here and we have some additional tools. We're going to work with a spreadsheet. This is a Microsoft Access spreadsheet, so we're going to use the XLSX package to import it. And you might think that's a little outdated, because I know when I'm doing any new projects, I try to save my data into a comma-separated variable file or something more standardized. But a lot of times you'll end up with these old databases where they're exporting data, and their export comes in an Excel spreadsheet, and guess what? This is a time saver. Instead of opening up the spreadsheet, resaving it as a comma-separated variable file, you can just open it right up in R, which is really nice. And then we have our data tree, which goes right along with displaying the data. So we have our rpart.plot, and we're going to put that into the data tree so we have a nice visual. And finally, you need to install the package CA Tools. And CA Tools is another package used for general manipulation of your data and your vectors. So it also has a split function for training data. I know we have another package for that, but both those packages fit in there as far as the working with the data. So a lot of times you'll see these loaded in there together. And you'll see in a moment we'll import the elementary StatLearn package also, which is very generic, working with data setup as far as statistics and data processing. Now, because my Java setup is a little different because I use a developer package, well, the latest update of the developer package and the R are struggling to see each other. So I need to go ahead and add this in. Chances are you don't need to worry about this. But if you do get an R Java error, you'll need to go ahead and add in a line to set your environment. And I'm just going to set the Java home. I went ahead and looked up the last solid JRE folder, and you'll see under Program Files Java, you can look them all up to make sure it's the JRE and not the JDK. The difference between those is one is a standard executable, that's a JRE folder, it is a folder, not an actual file, and the JDK deals more with developer side on things. And I'm going to go ahead and run this, and if you're in R, you can run these lines individually by holding your control key down and hitting the enter button. So I've now loaded my workspace and set my environment here. And we can actually look and just make sure system.getEnvironment is the opposite one. And I can just look real quick and say, hey, what's my Java home set to? And if I run that, whoops, I forgot to put brackets around it. There we go. And if I do that, you'll see that it's set to the JDK 18025. And again, we're looking at the split screen, and let me just move this up here a little bit, and let me hit the enter key a bunch of times so it comes up on the screen. When I run it, and I'm running it line by line, the run text then appears down here, and this is what's actually being executed. So I could just as easily type it in down here as putting it up here on the top part. That's just a little bit of RStudio and working with RStudio. So I've shown you the installs. And again, I've already installed it on my computer, so it takes a minute or two to install it. We need to go ahead and then bring those libraries in to work with. So basically, we're going through all the different libraries we're using. Element StatLearn is a standard R library, so it should already be installed. You don't have to install that one. And I can just go right down them, and you'll see as I install them that they show up on the bottom. And every time you go to run a new setup, you need to go ahead and install these, pull the libraries in. You got to tell your RStudio these are the libraries you're using. And you can see right down here that as it executes them, it has all the different things. One of them had like a couple different parts to it, so it loaded the lattice and the ggplot2. Really nothing to worry too much unless you see errors down here. So if you start getting error codes, then you might have to go troubleshoot and find out why it's not installing correctly, or did it install correctly. But it's pretty straightforward. We've covered all the libraries. And again, if you want a copy of this code, simply add a comment down below on the YouTube video, or visit www.simplilearn.com, and they'll be happy to send you a copy of the base code. The next step is we want to go ahead and load the Excel file after setting the working directory. So let's go ahead and set the working directory. SEWWD is a command for that in R. And then this is wherever you have downloaded your data to and your files to. A lot of times if you get the zipped framework sent to you, it will unzip all into one location. And then you got to look that location up and put that in here. A lot of times it automatically sets that for you if you're working in the same directory. In this case, you can see I've pasted in a very lengthy path because I have this as part of my documents, my business docs, and Simplilearn and marketing videos and so on. And I'll go ahead and do the Control Enter and run that. So now my working directory is set. And you can see down below it's executed this on the console down here. And if I open up that working directory, you can see I have a ship XLS file. That's the data we're going to look at. And we looked at that on the slide. You could also open this up, and I will want to go ahead and open it up with a notepad. By default, it'll open up as a spreadsheet. Oh, it is an Excel file, so I'd have to open it up as an actual spreadsheet. Wasn't thinking that one through. This is one of the problems with saving stuff as a proprietary ship file, even as something as widely used as Microsoft Excel spreadsheet. But when we open up the spreadsheet, you can see here the same data we looked at before. That's what's coming up in this file. And so I take this file, we can go ahead and let's create a variable. We'll call it add. And we're going to assign it. That's what the lesser than dash means if you've never used R before. And we're just going to assign it a ship XLS. And then I'll do my Control Enter and you'll see it run down here. Ship add is assigned ship.xls, our Excel spreadsheet on there. And then let's have another variable. We'll call it df for data frame. And we're going to assign this read XLSX. And that's from the library SLXX that we just imported. And we want to read the file add, because we just created that variable with the ship.xls. And I didn't catch this right away, but you'll see when we open it up in a spreadsheet. It might be hard to see in your video screen. It has the first sheet is called ship 1. So this data is on the page ship 1 in the Excel spreadsheet. And we got to make sure that we tell the reader to look for that. And so we can simply do that in our command line. Sheet name equals, and it was ship 1 on there. So we go ahead and hit the Control Enter and run this line, and it brings it down below and executes it. It's now reading in that data from that spreadsheet. That's what's going on. And it takes it just a moment to go ahead and read it in. And then with any data processing, we need to select the meaningful columns for the prediction. So this is important that we sort through our data and set it correctly so that whatever we're feeding it into can read it correctly. We can do this with df. We're going to reassign it, and we're going to select, and from there we're going to select df as our main data frame going in, and then list the columns that we want. And if we look at the data, we have survived, we have a class, we have a name, sex and age, and then there's siblings and parents. We really don't want to know the name because we don't need the name to run this on here. And then we got to decide which one of these we want to work with. And the guys in the back played with the data a little bit, and they came up with the following columns. Survived, which we need definitely, because that's what we're actually trying to figure out is whether we're going to survive or not. What class which class of the boat they're riding in, whether first class, second class. Sex and age. And we went ahead and dropped the rest of them, at least for this example. And so I can go ahead and do my Control Enter, and you'll see it execute down below. And now df equals these 3 columns, or 4 columns. Plus our answer is one of those. So I always think of it as 3 columns plus 1, but it is 4 columns. And then for the next step, we want to make sure the data is in the right format. So again, I'm going to reassign the df, and we're going to mutate the data. And that means we're going to take each one of these columns, and we're going to let it know what kind of data that is. So our first one is we got to put the database in, or the data frame in there, df. And then we want to go ahead and do survived equals a factor of survived. So this is a yes, no. It's letting us know that this is a 0 or a 1 on here. And then for the class and the age, those are as numeric. There's other ways to process class since it is a very restricted number on there, but for this we're just going to do it as a numeric value. Same thing with age. And you see we didn't do anything with sex. We're just going to leave that as male or female. And that's fine for this because it'll pick up on that when we run the decision tree. And we'll do our control enter. So now I've assigned the new DF, and you can see it comes down below as we run it on there. So this is now loaded, and DF now is a mutated data frame that we started with, and we've set it up with our specific columns we want to work with. In this case, survived, class, sex, and age. And we've formatted 3 of those columns to a new setup. So one of them is factor. That's what we use for survive, so it knows it's a 0 and 1. And then we switched class and age to make sure that it knows that those are numeric values. Now that we have our data formatted, we need to go ahead and split the data into a training and testing data set. And by now, if you've done any of our other machine learning tutorials, you know this is standard. You need to have your data that we train it with, and then you got to make sure it works on data that it hasn't trained on. So we'll go ahead and do the splitting. Let's take a look and see what that looks like. And when you're dealing with splitting the data, we're doing a little randomness. So we'll just go ahead and set the seed to 1, 2, 3. You can set that to whatever number you want. That's just setting the random variable seed. And we'll go ahead and hit enter on there. And to do this, we're going to create sample, and we're going to go equals sample.split. So we're splitting up the data. This is actually creating a whole new column, trues and falses, and it's all stored in sample. And we want our data frame, and we use a $sign to denote that we're going to be working with one of the different columns. A nice thing you can do in R, and it actually shows my survived, so DF survived. And then our split ratio, I wanted to add a period in there, which it doesn't have. Our split ratio is going to be equal to, and we'll do 0.70. So we're going to take 70% of the data of those that have survived, and we're going to just randomly select which one of those we're going to use for training and which one we're going to use for testing it out later. And we'll hit our enter and load that sample in there. And then we'll go ahead and create our train and our test data sets. So I'm going to set train equal to, and this is where it kind of gets interesting because we're going to do subset, and then we're going to do a subset of our DF where sample, and then we're going to use equals since this is a logic gate. So wherever it sets sample equal to true, we're going to use that line in DF. And this is of course R, so it's all capitalized for true. So here's our trained data frame we're creating. So when I execute this and it shows up down below, it goes up and says, hey, this sample created a whole bunch of trues and false. And we're going to take those trues and falses, and wherever we've created a true, which is 70% of the data randomly selected, that's what we're going to train the data with. And then we need our test set, and that's a subset, just the same thing we just did. And we need our data frame, and this is where the sample equals false. And again, when I hit Control Enter, it goes down this line of code and it runs it down here in our terminal window. So now we've nicely split our data up. We have our training data set and our test data set. And this is of course where we get to the point of what we're actually trying to do, which is create our decision tree. And we're going to do that by training the decision tree as a classifier. This always gets me. You spend all this work sorting through the data, reformatting it, in this case mutating it and filtering it, and creating a train set and a test set. And so we're going to go ahead and create our tree, and we're going to assign to it the R part. That's the module we imported. And for the R part, we need to go ahead and do what's called a survived, and this is kind of a little complicated to look at, so let's just take a quick look at this, and I'm going to go backward on it. The first part is we're importing the data, so data equals train. And then what we want to know is who survived. So the first part we put in here is the column we're looking for is survived. And you'll see that we have added the squiggly mark in the period because we're looking just for this prediction. We just want to know who survived on these boats for programming our decision tree. And I'll go ahead and hit Control Enter, and we've now created the tree. That tree with all those values is now in there. And if you remember from before, we've taken from when we did the closet full of clutter, we've done the same thing where we have our entropy, and that one line computes the entropy and the increase in information, and it brings the entropy down to 0. So it's the same thing, but instead of applying it here as we did visually to the closet, it's now applied it to the data on the ship. It's now looked at the survival of 0 or 1 based on female, male, what age they are, where the best split of the age is, and what class they were in. You can see we have first class. If we go down there, I think there's third, second. So I guess it's class 1, 2, and 3. But you can see that's how it's split it up. So it's used these different variables to minimize the entropy and maximize the information gain. And that's all done in that one line of code. Boy, we worked on all that theory, and computer does it for you in one line of code. It's important to understand the theory behind it so you know what's happening. Because as they make changes to these, or if you add special settings on it, you have to know what they're doing. But in this case, you can see that once we get it formatted, the computer does all the heavy lifting for us. And it never ceases to amaze me just how advanced machine learning has become these days, and how easy it is for people to get into it and learn the basic setups and be able to compute your different machine learning models. Once we've computed our decision tree and we built it on there, we want to go ahead and start doing predictions with it. And what are we going to predict? Well, you remember that we created our data with the train and test. So we have our training data, which we programmed the tree for. Now we want to see what it does with the test data. So let's see what that looks like. And we can wrap that into tree.survived.predicted. We'll assign that to our prediction. And this is nice because we have the command predict from one of the modules, the rpart module that we brought in. And I can simply put in here that we're going to use the tree. We have our test data and type. And this happens to be classification or class. And this would also be if you were to distribute this tree. You could save the tree and send it someplace else to be used on new data. This would be the command line you would use to predict on here. Predict, you have your tree saved, you have whatever data you're putting through, and you let it know it's doing a classification on the tree. And we'll go ahead and run that. So now that's loaded up. And now that we've gone through, we've trained our tree, we've run a prediction on our test data. Remember, the tree had never seen the test data till now. So we've already built the tree and we're just testing it out. And to do that, we're going to use a confusion matrix for evaluating the model. And let's see what that looks like. And that is simply confusion matrix. So once we have the confusion matrix, which came in from our caret, we need to compare the two different pieces of data. And the first one's going to be the value we generated up here. We have tree.survived.predicted. So I'm just going to copy that and paste it down here. And then the second one is the tree. We're comparing that to, let's see, survived. And it's not the tree. It's easy to get confused sometimes when you're moving these things around. We're going to compare it to test, the test group of data, specifically the survived column. And let's go ahead and run this and see what that looks like. And so let's go ahead and scroll up a little bit here to where it first executed the confusion matrix. And the most important part of this is that we have our prediction and our reference. And so 0 means they didn't survive, 1 means they survived. We had our prediction on here versus the actual. And that's what these two columns mean. And so when you read this little chart, we have 0, 0. So both the prediction and the actual reference said we agreed on 218 values for people who did not survive. A little grim there for data. Remember I talking about this is morbid data, talking about death rates of people on boats. And it says that they both agreed on 93. So 93 of them where we predicted the value that they would survive, and the reference came up the same. Likewise, the predicted, where it predicted 1, and the reference said, no, these people didn't survive, well, our prediction got 25 wrong. And where it says they didn't survive, and they actually did, it got 57 wrong. And we can come on down with the confusion matrix, and we can look at the accuracy. It comes up with the 0.7913 or 95% CI. So yeah, you're looking at pretty high accuracy. Information ratio, p-value. When you're in statistics, the p-value is one of the things we look at. Remember that there are certain values, if it's over 0.95, it's considered highly valuable variable. 0.5 means maybe, anything less than that means it's probably not connected. You have to look up the p-value a little bit more on that. And then they just have more information down here, which you can go through and But the important part is that we have a very high accuracy. That's what we're looking at. This is a very accurate model. And again, always remember the domain you're working with. Certainly this is an example, and this is a good little piece of data you can play with. But if I was, say, betting money, and my accuracy came up as 79% or over 95% CI, I'd be like, yes, let's bet on that. That's a good bet. But if I was betting on a life or death situation, I might kind of rethink that a little bit if it's going to affect my life that way. You can also look at this as if you're trying to figure out where the boats go in this particular example and where to put the lifeboats. That's actually pretty good. Be able to say, hey, we can increase the chances of people surviving this accident by putting the lifeboats in the appropriate places. And then, this is always fun. Let's visualize the decision tree. One of the cool things you can do inside of R real easily. And if you remember, one of the modules we brought in has a rpart.plot. We're going to take that and we're going to dump that into the PRP for the tree. And we'll just go ahead and hit enter. And this is fun. Let me move this over so you can get a nice view. You can see how it actually split it up. And let me just rerun that again. Now that I expanded the right, you'll see right here where one of the biggest splits was whether the person was male or female. I didn't know that was probably one of the biggest breaks as far as lowering the entropy and increasing the information gain. And then once sex is male, it came down here and it said you're not going to survive. I guess the men were throwing themselves overboard on the boat. I don't know. Maybe they're being very gallant and letting the women and children survive, which is what I hope that means. So once you know that it's not a male and it's a female passenger, if you were in class 3 or above, you had a high chance of surviving. If you were less in class 3, class 1 or 2, then it was based on age. And so you can see where age was greater than 19. So anybody over 19 had a high chance of surviving. And then if they were, or less than 19, I'm sorry, if the age was, a little confusing on that one. But if the age was one side of 19, they probably survived. If not, then it said, hey, if your age is less than 60, you probably survived. And if not, people who are older probably didn't make it out of the boat in time. So elderly have a much higher risk, which you would expect. You'd expect that to be the case, that elderly would have a hard time getting off into the lifeboats. And they would probably step aside for the younger generation. I know I would. So that might be more of a social norm statistic as opposed to a survival rate. Let's go ahead and put this back on over here and see what else we can do with this data. If you're working with the shareholders, it's good to have a lot of tools as far as how to display. They'll want to see this number here where you say, hey, this is what the confusion matrix looks like, and we got a 0.79 accuracy. That would be like the number one thing you would talk to the shareholders about. Other data scientists care about the p-value and the information rate and information like that. But this is really the core right here. This is how much data, and this also shows them how much data was looked at. So you can actually just add these numbers together and you can see how many different people were in this particular data set, or how many lines in the data set. But we go ahead and visualize the 2D decision boundaries. And let's take a look at that. That's kind of fun. It's a little bit more complicated, so I'm not going to go into it in too much detail today. Now, the guys in the back put this code together for me, which is great. So I'm just going to paste that in, because like I said, we're not going to go into it in too much detail. I want to just show you that there's some other ways to display the data that is not just this nice little tree over here, which gives us a little bit more maybe view of what's going on. As you dig deeper into data, that becomes very important. It might not be something so simple where you can look at, in this case, 1, 2, 3, 4 nodes. So they have 4 major nodes that they split the data in. So when we're looking at this, we're going to go ahead and create a set test equal to test, comma, C241. We're just assigning color column to go with the data. Okay? That's what that is. And then we're going to take set and have it equal to test. And we'll do x1. And we're going to set that equal to minimum set of 1 minus 1, max set of 1 plus 1 by equals 0.01. They had to play with these numbers a little bit to get this to look right. So we're creating a sequence on here from the set we created, so our test set. And then x2 is also creating a sequence based on different values. And then we're going to put that all into a grid. So let's go ahead and run that through all the way down to the grid. And they'll make a little more sense when we add the column names to the grid, okay? So we'll set our test. We'll create our x1 sequence and our x2 sequence. Remember, a sequence is just like, in this case, starting with 0.1, it's like 0.01, 0.02, 0.03, 0.04. So we're going to create a grid with all these values separated by 0.01. So that's all we're doing right now. And let's go ahead and set that up. There's our grid. And then we want to go ahead and create some column names. And for our grid set, we're going to have our C class and age. So we're just doing the class and the age on here. Remember, we did sex also before, so it's just class and age on this chart that we're pulling out. And we're going to create a Y grid, and the Y grid is going to equal tree survived predicted. Okay, so here's our Y grid and our predicted values on there. Now we're actually going to do something. We're going to plot, and we're going to plot the Y grid. Oops, hold on, let me see what's in here. And let me go ahead and just run the plot. It's got to be the there we go. So let's take a look at this and see if we can make a little sense of this code and what's going on here, because there's a couple of things going on. What we've done is we've plotted a decision tree classification data set. We've done our plot, and we have our set. So our set's equal to our test data. And then we have our main. We went ahead and give it a name, decision tree. And then we have our xlab and our xlimit, and we've set those up as class, with our ylab equals age, and our xlimit equals range, x1 comma ylimit equals range of x2. And when you look over here, you can see that we have age on the left and class on the bottom. And so based on age and class, and so once we put in this nice graph here, we want to go ahead and add our contours and our points. So let's go ahead and run that, and I'm going to run all three of these so we can see all the colors come in on the graph. And this is actually going to take a little bit, because remember, you can make it go a little faster by changing a couple of the notes up here. When we did 0.01 from the min to max, by changing that to 0.1 or other values, you can actually, it'll run a little quicker. And we're going to create a nice little decision tree classification test set just to see what that looks like and how that data displays. Now, that was taking so long to run with 0.01, I went ahead and just did a 0.1. So instead of filling the whole page with different colors for a really pretty view, now I just have these different colored lines coming across. It gives us another model that we can show for whoever you're working with, in this case, your shareholders of the company or the individuals who you're posting to the web for. And you can see where we have the green and the red, and we've set those up to identify from the decision who's going to make it and who's not based on age and class. Now, my favorite one on this, and I'm going to go back and just highlight this really quick, was, let me just rerun that, go back to PRP tree where we display the tree. And that's where we split it in part, because this information gives us some keys that we can then use in other models. So it's good to know that sometimes what you're taking comes out, and maybe you create a bucket for people under 19, between 19 and 60, and over 60, and different things like that, so you can actually put people in buckets in a class age split. Just a quick note on there. Again, lots of different things from which you can display the data, and you can see how we use the decision tree to figure out chances of somebody surviving based on their class and their age. Let's go ahead and take a look at the decision trees. So let's go ahead and talk about another algorithm, decision tree. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. It is a tree which helps us by assisting us in decision making. Let's look at the basic terminologies to understand decision trees. We have our root node, we have a splitting, we have decision node, and then those split into terminal node, decision node, terminal node, terminal node. And each decision node continues to split until it ends in a terminal node. Note, A is the parent node of B and C. Also note we call the terminal nodes leaf nodes. You can also see that we have a branch or a subtree. So when you have a split, everything under that split under one side is called a subtree. You cannot build your decision tree without knowing entropy and information gain. Entropy. Entropy is the measure of randomness of impurity in the data set. So we have here a bunch of fruit, and you can see we have, it looks like apples, oranges, and bananas. It's very chaotic, so it's a very random data set. It has a very high entropy. And if we take out one group, let's say we take out the apples, it's a little less random. Now we only have bananas and oranges. So it's a less random data set, and we have lower amount of entropy. Entropy is a measure of randomness or impurity in the data set. So when you have a homogeneous data set, we will have entropy equals 0. And here you can see it's all oranges. An equal divided data set will have an entropy equal to 1. So here we have half, or what is it? Looks like a couple bananas, a couple oranges, and a couple apples. So everything is equal. So we have an entropy of 1 on there since there's 2 of everything. Information gain. It is a measure of decrease in entropy after the data set is split, also known as entropy reduction. So we look over here and we have an entropy equals E1, and the information gain as we split the bananas out, the size becomes smaller, and you'll see that E1 is going to be greater than E2, or we measure E2 of the apples and oranges in this case. If you love your fruit, it's probably getting you hungry right about now. And then the information gain from our level 2 equals E2 minus E1, where E2 is greater than E3. And as we come down here, we'll see that the E3 is now the third level where we split the oranges and apples out. And each time that entropy becomes less and less and less, until in this case we have an entropy of 0, since they're all homogeneous in their order. All oranges, all apples, all bananas. So let's take a look at the use case decision tree and actually put this into code and see what that looks like as we go from theory to script. And to predict the class of flower based on the petal length and width using R. And you'll see here we have these beautiful irises, probably the most popular data set for beginning data analysis and statistics. We have the Setosa, the Virginica, and the Versicolor. Let's install the packages that will help us in the use case. So because we're doing decision tree, we have rpart.plot, and then we have the library rpart and the library rpart.plot. Let's go ahead and take a look at that. And if you remember, we have 2 ways of installing it. We can do the install packages. We did that earlier. Here we go, install packages, using my up arrow to get to it. Or we can go up to Tools, Install Packages, and I can do rpart and rpart.plot, and then go ahead and hit the install. Packages that will be updated as are currently loaded. Oh, it looks like some of them are already loaded. That's fine. We'll just go ahead and update those. And once we have those updated, let's take a look and see what we have going on here. Oh, it's still loading. Let's go ahead and type in library rpart and library rpart.plot. So we want to bring it into our console that we're working in. So up and now we just download the packages, and now we want those libraries available to what we're doing. So the iris, although it's built into the R package download on the basic download, we actually have to install the data or bring the data in. So we're going to do the data iris, and then we're going to do the string iris. And let's just flip back on over to our RStudio and set up our data iris, and then we're going to do string. Before we do that, let's do head iris. There we go. And you can see the head has sepal length, sepal width, petal width, species. In this case, the top part's all Setosa, and each row gets a number. And then we did the string iris, and that comes up with information. And if we flip back to our slide, you can see here the structure of the database under string is it's a data frame. It has 150 objects, 5 variables each, so each one has 5 variables. All features are numerical except species, which is categorical as it is our target variable, which we want to predict. So we want to predict whether it's going to be a Varicosa, Versicolor, Setosa. So you can see here we want to predict all the features are numerical except species, which is categorical. It is our target variable which we want to predict. And you can remember that's the Setosa, the Versicolor, the Virginica, the 3 different categories we saw earlier in the beautiful pictures of the flower. And so we're going to go ahead and use the set seed to decide the starting point used in the generation of sequence of random numbers. Remember, we set the seed so that if we ever want to reproduce what we're doing, it will reproduce the same thing each time because it's using the same randomizer seed. Bring slightly different results, but depending on what you need it for. And then we're going to generate random numbers using runIf. And the question is, why do we want to create random numbers on here. It's kind of an unusual thing to do for in-rows iris. And let's go back and just take a quick look here. Actually, we want to go back to our RStudio. And you're going to notice when I did the head of iris, what did I have? I had setosa, 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 setosa. So the data is organized by species, and it's already grouped them together in the data set. Well, we want to randomize that so that doesn't affect our output. And then we'll go ahead and take and create our iris ran, where we recreate the data frame based on a random order instead of setosa all being grouped together. Let's go ahead and put that into our RStudio and set.seed, and we'll match their number. It's 9850. This way we'll have identical results to what they're doing on the slides. Then we're going to set the variable g equal to run if, and base this on in-row of iris. And finally, we're going to create iris underscore ran, and we're going to assign our variable we're creating iris underscore ran, and we'll set that equal to, we're going to do that to the original database. We're going to set that equal to iris, and we need brackets because we're assigning the variables, and we want to change the order. So there's an actual command order we can do. It's going to be order G. So this means all the rows in the order that G is. So we just randomized all those rows. And then we want to keep all the columns. We'll just put a comma and we'll leave it blank for the columns. So now iris ran will have some randomized rows coming in. And if we do head, let's just do this real quick, iris ran. We can see that it's no longer setosa, setosa. We now have virginica, setosa, versicolor, setosa. And you can see the row numbers at the beginning. We have 103, 20, 63, 17. So they're randomized on there pretty well. Now that we've done a little data manipulation, we can go ahead and build our model using our part as follows. And one of the things I want you to notice here is we're going to build our model for our R part on the first 100, because our data equals iris ran 1 to 100. There's 150 objects, so we're keeping a third of them off to the side. That way we have our training set and our test set already pre-built because we randomized the rows going in from the beginning. And then once we've done that, we want to go ahead and print our model out and take a look at it. Let's go ahead and put this into our RStudio and take a look. And so we have our model. We're going to call it model. That's our variable name that we're giving it. We're going to assign that our part. And in brackets, we'll start with species, and we want to correlate species to all the other columns. So how do we do that? And the shorthand is just to put a period there. And then we're going to put a comma, and then we want to set our data equal to iris ran. That's the data we put in there. And remember I said we're going to do just the first 100 rows, so we can save the last 50 for testing. So we can do that simply by doing row 1 to 100. So in R you start with 1 for your rows, and because we want all the columns we just put a comma, and that denotes that we're going to use all the columns in here. And in the R part there's different methodologies. We're using the method equals class. And you realize that we're doing a classification between the 3 different types of flowers, and so this is what we want to go ahead and set up our model with. And when we run that, we've now created a nice model for us. We can go ahead and just type in model, hit enter, and you'll see it'll print out a bunch of information about our model to let us know what's going on in there. And let's just break that down and see what that looks like. So we have our target, our predictors, that's species, and it's going to relate to, we used a period to denote all the columns. We're going to take the first 100 rows to train the data, and we have the defining method to be used as classification. That's what the method equals class is. And what we want to do next is we're going to do a plot and take a look and see what this actually looks like, a little visual here, which is nice. And we simply do that with our plot for the model. And let's break this down a little bit and just see what that looks like in the R setup. And we do this rpart.plot, a little bit of a mouthful there sometimes. That's part of the rpart package or module. So when you imported this in, it also included its own plotting format. And we're going to send it our variable model. And there are actually a number of types of plots listed for rpart, but we're just going to do type equals 4, fallen.leaves equals t, and extra equals 104. Let's go ahead and hit enter on there. And you'll see right over here on the right hand side it goes into our plots. We just enlarge that. We have our versicolor, our setosa, versicolor, virginica. And let's go ahead and break that down. As you can see down here, it represents the tree as it splits. It looks at it and says, hey, if the petal dot length is less than 2.6, it's going to be a setosa. So 34% of them fall into that category. And if the petal length is greater than 2.6, then looks at that and says, okay, now I have 3 different variables. We're going to split it again. Petal width is less than 1.7. It's going to be a versicolor, and if it's greater than 1.7, it's a virginica. And so you can see here, it's a very simple tree it forms. It's only got a couple levels. You can see a branch off to the right. Very nice depiction of what's going on as far as the model now that it's created. But once we create the model, we need to figure out, is this model any good? So let me go back over here and let's go back to our slides. And the first thing we're going to do is we're going to take our test data. Remember, we saved 50 rows for the end to go ahead and run a predict on there. So let's go ahead and run that prediction. So we'll call it model_predict. And we're going to hit a wrong button there, to predict. And what are we going to predict? We're going to predict our initial model. And we need to send the data, so data equals. And we don't actually have to put the data part in, we just put in iris_ran. And then we want to do just the last 50 rows. And we denote that by 101:150 and then comma, and we'll leave that part blank since we want all the columns to show up. And then finally, this is a classification, so we need to let it know that type equals class. There we go. And let's just see what that looks like. Model predict. And so this is what the data is put out as, is it says whatever this is, 131 is a virginica, number 10 is a setosa, line number 95 is a versicolor, and so on all the way through. What we really want to know is how good our model is. So we're going to go ahead and install a couple more packages. We're going to install the packages required to use the confusion matrix. And to do that, we're going to install caret and E1071. And then, of course, we want to set them to our project by using the library command. And so we can simply install packages, and we want caret, and we'll go ahead and just do that right there. There's caret installed. And we went ahead and did the install for packages E1071. As it goes through there, it's a really quick install compared to the caret. And then once we've installed the packages, we need to load it into our workspace. So there's our library caret. Oops, I should load it in there. There it goes. And once that's loaded, we'll go ahead and also load the, or set the library to the E1071 so that we have both those libraries available to us. And here we go, library, and then this one is E1071. And now these two libraries are fully available to us. And then we're going to use these tools to create the confusion matrix. And this one, confusion matrix, this is the iris_ran. And then we'll go ahead and put the brackets here, and we're only going to do 101 to 150. And then we only want the first 5 columns, not the last 5 columns, the first 5 columns. So 5 in there, and we'll set that to our model predict. And then when we hit enter, it's going to head and just print out all this information. So right here, we're looking at our confusion matrix to see how everything kind of balances out. Let's go over that and see a little closer what that actually means. So the first part we see is a reference. And in here we have our prediction, because that's what we called the column, if you remember correctly. And we have it for setosa, versicolor, virginica, and then we have setosa, versicolor, virginica going down each side. And the way you read this is, if you look at this, we predicted 16 out of 16 setosa. And then versicolor, we predicted 13 of the versicolor, and then 2 of those we predicted as virginica. So we were wrong on 2 of those. And with the virginica, we predicted 17 correct, and we had 2 wrong that were versicolor. So we look at the overall statistics on here, and we have an accuracy of 0.92 and a 95% CI. That's pretty good as we're going through here. Those are good deals on that. And there's a lot more information as you go down this. The one thing I want to remind you on this as we're looking at these predictions, and this is also true for the linear regression model we looked at earlier, when we talk about the accuracy, that is the accuracy on this data. And we say that as a programmer to make that a very clear distinction, because if you're in data analysis, you should cringe if I say, this is a 95% accurate model without that put in there, because bad data in, bad data out. We won't go into detail right now on that, but that is very important to note that whenever you quote any of the accuracies on here or you discuss any of these values that come up. Today we're going to cover the random forest in R. If you remember from part 1, we did the decision tree. And no one wants a poor lone standing tree out in the field. We want a forest. And so we're going to cover random forest. Just a little play on words there. I'm sure the people who designed it also knew that too when they were thinking about it. So what's in it for you? What is a random forest? How does a random forest work? We're going to cover applications of a random forest, some of the terms you need to know when using a random forest, and then we'll go over the use case in R, predicting the quality of wine. So let's start a little bit with exploring what is a random forest. And welcome to Raphael's vineyard in, I don't even know how to pronounce that, in Alsace, France, the largest wine production region in the world. So they have centuries of wine production and data they've collected on how to make their grapes and grow them and how to properly get the right grapes and ferment them. Like Raphael, winemakers around the world are facing a grave problem. So let's meet the man himself and try helping him out. What is a random forest? We're going to come back to the vineyard, but we're going to look at some other examples along the way too. Open up the door, and of course here comes Raphael. I'd probably look closer to Raphael than I do to the young lad with the beard. Hey Raphael, so tell us how it's going. Not as good as before. Not many people work in this profession anymore, so every stage of production has gone slower. If only we could somehow speed up the process. Well, lucky for you, I'm a machine learning engineer. How about we automate the quality prediction process for wine? Let me begin by telling you what machine learning and random forest is. Machine learning is the science of applying algorithms that allow a computer to predict the outcome without being explicitly programmed. Random forest is an ensemble machine learning algorithm. So we're bringing in different pieces and then putting those pieces together. It operates by building multiple decision trees. Remember I told you we don't want just a lone tree out there, we want a forest? They work for both classification. If you remember from part 1, we had our vendor with his broccoli and oranges. I think he also had carrots. And it also, the output given by the majority of its decision trees is the forest final output. So if you have a number of decision trees, you have 5 decision trees and 4 of them say it's broccoli, then it's probably broccoli. And you can also use it as a regression model. The output given by the majority of decision trees is a forest final output, just like you do in classification. You can also come up with actual values and numbers as a regression model. Could you explain how a random forest works in layman terms? It's always a good thing to explore the information on something a little bit easier to understand and see. Sure, let's consider the case of Sam, a high school student. This so reminds me of my own high school student who's just started his first year in college, asking all his friends. So Sam is confused on which course to take up. So he's trying to figure out what his next class is going to be at school. Should he take music lessons, dance lessons, math, science, maybe social studies? So he decides to ask a couple of his friends for suggestions. And Sam approaches Jane first. So he comes up to Jane and says, hey, which of these classes should I take? And Jane asks Sam a few questions based on which she can suggest. Theoretical? Do you like theory? No, he doesn't like the theory part. Calculative? Do you like calculative? And he goes, yes, I like doing calculations. And so Jane, based on a couple questions, she has her little decision tree there going. She goes, mathematics sounds good. So Jane forms a decision tree based on Sam's response and gives her suggestion. And of course, this is based on Jane's views and her history and the data that she's collected over her years in high school. Next, Sam approaches Bella. Bella asks him, hey, do you like the field of science? And Sam goes, yes. And then Bella goes, do you like new in industry? You like new things coming up in industry? And Sam goes, yes. And Bella goes, you should, similar to Jane, Bella also forms a decision tree based on Sam's response and gives her suggestion and says, hey, how about artificial intelligence? Sam's like, oh, artificial intelligence. So Sam next asks Terry for his suggestion. And Sam goes, do you like scoring things? And he goes, yes. And he goes, do you like theoretical? And he goes, no. And he comes up and says, mathematics. So you have 2 people saying mathematics and 1 person suggesting artificial intelligence. Since 2 out of 3 friends suggested math, Sam decides to take mathematics. And there's a lot of subtleties in this example. It's actually a really good example. Some of the things we run into in data science is when we collect data, and we collect from different sources, we might have data from one source that measures one thing or one set of instruments. And we might have data from another source that measures something else. We saw that with each of his friends are measuring different things and asking different questions. That's a little bit beyond the scope of this particular tutorial. So let's go back to our wine cellar. So you see, more the number of decision trees, more accurate will be the prediction. Random forests have a number of applications in market already. If you've been watching any of our other tutorials, you'll see that these are very common. We have in banking, it can be used to predict fraudulent customers. It is used to analyze symptoms of patients and detecting the disease. In e-commerce, the recommendations are predicted based on customers' activity. Stock market trends can be analyzed to predict profit or loss. Most recently, I was watching a review on weather here in the United States and the data they pull in for that. And one of the top weather places actually uses 5 different models. Random Forest was one of them, I believe. They use 5 different models to predict the weather, and depending on what the models come up with and what's going on, some of the models do better than others. I thought that was really interesting. It's important to note. So when you see us repeat the same things over and over, and you're looking at the different machine learning tools, you realize that we use multiple tools to solve the same problem, and we can find the best one that fits for that particular situation. So let's see how that fits back in our wine production. To help speed up the process of wine production, we will automate the prediction of wine quality. Suppose our random forest builds 3 decision trees. We have the first decision tree, which is going to divide everything by chlorides, less than 0.08, and it's either yes or no, and then it's going to look at alcohol greater than 6, yes or no, quality equals high, quality not so good, and if the chlorides were greater than 0.08, quality equals low. So there's our first tree. And then our second tree is going to split it on sulfates less than 0.6, and pH less than 3.5. And again, we have it coming down here that if the pH is low and the sulfites are low, the quality equals high. If the pH is a little higher but the sulfites are low, it's not so good. And if the sulfides are greater than 0.6, we have a quality equal to low. And then we'll do a third decision tree. We'll split it based on pH. And we can see below how that tree looks like with our sugar less than 2.5. If not, it's a quality equals low. It's a real low quality. And if it is less than 2.5, then the pH decide whether it's going to be a quality high or not so good. And if we track one of our wines down the list, we'll look at it and we'll say, oh, 2 out of 3 decision trees indicate the quality of our wine to be high. The forest predicts the same. So this sounds promising. So let's go ahead and dive in and see what that actually looks like. So this is the data set that holds all the attribute values required to predict the wine's quality. And I'll pull this up in a spreadsheet in just a moment. But you can see here we have fixed acidity, volatile acidity, citric acid, all the way to quality. And then quality is like a 4, 5, 6, or 7, I believe. And this will be done in R. So let's go ahead and get started on our coding. We'll be using RStudio. Before we dive into RStudio, I always like to open up the data in the spreadsheet and look at the actual data that I have. And they've called it winequality-red.xls, so it's a spreadsheet, a Microsoft spreadsheet. And when we open it up, we'll see that it matches what we had before, as far as the slide was showing us. We have 12 different columns. The first 11 are our features, our fixed acidity, volatile acid, citric acid, things you always want to look at when you're looking at your data. And we've done this before in the part 1, but just a reminder, we want to note that we have decimal places here, float values, in a lot of these things, especially the first number of columns. Our free sulfur dioxide looks to be an integer, but it varies a lot. So we have, I see some values all the way up to 51, 7, 4. So we'd probably keep this as a linear model kind of thing. Same thing with the sulfur dioxides, densities again, decimal places, sulfides, alcohol. Quality. I want you to note in the quality that we only have a few qualities here. This isn't like a spread between 0 and 100. It looks to be 3, 4, 5, 6, and 7. And so when we start looking at the process, we can have the option of either doing this as a series of integers or float values going from 3 to 7, or we can convert that to a categorical, 3, 4, 5, 6, and 7 being the categories. But we'll look at that in the coding here in just a minute. And finally, you'd want to go ahead and scroll down through the data and just look for missing data or anything weird. Obviously, working with big data, you wouldn't be able to do that. If this was spread across numerous computers and you had millions of rows. We have, 1,687 rows here, so it's a nice size spreadsheet, still considered a small data set. Let's go ahead and switch over, and let's take a look at this in the R. So here we are in our RStudio, And if you remember, it comes up automatically in 3 panels. I have my font on fairly large to help out. The upper left panel is a file that's open. You can have multiple files and tabs open, as you can see on mine right now. I'll probably close most of those in just a minute. And this is where you can put in your commands. Then you can execute these commands by either clicking on the run box or Control-Enter is the hotkeys for that. And all that does is then puts that down in the console and executes that line of command. You could just paste these directly in the console. I've certainly been known to do that if I'm loading up some data and I just want to take a quick look at it in R because I'm doing the coding in something else. Or if I just want to do a quick explore before I dive in and figure out what needs to be done. That's one of the tricks you can do. And then on the right hand side we have our environment, history connections. We mainly are going to just be sitting on plots, and I'm just going to minimize this for right now out of the way while we dive in. If you haven't yet, you do need to go ahead and install the package Random Forest. I'm not actually going to do that because I've already run that. We don't need to rerun that. But I am going to go ahead and import it into our project with the library and then Random Forest. And we'll do the Control-Enter. You can always hit the Run button up there too. And then now the library has been uploaded in there, and you can see down below it takes this and just copies it and pastes it down below and runs it in our console. And then just a quick troubleshooting thing. My Java happens to be the developer's Java. The latest release of the developer's Java from last week is clashing with my R and rerouting my Java files. So chances are you don't need to look this up or find out where your Java is. But there's a JRE folder. If you do have an error that comes up in the next library, you look that up. It's usually under Program Files, Java, and you'll see JDK, depending on what version you have on there, and then find that JRE folder. And I'm just going to set the environment on there. You have to do that every time you run the script. So with R, there is a place in R where you can set it permanently, but generally it's set to whatever your system variables are set to, so you don't want to mess with that. So you just want to put this in your code if you're having problems, and you can always take it out. And then we need to go ahead and bring in another library, and we're going to be importing the spreadsheet. So it's the XLSX, since it's a Microsoft spreadsheet. And I'll go ahead and run that. Now let's go ahead and create a variable path. We're going to assign to variable path the location of our folder. So this is a very lengthy one. You'll have to copy and paste it off your computer. My name is Richard, and you can see it's under C column Users, Richard's Documents, Docs Business, Simplilearn, Marketing, Random Forest, and then the actual file, which is winequality-red.xls. So I put in the whole path in here. And you could also set the computer path to whatever folder you have it in, and then just use the name of the file. But I went ahead and did this because a lot of times it's good to be aware where your paths are going and where you're pulling your data from. And again, I went the Control-Enter, so you'll see that pushed the line down below and ran that line, so our path is now set. And then let's create a variable called data, and we'll assign that to a read. And we're going to be reading, let's see, where is it? There it is, on spreadsheet. And before I put in, we need the path, but we also need one more thing on the spreadsheet. Because it is an Excel spreadsheet, we need to know which page we're on. So let's go look that up. And in the spreadsheet, it might be a little hard to see because it's a very tiny font down there. But you'll see the page tabs on the bottom. This actually has 2 different pages, and we want page 1 for this project. So let's flip back over and put that in our code. And the term they use is sheet index. I always have to look that stuff up. And it was sheet index of 1. We'll go ahead and execute this. So at this point, we've now loaded the data into the variable data. And it's reading those in. I think there was a couple thousand rows of data in there, so it takes it just a moment to pull it in. Once I have my data in there, I always like to do something like this. Data, and I always forget in R it's head data. And we can run that. And you'll see it prints out what we looked at in the spreadsheet. So we have our fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, free sulfur, all the different things. We're actually looking for quality, so you want to keep that in mind, that quality is the final setting. Is it a 3, 4, 5, 6? What is the quality on there? And the first thing we need to do is we're actually going to take the data quality, and let me see, quality, there it is. In R, the $ means that you're looking at one of the columns in here, or features as it is. So we see data $quality in R, that means that's what we're going to be editing. And what we want to do is we want to change the quality just a little bit. And so we're going to set it equal to. Now we're not assigning a variable, we're altering it. So data $quality equals, and we want to do as is one of the functions in R, and we're going to do as a factor. And then data quality, because that's what we're actually editing on there. And let's stop just for a second and look at this. Factor takes this and looks at the data as a categorically. So instead of it being on a continual scale of 0 to 100 or something like that, it actually looks at it as category of 5, category of 6, category of A, category of cat, category of dog. They're yes or no categories versus a continual. Now there's a lot of different things in here that we could do the same thing with, but all of these really are linear numbers, 7.4, 0.70, sulfur dioxide 3467. So we really don't need to mess with any of the other variables in there, but we do want to go ahead and set this up. And we'll come up here and we'll do our control enter, and it'll run it down below. And you'll see data quality equals as factor data quality. So we've now turned that into a factor, or into a categorical data. And so let me just bring this down a little bit. The guys in the back did the rest of this next piece of code. There are so many different ways, and if you have been looking at any of our tutorials, this should look kind of familiar. This is one way to do it. And you'll see we have our training data and our testing data. And so what we've done here is we have a data set size equals, and we're just going to do by the row. And so we want 0.8, or 80% of the data is going to be our training set to train our forest. And if you train a forest or any machine learning model, of course want to test it. So we're going to save 20% of the data for testing. And when you look at this, we have the index, which we set at 80%, comma, and then a negative index. So that's the remaining setup. So it goes from that index on. This is our notation for sorting out that data. And then we create the index, and we use the term sample. And this is just going to go in there and set our different samples for our in-row size, data set size, and everything. So we have an index now. So the data is indexed, and we're just going to pull off the first set of index and the end of the index for our data. And we can run all of this in one shot. We'll go into code, and we'll run selected lines. And so now we have our data in here. We have our training set and our testing set. That's what we wanted to get to. So once we've formatted all the data, then we get to the next real easy step, which is a single line to bring in our random forest. So let's go ahead and we'll use the variable RF, standing for random forest, and we're going to assign, if you remember correctly, we brought in our library random. If you wonder why I go up here all the time, it's because I'll forget which letters are capitalized in some of these because I switch between packages so much. But it's random with a capital F for forest, random forest. So the RF is going to equal random forest, and of course we start by telling it which column we're trying to predict. And of course you can always go down here and double check. We're running this on the quality. There we go, quality. And we're using just that column all the way to the end. And then we've added, our team in the back has gone in and played with this a little bit, and we'll go a little bit over what they did. But I'm going to put in the values that they have set for the different options in the random forest. Before I do that, it would help if I tell it what data to use. Data is going to equal our training set. And then we have the variables that they've put together. And let's just talk a little bit about what these different variables mean. So, mtry and ntree. These are some of the variables you play with the random forest. The mtry, not so much. When they first put it out, I think mtry was very common. 4 is a good value. I can't remember what the default is, but it's probably 3, 4, or 5 or something like that, depending. I think it depends on how many features you have going in there. So you could even just leave this as a default without too much troubles. The end tree, this is where it gets important, and I'm going to make this 2001. One of the suggestions is to always make this odd, like a tiebreaker, just in case. The default is like 500 or 501. And then finally we have importance equals true. I can't remember what it defaults to, but generally you want to set the importance equals to true. It actually looks at the correlation between the different features to make sure that there is some kind of correlation as it's doing its calculations. So our one line of code is going to assign our random forest and go ahead and train our random forest all in one execution. So this whole thing has been centered around getting to RF set to the random forest. And let's go ahead and execute this variable, or this line of code. And you'll see it takes a little bit down here to execute as it goes through and sets it up. And you'll see it probably takes a minute or so to execute the code depending on the size of the data and how good your machine is. And then with all of our data, we can start looking at the answers. We'll just do RF, we'll execute that. And you'll see that the random forest does a nice job. You can see right here it has our data equals training. It basically goes over everything we talked about. And you come down here and it has a confusion matrix, which is nice. We always like our confusion matrix when we're talking to our shareholders and explaining what the data comes out with and how it trains. And we can go ahead and plot our RF. Let's see what that looks like. And as the number of forests grows, remember we set it to 2001 forest, you can also see how the error comes in, how the different error on the different variables. This is kind of a nice graph that gives you an idea. It might help you adjust whether you really want to do 2,000 different forests. You might actually truncate this off at around maybe 800 because you notice the lines kind of continue on. Again, this is just still on the plot. And of course the next step is we need to go ahead and predict. Remember we split our data into two groups. So let's go ahead and get a result. We'll call it result and we'll assign this one. There we go. We'll set this to a data frame. There we go, there's our data frame. And then, let's call this, we have our test quality, because that's what we're setting up on our test group with the quality on there. And then we want to have a predict, nice little keyword there to go ahead and run our random forest. And then we tell it that we're going to predict using our RF, our random forest, our testing group. 1 to 11 is what we're using. Type equals response. So let's go ahead and execute it. That's a mouthful on there. Somewhere I left out a comma in there, so it gave me an error. But you can see right here, we've set in there, now we have a result. And just real quick, we could do the head of the result, comma 5, and just take a look at the first 5 lines. And you'll see we have the actual value and what we predicted over here. And we could also just do all of the result and just see what that looks like. Oops. And print that out. And so it has all the different data we're going through on there. And finally, let's just go ahead and plot. There we go. We'll put plot up here. Plot. And let's plot the result. And just see what that looks like. Maybe not the best one to show to the shareholders, but it does give you an idea. On the left, on the y-axis, you'll see that it predicted 8. And this tells you that a lot of the 8 and the 8 scale was probably gave us about 50% came up there at 8. Really, maybe 50% it didn't guess right, but it did come up there and say that it was at least a 4, 5, or 6, even where it was considered an 8. And so on. You can see these different blocks coming in, so that if you line up the 3 with the 3, 4 with the 4, and you kind of cross-index them, a heat map would probably do better. But for this example, we'll just do a quick plot of the data as far as how it works. And you can again see the results that we predicted over here, and you can look those over. Of course, back in the wine cellar, we're talking to our vineyard owner. And if you remember from before, we looked at this chart right here. The error rate is 29.05%. Therefore, our accuracy is 70.95%. If you're doing a vineyard, that's probably pretty good accuracy. And always check your domain when you're sharing this stuff, because if you're doing something that's life or death, maybe 70% accuracy might not be so good. But if you're looking at where you're going to distribute the bottles to for the wine and who's going to drink it, 70% accuracy is pretty good for that. That's probably a lot better than having no accuracy whatsoever and not even knowing what wine's going out to who. So we have automated the process of predicting the quality of wine. I myself prefer to predict it by sampling it. That's great, thank you. I'd like to visit this guy and sample his wine and find out just how good his different vineyards are.
So now let's understand what an SVM is. And if you want to understand support vector machine, you really need a good example. And I know that cricket is a wonderful game. I don't know a lot about it, but I know it's very popular around the world, and we're going to use cricket as an example of SVM. So we'll classify cricket players into batsmen or bowlers using the runs to wicket ratio. So a player with more runs would be considered a batsman, and a player with more wickets would be considered a bowler. And if we could take a data set, say of people, cricket players, with runs and wickets in columns next to their names, we could create a plot, a two-dimensional plot. In this example, clear separation between cricket players considered bowlers and those cricket players considered batsmen. And you don't always have a data set this clean where there is a clear segregation of data, bowlers versus batsmen. But for the sake of understanding SVM, this example does well. So before we do any separation, before we apply any high-level mathematics, let's just take a look at an unknown value, a new data coming into our data set. And that datum, we don't know what class it belongs to. That datum is a bowler or a batsman, we know that much, but we don't know, should we consider that cricket player a batsman or a bowler? And so we want to draw a decision boundary, some type of line separating the two classes, so that we can use that decision boundary to classify the new data point. Of course, we could draw lines. There's a yellow line, a green line, a blue line. There's actually not just 3 lines, but an infinite number of lines that we could draw between those two classes. So which one do we pick? And this is kind of reminiscent of simple linear regression, where we find the line of best fit. We want the line of best separation. We want a line that clearly separates those two groups as much as possible. Once we have the correct line, we would be able to classify the new data point. But in this example, you can see if we pick yellow, the new data point would be a bowler. But if we picked green or blue, the new data point would be a batsman. So we need the one that best separates the data. What line best separates the data? We'll find the best line by computing the maximum margin from equidistant support vectors. Now, support vectors in this context simply means the 2 points, one from each class, that are closest together, but that maximize the distance between them, or the margin. So the word vector here, you may think, well, he really means points, data points. Well, in 2-dimensional space, yes. And maybe even in 3-dimensional space. But once you get into higher dimensional spaces, when you get more and more features in your data set, you have to consider these as vectors. You can no longer really describe them as points, so we call them vectors. And the reason they're support vectors is because the 2 vectors that are closest together, that maximize the distance between the 2 groups, support the algorithm. So that's why we call them support vectors. So if you look at our example, there are a couple of points at the top that are pretty close to one another, and a couple of points at the bottom of that graph that are pretty close to each other. And I'm not really sure, looking at the graph, which 2 are closest, but clearly those points are the ones we need to consider. The rest of the other points are too far away from the rest of the other points. In other words, the bowler points are far to the right and the batsman data points are far to the left. So we'll look at these 4 points to begin with. Mathematically, we would calculate the distance among all of these points, and we would minimize that distance. Once we pick the support vectors, we'll draw a dividing line and then measure the distance from each support vector to the line. The best line will always have the greatest margin or distance between the support vectors. If we consider the yellow line as a decision boundary, the player with the new data point would be considered a bowler. The margins don't appear to be maximum though. So maybe we can come up with a better line. So let's take two other support vectors, and we'll draw the decision boundary between those, and then we will calculate the margin. And notice now that the unknown data point, the new value, would be considered a batsman. We would continue doing this, and obviously a computer does it much quicker than a human being, over and over and over again until we found the correct decision boundary with the greatest margin. And in this case, if you look at the green decision boundary, the green line appears to have the maximum margin compared to the other two. And so let's consider this the boundary of greatest margin, and now classify our unknown data value, and now clearly it belongs in the batsman's class. The green line divides the data perfectly because it has the greatest margin, or the maximum margin, between the support vectors. And now we can have confidence in our classification that the new data point is indeed a batsman. Technically, this dividing line is called a hyperplane. And the reason it's called a hyperplane will become a little bit more evident in a few minutes. Generally, in two-dimensional space, we consider those lines. But in three-dimensional space and higher dimensional spaces, they're considered planes or hyperplanes. So we always tend to refer to them as hyperplanes. And the hyperplane that has the maximum distance from the support vectors is the one we want. So, sometimes called the positive hyperplane, d plus is the shortest distance to the closest positive point, and d minus, sometimes called the negative hyperplane, is the shortest distance to the closest negative point. And the sum of d positive and d negative is called the distance margin. So if you calculate those two distances and add them up, that's the distance margin. And we always want to maximize that. If we don't maximize it, we can have a misclassification. And you can see the yellow margin is much smaller than the green margin. So this problem set is two-dimensional because the classification is only between two classes. And so we would call this a linear SVM. Now we're going to take a look at kernel SVM. And if you notice in this picture, this is a great depiction of a plane, not a line. This is three-dimensional space. So that's the plane that separates those two classes. So what if our two-dimensional data looks like this? What if there's no clear linear separation between the two classes? In machine learning parlance, we would say that these are not linearly separable. How could we get support vector machine to work on data that looks like this? Since we can't separate it into two classes using a line, what we're going to do, and clearly there's no line, I mean, convince yourself, there's no line that goes and separates those two classes. So what we would do is we would apply some type of transformation to a higher dimension. We would apply a function called a kernel function to the data set such that the data set would be transformed into a higher dimension, a dimension high enough where we could clearly separate the two groups, the two classes, in this case with a plane, much the same way you saw the picture a few slides ago where the plane was separating the two classes. Here we clearly could draw some planes between the green dots and the red dots. And of course, we could draw an infinite number of planes separating those two classes, but we would draw the one that would maximize the margin. So if we let R be the number of dimensions, then the kernel function would convert a given two-dimensional space to a three-dimensional space. And as I said, once the data is separated in 3 dimensions, we can apply SVM and separate the two groups using a two-dimensional plane. And this is analogous in the higher dimensions. And that last picture on the right-hand side would be some type of depiction of a higher dimension hyperplane. And there are more than one type of kernel function. There's Gaussian RBF kernel, sigmoid kernel, polynomial kernel, depending on the dimension and how you want to transform the data. There are more than one choice for kernel functions. So now let's go through a use case. Let's take a look at horses and mules and see if we can use SVM to classify some new data. So the problem statement is classifying horses and mules, and we're going to use height and weight as the two features. And obviously, horses and mules typically, in general, tend to weigh differently and tend to stand taller. So we'll take a data set, we'll import the data set, we'll make sure we have our libraries. The E1071 library has support vector machine algorithms built in. We'll compute the support vectors using the library. Once the data is used to train the algorithm, We'll plot the hyperplane, get a visual sense of how the data is separated, and if it's two-dimensional or three-dimensional, that's great. Remember, if it's higher dimensional, it's tough to plot those. And then we'll use the new model, the trained model, to classify new values. In general, we would have a training set, a test set, and then ingest the new data. But for our example, we're just going to use the whole data set to train the algorithm and then see how it performs. And once we see how it performs, we'll see, did we get a horse? Did we predict a horse when we had a horse? Did we predict a mule when we had a mule? So here's the R code. Of course, if you want to run this R code, you'll have to install R and then R Studio. Then you'll have to ingest the data, and then you'll have to create an indicator variable to help us with our plots. We'll install our libraries, install the package if you don't already have it installed. I do. And then call the library up into the R session that you're working. We'll create the data frame from the data that was ingested. We will then view the data frame, and of course we have to explore the data frame hoping that we don't have missing values or we don't have outliers. If we do have missing values or outliers, we'll have to either impute those values or delete those values. But in this case, let's hope we don't have any. And now for a quick demo on support vector machines. So we have a working directory where my data is stored, and I'm going to set the working directory to that data source and read the data file into R. And now I'm going to create a vector that really is just an indicator variable. It's the -1s and the 1s that indicate whether it's a mule or a horse. -1 for a mule, +1 for a horse. So I'll create that vector. And SVM, there's a great package, E1071, great library that has the support vector machine functions that we're going to use. And now I'm going to create the data frame. I'm going to take my data and I'm going to add to it the isHorse vector. And now let's just take a peek, and as you can see, there's the height, weight, and whether or not the animal was a mule or a horse. So remember, machine learning, we take a data source with known outcomes, and we apply our algorithm to that data source, in this case a data frame of heights, weights, and the indicator variable. And then we use the machine learning algorithm to learn from that data with those known results. So now let's plot the data, the height versus weight. And as you can see, the horses tend to be a lot taller and weigh a lot more than the mules. So now let's run our algorithm, our SVM model against the data. And the key here is that it's a linear model, and we've run it, and great, now we have a model. Let's look at the summary of the model, and as you can see, there's the formula that it ran and some of the information about the vectors and the classes. And there are two support vectors. So now let's find those two support vectors on our graph. And this might be a little hard to see. The orange outline around this point and this point indicate that those are the two vectors that will support this model, and thus we call them the support vectors. Now let's get the parameters of the hyperplane from the model, and let's plot a line that will be our hyperplane. There's our hyperplane line, and therefore to the left and below are mules, and to the right and above are horses above that line. Let's take a few new observations, and I've encoded these so that it would be illustrative. We'll take these new observations and we'll plot them, and I'm going to generate a new plot, red being the horses, black dots being the mules. I'll create an X and Y axis. I'm going to plot 3 dots, and you can see one of them, the green dot, the first one, kind of falls near the mules. The blue one kind of falls near the horses, and visually we might conclude, hey, one's a mule, one's a horse. But what about the orange dot? Well, for the orange dot, we really need our hyperplane. We really need something to clearly indicate which side it's on. And of course, by looking at this data visualization, you can tell that the orange dot is probably a mule. And let's verify those results by sticking those observations into our model and predict some outcomes. And down below, you can see that for the 3 data points, 1, 2, and 3, the first one, the green one, was -1. That's a mule. The second one was a +1. That's blue. That's the blue point, which was a horse. And the third one, which we weren't sure about, but clearly the SVM model correctly predicted that that third point would be a -1, would be a mule, and we can visually see that by the hyperplane on the graph. So that's a quick example of SVM. In general, support vector machines are binary classifiers. We don't use them for higher level classification. If you had 3 or more classes, you might want to use something like random forest. What applications? You can use it for face detection, text categorization, image classification, and bioinformatics. Really anywhere that you have the need to classify things into 2 groups.
So let's dive into what is clustering. What is clustering? So we'll have a group of people here hanging out at a table or local coffee shop. I'm guessing coffee shop since they all have the same mugs. And one of them is trying to figure out what they're going to do. I have 20 places to cover in 4 days. I guess he's going traveling. That sounds fun. One of those breeze through Costa Rica or visiting the U.S. or going to Europe to go visit all the highlights. So he's got 20 places he wants to go, and he wants to hit them in 4 days. Very ambitious. And how will I manage to cover all of them? That's the question that he's coming up. How am I going to get to all these different places in the short time I have? Maybe he's a sales team, so he has 20 places he's got to do demos for. You can make use of clustering by grouping the places into 4 clusters. Each of these clusters will have places which are close by. So we're going to cluster them together by what is closest to the other one. Then each day you can visit one cluster and cover all the places in the cluster. Great! That's a great idea. You know, if you're going to hit 4 different places, maybe you're going to cluster whatever streets are closest together so you don't have to travel, spend all your time traveling. The method of dividing the objects into clusters, which are similar between them and are dissimilar to the objects belonging to another cluster. So this is a formal definition of clustering. And we have here what we call hierarchical clustering and partial clustering. And we're going to go more into detail on hierarchical clustering, and you'll see the difference between the two, where partial clustering doesn't have the descending graph. It just has groups of things. And under hierarchical clustering, we're going to go over agglomerative and divisive. And you can think of agglomerative of bringing things together and divisive as dividing them apart. And then partial clustering, the 2 most common ones are k-means. That's probably the most common used for partial clustering. And there's also fuzzy c-means. And there's other ways of clustering and other algorithms out there. But these are the 2 big ones, k-means really being the most common one used. But we're not going to dig too deep into partial clustering because we're studying hierarchical clustering today. So what is clustering? Well, the applications of clustering are pretty numerous. We have things like customer segmentation, what people kind of belong together, how do we group them together? We have social network analysis. So social networks, we might look at sentiments. What group of people like something? What group of people don't like something? And then we can use that sentiments to suggest new sales for them. You know, this whole group is into Harley-Davidson motorcycles, so we cater to them to sell them Harley-Davidson motorcycle parts. And we find out that people in that group also like leather jackets, they also like motorcycle boots, and they like bandanas. My brother's into Harley-Davidson, so that's why I picked that kind of funny example. But you can kind of see we look for similarities between these people, and then we group them together accordingly. And that's a good sentimental clustering is very common in so many things today, where we want to know the sentiments on stocks. Who is interested in stocks, who's not. Sentimental analysis, we talked about customer segmentation and sales. Well, we want to know what kind of sentimental view people have on different restaurants if we're going to open up a new restaurant or a new putting stores in. And of course, city planning. A lot of this I just kind of aimed at the city planning side. City planning is big with clustering. We want to cluster things together so that they work. We don't want to put an industrial zone in the middle of somebody's neighborhood where they're not going to enjoy it, or have a commercial zone right in the middle of the industrial zone where no one's going to want to go next to a factory to go eat a high-end meal or dinner. So it's very big in city planning. But it's also very big in just pre-processing data into other models. So when we're exploring data, being able to cluster things together, reveal things in the data we never thought about. And then once we have it clustered, we can put that into another model to help us figure out what it is we want for our solution. So let's go a little deeper into hierarchical clustering. Let's consider we have a set of cars and we have a group similar. We want to group similar ones together. So below we have, you'll see 4 different cars down there. And we get 2 clusters of car types, sedan and SUV. So if you're just looking at it, you can probably think, oh yeah, we'll put the sedans together and the SUVs together. And then at last we can group everything into one cluster. So we just have just cars. So you can see as we have this, we make a nice little tree. This is very common. When you see anybody talks about hierarchical clustering, this is usually what you see and what comes out of it. We terminate when we are left with only one cluster. So we have, as you can see, we bring them all together. We have one cluster. We can't bring it together anymore because they're all together. Hierarchical clustering is separating data into different groups based on some measure of similarity. So we have to find a way to measure what makes them alike and what makes them different. Agglomerative clustering is known as a bottom-up approach. Remember I said think of that as bringing things together? You see, think the Latin term agglo is together because you have your agglomerate rocks where all the different pieces of rocks are in there. So we want to bring everything together. That's a bottom-up. And then divisive is we're going to go from the top down. So we take one huge cluster and we start dividing it up into 2 clusters, into 3, 4, 5, and so on. Digging even deeper into how hierarchical clustering works, let's consider we have a few points on a plane. So this plane is 2D, so we have an XY coordinates, kind of makes it easy. We're going to start with measure the distance. So we want to figure a way to compute the distance between each point. Each data point is a cluster of its own. Remember, if we're going from the bottom up, agglomerative, then we have each point being its own cluster. We try to find the least distance between 2 data points to form a cluster. And then once we find those with the least distance between them, we start grouping them together. So we start forming clusters of multiple points. This is represented in a tree-like structure called dendrogram. So this is another key word, dendrogram. And you can see it's just the branch that we've looked at before. And we do the second group the same, so it gets its own dendrogram, and the third gets its own dendrogram. And then we might group 2 groups together, so now those 2 groups are all under one dendrogram because they're closer together than the P1 and P2. And then we terminate when we are left with one cluster. So we finally bring it all together. You can see on the right how we've come up all the way up to the top. Whoops. And we have the gray hierarchical box coming in there and connecting them. So we have just one cluster, and that's a good place to terminate because there is no way we can bring them together any further. So how do we measure the distance between the data points? I mean, this is really where it starts getting interesting. Up until now, you can kind of eyeball it and say, hey, these look together. But when you have thousands of data points, how are we going to measure those distances? And there is a lot of ways to get the distance measure. So let's go ahead and take a look at that. Distance measures will determine the similarity between 2 elements, and it will influence the shape of the clusters. And we have Euclidean distance measure, we have squared Euclidean distance measure, which is almost the same thing but with less computations. And we have the Manhattan distance measure, which will give you slightly different results. And we have the cosine distance measure, which again is very similar to the Euclidean, playing with triangles. And sometimes it can compute faster depending on what kind of data you're looking at. So let's start with the Euclidean distance measure. The most common is we want to know the distance between the 2 points. So if we have point P and point Q, the Euclidean distance is the ordinary straight line. It is the distance between the 2 points in Euclidean space. And you should recognize D equals, in this case we're going to sum all the points. So if there was more than one point, we could figure out the distance to the not more than 1 points. This is the sum of more than 2 dimensions. So we can have the distance between each of the different dimensions squared, and that will give us, and then take the square root of that, and that gives us the actual distance between them. And they should look familiar from Euclidean geometry. Maybe you haven't played too much with multiple dimensions, so the summation symbol might not look familiar to you. But it's pretty straightforward as you add the distance between each of the 2 different points squared. So if your y difference was 2 minus 1 squared would be 2, and then you take the difference between the x, again squared, and if there was a z coordinates, it would be z1 minus z2 squared, and then take the square root of that and sum it all together, and then take the square root of it. So to make it compute faster, since the difference in distances, whether one is farther apart or closer together than the other, we can do what's called the squared Euclidean distance measurement. This is identical to the Euclidean measurement, but we don't take the square root at the end. There's no reason to. It certainly gives us the exact distance, but as far as doing calculations as to which one's bigger or smaller than the other one, it won't make a difference. So we'll just go with so we just get rid of that final square root. It computes faster, and it gives us pretty much the Euclidean squared distance on there. Now, the Manhattan distance measurement is a simple sum of horizontal and vertical components, or the distance between 2 points measured along axes at right angles. Now this is different because you're not looking at the direct line between them. And in certain cases, the individual distances measured will give you a better result. Now generally that's not true. Most times you go with the Euclidean squared method because that's very fast and easy to see. But the Manhattan distance is you measure just the y value, and you take the absolute value of it, and you measure just the x difference, and you take the absolute value of it, and just the z. And if you had more, different dimensions in there, A, B, C, D, E, F, however many dimensions, you would just take the absolute value of the difference of those dimensions. And then we have the cosine distance. Similarity measures the angle between the two vectors. And as you can see, as the two vectors get further and further apart, the cosine distance gets larger. So it's another way to measure the distance. Very similar to the Euclidean, so you're still looking at the same kind of measurement, so it should have a similar result as the first two. But keep in mind the Manhattan will have a very different result, and you can end up with a bias with the Manhattan if your data is very skewed, if one set of values is very large and another set of values is very small. But that's a little bit beyond the scope of this. It's just important to know that about the Manhattan distance. So let's dig into the agglomerative clustering. And agglomerative clustering begins with each element as a separate cluster, and then we merge them into a larger cluster. How do we represent a cluster of more than one point? So we're going to kind of mix the distance together with the actual agglomerative and see what that looks like. And we're actually going to have three key questions that are going to be answered here. So how do we represent a cluster of more than one point? So we want to look at the math, what it looks like mathematically and geometrically. How do we determine the nearness of clusters? When to stop combining clusters? Always important to have your computer script or your whatever you're working on have a termination point so it's not going on eternally. We've all done that if you do any kind of computer programming or writing a script. Let's assume that we have 6 data points in a Euclidean space. So again, we're dealing with x, y, and z. In this case, just x and y. So how do we represent a cluster of more than one point? Let's take a look at that. And first we're going to make use of centroids. Very common terminology in a lot of machine learning languages when we're grouping things together. So we're going to make use of centroids, which is the average of its points. And you can see here we're going to take the 1, 2, and the 2, 1, and we're going to group them together because they're close. And if we were looking at all the points, we'd look for those that are closest and start with those. And we're going to take those two, we're going to compute a point in the middle. And we'll give that point 1.5, 1.5. And that's going to be the centroid of those 2 points. And next we start measuring like another group of points. We got 4, 1, 5, 0. When they're pretty close together. So we'll go ahead and set up a centroid of those 2 points. In this case it would be the 4.5 and 0.5 would be the measurements on those 2 points. And once we have the centroid of the 2 groups, we find out that the next closest point to a centroid is over on the left. And so we're going to take this and say, oh, 0, 0 is closest to the 1.5, 1.5 centroid. So let's go ahead and group that together. And we compute a new centroid based on those 3 points. So now we have a centroid of 1.1 or 1, 1. And then we also do this again with the last point, the 5, 3, and it computes into the first group. And you can see our dendrogram on the right is growing. So we have each of these points become connected and we start grouping them together. And finally we get a centroid of that group too. And then finally the last thing we want to do is combine the 2 groups by their centroids. And you can see here we end up with one large group and it'll have its own centroid, although usually they don't compute the last centroid, we just put them all together. So when do we stop combining clusters? Well, hopefully it's pretty obvious to you. In this case when they all got to be 1, but there are actually many approaches to it. So first, pick a number of clusters k up front. And this is done in the fact that we don't want to look at 200 in clusters. We only want to look at the top 5 clusters or something like that. So we decide the number of clusters required in the beginning and we terminate when we reach the value k. So if you looked back on our clustering, let me just go back a couple screens. You'll see how we clustered these all together, and we might want just the 2 clusters, and so we look at just the top 2. Or maybe we only want 3 clusters, and so we would compute which one of these has a wider spread to it or something like that. There's other computations to know how to connect them. And we'll look at that in just a minute. But to note that when we pick the k value, we want to limit the information that's coming in. So that can be very important, especially if you're feeding it into another algorithm that requires 3 values, or you set it to 4 values, and you need to know that value coming in. So we might take the clustering and say, okay, only 3 clusters, that's all we want for k. So the possible challenges, this only makes sense when we know the data well. So when you're clustering with k clusters, you might already know that domain and know that that makes sense. But if you're exploring brand new data, you might have no idea how many clusters you really need to explore that data with. Let's consider the value of k to be 2. So in this case, in our previous example, we stop when we are left with 2 clusters. And you can see here that this is where they came together the best while still keeping separate the data. The second approach is stop when the next merge would create a cluster with low cohesion. So we keep clustering till the next merge of clusters creates a bad cluster low cohesion setup on there. That means the point is so close to being between 2 clusters, it doesn't make sense to bring them together. But how is cohesion defined? Oh, let's dig a little deeper into cohesion. The diameter of a cluster. So we're looking at the actual diameter of our cluster, and the diameter is the maximum distance between any pair of points in the cluster. We terminate when the diameter of a new cluster exceeds the threshold. So as that diameter gets bigger and bigger, we don't want the 2 circles or clusters to overlap. And we have radius of a cluster. Radius is the maximum distance of a point from centroid. We terminate when the radius of a new cluster exceeds the threshold. Again, we don't want things to overlap, so when it crosses that threshold and is overlapping with other data, we stop. So let's look at divisive clustering. Remember, we went from the bottom up, now we want to go from the top down. Divisive clustering approach begins with a whole set and proceeds to divide it into smaller clusters. So we start with a single cluster composed of all the data points. We split it into different clusters. This can be done using monothetic divisive methods. What is a monothetic divisive method? And we'll go backwards and let's consider the example we took in the agglomerative clustering to understand this. So we consider a space with 6 points in it, just like we did before, same points we had before. And we name each point in the cluster. So we have, in this case, we just gave it a letter value, A, B, C, D, E, F. Since we follow top-down approach in divisive clustering, obtain all possible splits into 2 columns. So we want to know where you could split it here. And we could do like a AB split and a CDEF split. We could do BCE, ADF. And you can see this starts generating a huge amount of data. ABCDEF. And so for each split, we can compute cluster sum of squares. And we can see here they actually have the formula out for us. BJ12 equals N1 of absolute value of x minus absolute value of x squared. So again, we're computing all the different distances in there squared. Back to your kind of Euclidean distances on that. And so we can actually compute B of j between clusters 1 and 2. And we have the mean of the cluster and the grand mean, depending on the number of members in the cluster. And we select the cluster with the largest sum of squares. Let's assume that the sum of squared distance is largest for the third split we had up above. And that's where we split the ABC out. And if we split the ABC out, we're left with the DEF on the other side. We again find the sum of squared distances and split it into clusters. So we go from ABC, we might find that the A splits into BC and D into EF. And again, you start to see that hierarchical dendrogram coming down as we start splitting everything apart. And finally, we might have A splits in B and C, and then each one gets their own DEF. And it continues to divide until we get little nodes at the end and every data has its own point. Or until we get to K, if we have set a K value. So we've kind of learned a little bit about the background and some of the math in hierarchical clustering. Let's go ahead and dive into a demo. And our demo today is going to be, for the problem statement, we're going to look at U.S. oil. So a U.S. oil organization needs to know its sales in various states in U.S. and cluster the states based on the sales. So what are the steps involved in setting this problem up? So the steps we're going to look at, and this is really useful for just about any processing of data, although I believe we're going to be doing this in R today. We're going to import the data set. So we'll explore our data a little bit there. Create a scatter plot. It's always good to have a visual if you can. So once you have a visual, you can know if you're really far off in the model you choose to cluster the data in or how many splits you need. And then we're going to normalize the data. So we're going to fix the data up so it processes correctly. We'll talk more detail about normalization when we get there. And then calculate the Euclidean distance. And finally, we'll create our dendrogram so it looks nice and pretty and we have something we can show to our shareholders so that they have something to go on and know why they gave us all that money in salary for the year. So we go ahead and open up R. And we're actually using R Studio, which is really it has some nice features in it. It automatically sets up the 3 windows where we have our script file on the upper left. And then we can execute that script and it'll come down and put it into the console, bottom left, and execute it. And then we have our plots off to the right. And I've got it zoomed in Hopefully not too large a font, but large enough that you can see it. And let's just go ahead and take a look at some of the script going in here. It's clustering analysis, and we're going to work, we'll call it my data, and we're going to assign it. In R, this is a symbol for assigning. And we're going to go read CSV. Read CSV file. And we'll put that in brackets. And before we go any further, let's just look at the data outside of R. It's always nice to do if you can. And the file is going to be called utilities.csv. This would also be the time to get the full path, so you have the right path to your file. And remember that you can always post in the comments down below. And when you post down there, just let us know you want to connect up with Simplilearn so that they can get you this file. So you can get the same file we're working on and you can repeat it and see how this works. This is utilities.csv. It's a comma-separated variable file, so it's pretty straightforward. And you can see here they have the city, fixed charge, and a number of different features to the data. And so we have our ROR, cost, load, demand, cells, nuclear fuel cost on here. And then going down the other side, we have U.S. cities, Arizona, Boston. They have central U.S., so I guess they're grouping a number of areas together. The Commonwealth area, you can see down here, Nevada, New England, northern U.S., Oklahoma, the Pacific region, and so on. So we have a nice little chart of different data they brought in. And so I'm going to take that complete path that ends in the utilities.csv, and we're going to import that file. Let me just enlarge this all the way. Oops, I had an extra set of brackets here somehow. Or maybe I missed a set of brackets. This can happen if you're not careful. You can get brackets on one side and not the other, or in this case, I got double brackets on each side. There we go. And then the magic hotkeys in this case are your Control-Enter, which will let me go ahead and run the script. And so I've now loaded the data, and as you can see, I went ahead and shrunk the plot since we're going to be looking at the window down below. And we can simply convert the data to a string. Now, all of us do this automatically the first time. We say, hey, just print it all out as a string. And then we get this huge mess of stuff that doesn't make a whole lot of sense. So, and you can see here they have, you can probably kind of pull it together as looking at it. But let's go ahead and just do the head. And we'll do the head of my data. There we go. And Control-Enter on that. And the head shows the first 5 rows. You'll see this in a lot of different scripts. In R, you type in head, and then in brackets you put your data. And it comes through and lists the first 5 rows, as you can see below. And it shows Arizona, Boston, Central, and it has the same columns we just looked at. So we have the fixed charge, the ROR, the cost, the load, the D demand. I'm not an expert in oil, so I'm not even sure what D demand is. Cells, I'm guessing nuclear, how much of it's supplied by nuclear, and the actual fuel cost. And then the different states that it's in or different areas. And one of the wonders of R is all these cool, easy to use tools that are so quick. So we'll do pairs, and pairs creates a nice graph. So let me go ahead and run this. Whoops. The reason it gave me an error is because I forgot to resize it. So let me bring my plot way out so we can see it, and let's run that again. And you'll see here that we have a nice graph of the different data and how it plots together, how the different points kind of come together. This is neat because if you look at this, I would look at this and say, hey, this is a great candidate for some kind of clustering. And the reason is when I look at any 2 pairs, let's go down to, say, cells and fuel cost towards the bottom right. And when you look at them where they cross over, you sort of see things how they group together, but it's a little confusing. You can't really pinpoint how they group together. You could probably look at these 2 and say, yeah, there's pretty good commonalities there. And if you look at any of the other pairs, you'll start seeing some patterns there also. And so we really want to know what are the patterns on all of them put together, not just any 2 of them, but the whole setup. Let me go ahead and shrink my this down for just a second, just a notch here. And let's create a scatter plot. Oops. And this is simply just use the term plot in brackets, and then which values do we want to plot. And if we remember when we looked at the data earlier, let me just go back this way. In this case, let's go ahead and compare just two values to see how they look. And we'll do fuel cost in cells, and it's in my data. So we got to let her know which two columns we're looking at next to each other. And we'll open up our plot thing and then go ahead and execute that. And we can see on those close up of what we were just looking at in the pairs. And if I was eyeballing this, I would say, oh look, there's a kind of a cluster up here of 5 items, and this one is hard to tell which cluster it'd be with, but maybe it's 6 to go in the top one, and you have a middle cluster and a bottom cluster, maybe 2 different clusters. So you can sort of group them together, fuel cost and the cells, and see how they connect with each other. And again, that's only 2 different values we're looking at. So in the long run, we want to look at all of them. And then the people in the back, they sent me the script so we can go ahead and add labels. So with my data text, fuel cost cells, the labels equals city, position 4. These are numbers you can kind of play with till they look nice. And oops, again, I forgot to resize my plot. It doesn't like having it too small. And we'll run that. I mistyped something in here. Oh, I did a lowercase d and they did a capital D. There we go. So now we can go in here and do this with my data. And you can see, a little hard to see on my screen with all the different things in there. It plots the actual cities. So we can now see where all the cities are in connection with, in this case, fuel cost and cells. So you have a nice label to go with the graph. And then we can also go ahead and plot, in this case, let's do, the ROR, whoops. And we'll do that also with the cells, and do my data. Remember to leave it lowercase this time. So when we plot those two, we'll come over here, and it's going to, I'm surprised it didn't give me an error. And then we'll also add in the with statement, so we put some nice labels in there. And it's going to be the same as before, except instead of doing the fuel cost cells, we want the R cells. And we'll execute that. Oops, and of course it gives me an error because I shrunk it down. So let's redo those two again. There we go. And we can see now we have the ROR with cells. And we'd probably get a slightly different clustering here if I was looking at these cities. They're probably different than what we had before. But you could probably look at this and say, these kind of go together and those kind of go together. But again, we're going to be looking at all of them instead of just 1 or 2. And so at this point, we want to dive into the next step. We're going to start looking at a little bit of coding or scripting here. This is very important because we're going to be looking at normalization. We put that in there, normalization. And if you've done any of the other machine learning skills and setup, this should start to look very normal in your pre-processing of data. Whether you're in R or Python or any of these scripts, we really want to make sure you normalize your data so it's not biased. Remember, we're dealing with distances, and if I have, let's say the ROR is, even look at this graph here on the right, you can see where my ROR varies between 8 and 14. That's a very small variable. And our cells varies between 4,000 and 16,000. So you can imagine the distance between 4,000 and 8,000, which is the distance of 4,000, versus 8 to 10 versus 2, the cells is going to dominate. So if we do any kind of special work on this, it's going to look at cells and it's going to cluster them just by the cells alone. And then ROR might have a little tiny effect of 2 versus 4,000. We want to level the playing field. Turns out there's actually a number of ways in script to normalize. So I'm just going to put in the code that they put together in the back for me. And let's talk about it a little bit. So we have Z, we're going to assign it to my data. And it's go ahead and we're going to do a little reshaping across all rows. Or across all columns. So each of the rows is going to have a little reshaping there. And then we're going to get M, which stands for means. And we're going to apply it to my data. So again, we want to go ahead and create the most common variable in there. And then S is going to be, SD stands for standard deviation. So instead of just doing, a lot of times what they do with normalization of data is we just reshape the data everything between 0 and 1. So that if the lower end is 8, that now becomes 0, and the upper end is 14, that now becomes 1. That doesn't help if it is not a linear set of data. So with this, we're going to look for the means and the standard deviation for reshaping the data. And that way the most common values now become the kind of like the center point, and then the standard deviation is how big the spread. So we want the standard deviation to be equal amongst all of them. And then finally we go ahead and take z, and with the z we're going to reassign it, and we're going to scale the original my data, which we reshaped, based on m and based on the standard deviation. And the 2 in here, that just means we're looking at everything in kind of a XY kind of plot. And we can quickly run these. Control Enter, Control Enter, Control Enter, Control Enter. So now we have Z, which is a scaled version of my data. And now we can go ahead and calculate the Euclidean distance. Oops, calcu. There we go. And in R, this is so easy. Once you've gotten to here, we've done all that pre-data processing. We'll call it distance. And we'll assign this to dist. So dist is the computation for getting the Euclidean distance. And we can just put z in there because we've already reformatted and scaled z to fit what we want. Let me go ahead and just hit enter on that. And I'm going to widen my left-hand side again. I'm always curious, what does this data look like? So let's just type in distance, which will print the variable down below. Oops. You have to hit Control Enter. And this prints out a huge amount of information. As you can see, it just kind of streams down there. And let's go ahead and enlarge this. And I don't know about you, but when I look at something like this, it doesn't mean a whole lot to me, other than I see 2, 3, 4, 5, 6, and then you kind of have the top part, 6, 17, 18. So imagine this is like a huge chart, is what we're looking at. And we can go ahead and use print, distance, digits equal 3. And let's run that. Oops, I keep forgetting that it has to go through the graph on the right. And we see a slightly different output in here. Let me just open this up so we can see what we're looking at. And by cutting down the distance, you can start to see the patterns here of it's looking at the different distances. So if I go to the top, we have the distance between 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, and then 2 and 3, and so on. Obviously, the distance between itself is 0, and it doesn't repeat the data, so we don't care to see 2 versus 1 again, because we already know the distance between 1 and 2. And so we have a nice view of all the distances in the chart, and that's what we're looking at right here. And it's a little easier to read. That's why we did the print statement up here to do digits equals 3. Make it a little bit smaller. We could even just do digits. Oh, let's just do 2. See what that looks like. We might lose some data on this one if something's way off. But we have a nice setup and we can see the different distances, and that's what we were computed here between each of the points. And then the whole reason we're doing this is to get ourselves a nice dendrogram going, a nice clustering dendrogram. We'll do a couple of these looking at different things. We'll take a variable hc.l and we're going to assign it h cluster and then distance. That easy. We've already computed the distances, so the h clustering does all the work for us. And let me hit enter on there. So now we have our HCL, which is assigned the h clustering computation based on distances and apart. And then I'm going to expand my graph because we would like to go ahead and see what this looks like. And we can simply plot that and hit the Control Enter so it runs. And look at that, we have a really nice clustering dendrogram. Except when I look at it, the first thing I notice is it really shows like numbers down below. Now, if you were a shareholder and some data scientist came up to you and said, look at this is what it means, you'd be looking at that going, what the heck does 3, 9, 14, 19, 1, 18 mean? So let's give it some words there. So let's do the same plot with our HCL. There we go. And let's add in labels. And this is just one of the commands in plots. So we have labels equals my data. And then under my data, we want to know the city. And we'll have it hang -1. That's just the instructions to make it pretty. So we'll run that. Oops, I accidentally ran just hang my 1. Let me try that again. There we go. Okay, so now you can see what it's done. And the hang my 1 turns it sideways. That way we can see Central, which is Central US, and Kentucky. And we start to actually get some information off our clustering setup. And the information you start looking at is that when we put all the information together, you probably want to look at Central America and Kentucky together. Oklahoma and Texas has a lot of commonality, as does Arizona and Southern U.S. And you could even group all 5 of those: Florida, Oklahoma, Texas, Arizona, and Southern U.S. These regions, for some reason, share a lot of similarities. And so we want to start asking what those similarities are. But this gives us a place to look. It says, hey, these things really go together. You should be grouping these together as far as your cells and what you're doing. And then one of the things you might want to do is we can do the dendrogram average. And this changes how we do the clustering. So it looks very similar like we had before. And there's our HCL. We're going to assign it. We're going to do an H cluster. We're still doing it on distance. Oops, distance. And this time we're going to set the method to average. So we can change the methodology in which it computes the values. And before, if you remember correctly, we did median. Median's a little bit different than means. We did the most common one, and then we want the average of the median. And let's go ahead and run that. And then we can plot. And here's our HCL. Oops, there we go. Here's our HCL, and I can run that plot. And you can see this changed a little bit. So our way it computes and groups things looks a little different than it did before. And let's go ahead and put the cities back in there and do the hang. Control copy. Let me just real quickly copy that down here, because we want the same labels. And again, you can see Nevada, Idaho, Puget. I remember we were looking at Southern U.S. and Arizona, Texas and Oklahoma, Florida. So the grouping really hasn't changed too much. So we still have a very similar grouping. It's almost kind of flipped it as far as the distance based on average has. But this is something you could actually take to the shareholders and say, hey, look, these things are connected. And at which point you want to explore a little deeper as to why they're connected, because they're going to ask you, okay, how are they connected and why do we care? But that's a little bit beyond the actual scope of what we're working on today. But we are going to cover membership, what's called clustering membership on there. And let's create a member. We'll just call it member 1. Oops, there, member.1. And we're going to assign to this, we're going to do cut tree. And cut tree, it limits it. So what that means is I take my hc.l in here. Oops, there we go, .l. And so I'm taking the cluster I just built, and we want to take that cluster, and we want to limit it to just a depth of 3. So we go ahead and do that, and run that one. Oops, let me go run. There we go. So now I've created my member 1. And then, whoops, let me just move this out of the way. We're going to do an aggregate, and we're going to use Z, remember Z from above, and we're going to turn member 1 into a list, and then we're going to aggregate that together based on the mean. Let me go ahead and enter, run that. Oops, I did member L, it's actually member 1. There we go. And if we take a look at this, we now have our group 1 fixed charge and then all your different columns listed there. And most of them should come up kind of looking between 0 and 1, but you'll see a lot of variation because we're varying it based on the means. So it's the means and standard deviation, not just forcing it in between 0 and 1, which is a much better way usually to normalize your data than just doing the 0-1 setup. And finally, we can actually look at the actual values, and the same chart we just did. Oops. I made a mistake on there with my data. There we go. Okay. And again, we now have our actual data. Instead of looking at just if you looked up here, it's all between 0 and 1. And when we look down here, we now have some actual connections and how far distance this different data is. Again, becomes more of a domain issue and understanding the oil company and what these different values means. And you can look at these as being the distances between different items. So a little bit different view, and you have to really dig deep into this data. What we really want you to take away from this is the dendrogram and the charts that we did earlier. And that is the cluster output and our nice dendrogram. So this would be stage 1 in data analysis of the cells. Again, you'd have to have a lot more domain experience to find out what all the individual numbers we looked at mean, and what the distance is, and what's difference between Central America and Kentucky, and why they're similar, and why it groups all of Central Kentucky, Florida, Oklahoma, Texas, Arizona, and Southern U.S. together into one larger group. So that'd be way beyond the scope of this. But you can see how we start to explore data, and we start to see things in here where things are grouped together in ways we might not have seen before. And this is a good start for understanding and giving advice for sales and marketing, maybe logistics, city development. There's all kinds of things that kind of come together in the hierarchical clustering as you begin to explore data. And we just want to point out that we get 3 clusters of regions with the highest cells, region with average cells, region with the lowest cells. Again, those are some of the things that they clustered it around, and you could actually see where things are going on or lacking. In this case, if you're the lowest cells, no one wants to be in the region of the lowest cells.
Welcome to this session where we will learn on time series analysis using R programming language. So this is basically a mini project where we will look at time series data and how we can analyze it, visualize it to basically find some important information or gather insights from the data. Now, when you talk about time series analysis, time series is basically any data set where your values are measured at different points in time. So when you talk about time series data, data is usually uniformly spaced at a specific frequency. For example, hourly weather measurements, you have daily counts of website visits, monthly sales total, and so on. So when you talk about time series, that can also be irregularly spaced and sporadic. For example, timestamp data in computer systems, event log, or history of 9/11 emergency calls. Now, when we work with time series data, for example, here I'm taking an energy data set, we can see how techniques such as time-based indexing, resampling, rolling windows can help us explore variations in electricity demand and renewable energy supply over time. Now here we will look at some aspects of this data set which I am considering. So this is open power systems data set, and here is the data set I have. We can look at the data set. Now this is in a simple format. It has time. It basically has values for consumption, and then you have data for wind and solar and wind plus solar. So in certain cases you have only the date and the consumption. But then if we scroll down, we will also find data for wind, solar, wind plus solar, and so on. So this is a time series data set which we would want to work on. Sometimes you may also have the data collected which just does not have the time, but it may also have timestamp. That is, it would have, say, hour, minutes, and seconds, and that can also be worked upon. So let's consider this data set and let's work on this project where we will analyze this time series data set. Now here We can work on this time series data. We can basically create some data structures out of it, such as data frames. We can do some time-based indexing. We can visualize the data. We can look at the seasonality in the data, look at some frequencies, and also do some trend detection. Now, when you talk about this data set, it has electricity production and consumption, which is reported as daily totals in gigawatt hours. And here are the columns of the data, which I was just showing you. So you have data, you have consumption, you have wind, you have solar, and wind plus solar. So this is the data we have, and we will basically explore, say, electricity consumption and production in Germany, which has varied over time. So some of the questions which we can answer here is, when is electricity consumption typically highest and lowest? How do wind and solar power production vary with seasons of the year? What are the long-term trends in electricity consumption, solar power, and wind power? How do wind and solar power production compare with electricity consumption, and how has this ratio changed over time? We can also do wrangling or cleaning of this data or pre-processing of data and create a data frame, and then we can visualize this. Now let's see how do we do that. So I will open up my RStudio and let's look at the data set. So here is the data set. Now I'm picking it up from my machine. You can also pick it up from GitHub. So all the data sets or similar data sets can be found in my GitHub repository. And here I can look in the data sets. You will find a lot of different data sets here. There are some time series data sets such as power. I can search for power, or you have basically coal, or you have this OPSD Germany daily data set, and there are many other data sets which you can work on. Now, to get the documentation on this project, you can also look in my GitHub repository and you can search for repositories, and then basically you can look in data science and R, and here there is a project folder where I've given the documentation, sample data set, and also your time series analysis related document. This is also the code which you can directly import in your RStudio, and you can practice or work on this project. So let's see how does that work. So first thing is, we will create a data frame from this data set. Now here, if you see, I am using header as true so that it understands the heading of each column. I'm also giving row.names and I'm specifying date. So there is this date column in the data set as I showed you earlier. Let's look at it again. So you have date, consumption, wind, solar, wind plus solar. So you can suggest that date should become the index column, which can be useful. So you can do this. Now let's just create this. Let's look at what does this data frame contain. And here, if you see, it shows me some data which has been now as a part of this data frame structure. It starts with consumption, wind, solar, wind plus solar. And if you see, this one is becoming my index column. So I can always do a head and look at part of the data frame using head or tail. So look at the first records. So let's see this. Now that shows me the head data. I can also do a tail and look at the ending values. So if you closely see here, we have wind, solar, wind, dot solar, and that basically has NA values. So there are missing values, but let's look at the tail, and that tells me that there is some data available for wind and solar and wind solar. Now we can always look in a tabular format using view, and we can look at the data. So this shows me that there are values in these columns. We see NA values, but if I really scroll down, I can see some values which would be available for wind and solar and wind solar. So I can just use view. Now I can look at the dimensions of this particular object, and that tells me there are 4,384 rows and 4 columns. You can always look at the structure, that is, check the data type of each column, which can be very useful. So if I see here, I don't see the date column, because date column was considered as an index which can be useful, but I also look at my other columns. So they are of the num types. So that's the data type for each attribute or each column here. Now we would be interested in looking at this date column. So let's look at the data type of this date column. Now if I try to do this, this will show me that this is null because date as a column does not exist because we created it as an index. So if I look at row names and then I search for my data, show me the index column or row dot names, it tells me these are the values. That's the date column which we are seeing here. Now we can access a specific row by just doing a my data and give the index value or row name value. So let's look at that, and that shows me based on this index you're looking at the value. You can obviously search for a different date, something like this. You can also pass in a vector and you can give range of values. So that is 0, 1, 2006 to 4 of January. And we can look at this one. So it shows me these are the values. So here actually I'm not giving a range, but I'm just selecting multiple values from row dot names. Now we already know that in R you have a summary function. So you can always do a summary, and that gives you for each column, it gives you minimum, first quartile, median, mean, third quartile, and maximum values. So we are looking at consumption, we are looking at wind, solar, and wind dot solar. Now this is good, but then if I would want to really visualize the data, access the data, do some analysis, then it would be good to take all the columns, and then we can later decide to change the data type of, say, date column if we want to use it. So earlier I was using date as row dot names or the name of the rows or index, what you call in any other programming language. So here I will just use my data set and I'll say header as true. I'm calling it my data 2. Let's look at the data, and this one shows me 5 columns, wherein my first column is the date, consumption, wind, solar, and so on. Now looking at the structure, so let's look at the data type. So it tells me that if now I'm interested in looking at the date column from my data to data frame, it tells me it is a factor with 4384 levels, and these are the values. So it is not in a date time format, it's a factor. Now what we can do is we can convert this into a date format. How do we do that? So let's have a variable x, and I'm going to use as.date function, and I'm going to pass in my date column. So that's assigned to x. Now let's look at the head of x, and it shows me the values. We will also see what kind of class it is, and we will look at the structure of x. So class already says it is date type, and look at the structure, so it shows me the format. Now we have converted this column or column related value into x. Now how do I basically extract values out of it or make it a part of data frame? So first I will use, so all once it has been converted in date format, I will go for as.numeric, and here I will create a variable called year, and I will just do a format on x, which is basically of date type, and then I'm saying %y, so that will get me the year component out of this. Let's look at the values. That shows me year component. Now similarly we can get the month out of this, and then basically look at the month values. We can get the day out of it, and we can get the day component. Now if I look at my data 2, which we had created earlier, this basically had date, consumption, wind, solar, wind, solar. So what I can do is I can add these extracted columns such as year, month, day to my data frame using a cbind, that is column bind, and I will assign it to my data 2 again. So let's do this, and now if you look at head, it shows me date, so that should be date format, consumption. Now this one might not be date format, but we'll see. you have consumption, wind, solar, and we have extracted the year, month, and day, which can help us for group by. We can do some aggregations, we can do a plotting, and we can do various things by these additional columns. Now let's look at first 3 rows here. So I'll say 1:3 for my data 2, and that shows me some data here. You can always do a head and look at the sample of data. So that basically shows me month, day, your columns, and then you have your date. Now, what we can do is we would want to visualize this data. We would want to basically understand the consumption. Now, as I said, if we want to visualize the data, say for example, I want this, which is consumption of data over years. And this one is in terms of gigawatts per hour, as we were mentioning here, gigawatt hours. So if I would want to create this visual to basically understand the pattern of the data, how do we do it? So we can create a line plot of full time series of Germany's electricity consumption using the plot method. Now, how do we do that? So here, one of the option is I can straight away use the plot method. I can then say what would be in my x-axis, what would be on my y-axis, what would be the type of graph I would want to plot, what is my name on x-axis, y-axis, and this is the simplest way. So I'm saying my data 2, I'm extracting the year column, and here I'm taking the consumption. So let's create a plot. And here, if you see, we are looking at a plot. We do see some tick times, and we see that the data has been divided with every 2 years. So from 2006 onwards to 2016. But then really this data does not give me a very useful way of looking at the data or understanding it. Might be what I can do is I can use the same way, but I can give, apart from x-axis and y-axis, I can say the limits, that is x limit is 2006 to 2018 and y limit is from 800 to 1700. So we can do this, and let's look at this again. This is a plot, but it really does not help me in visualizing and understanding the data. So what are the better options? I can go for multiple plots in a window. As of now, we are just sticking to one plot in window. So if you would want to have multiple plots, you can always change the value here and make it 2 or 3. That will say how many rows and how many columns. So as of now, we will just keep it as it is, par mf row. Now, if I would want to plot, I can straight away give the column name. So I'm interested in getting the consumption. Now I can just do a plot. I'll say my data 2, and I will choose the second column, which is consumption, which we saw here from our data. So consumption was the second column. So I can just do a plot in a straightaway way without mentioning your x-axis, y-axis, limits, and so on. And if you look at this one is giving me a pattern. Now here I am looking at x-axis, y-axis, which is not really named. We do not have a name to this graph, and we are looking at the data. It does show me some kind of pattern, but might be we can make it more meaningful. So I can do it this way, where I say my data second column, let's give axis as year, x-axis, y-axis is consumption. Now that has changed the x-axis and y-axis. Now I can also give some more details. I can say type should be line. I have the line width. I'm saying color is blue, and let's do this. So this looks more meaningful, might be shows a wavering pattern of consumption over years. I can also give a limit of x, that is 0 to 2018, and that basically shows me the range. Now we can change that, and we can be more specific and saying x limit should be 2006 to 2018. And let's look at this. Now this one, once you have given a proper limit, it shows the line graph, and it shows what was the consumption in 2006 and over a period till 2018. I can then use any of these options are fine, but it depends on what and whom you are presenting the data or what kind of analysis you're doing. So I can do a plot. I can choose column second, X lab, which is x-axis, y-axis, type is line, width, giving a X limit, Y limit, and then I'm giving a title to this, which is consumption graph. And then basically you are looking at the line graph. Now, those are the options which you can do. Either you could be very specific, or you could just give your column which you want to plot, or obviously make it more meaningful by giving all the details. Now, what we can do is, if we would want to look at this data and understand it better, rather than just looking at a simple line, I can take the log values. So here I'm saying log of my data 2 second column. So I'm taking log values of consumption and I'm taking the difference of logs. So I can say difference, and then you can basically increase or decrease this by multiplying it by some number. So rest remains the same. I'm changing the color, and let's look at this plot. And you see, this basically is giving me a better pattern which makes meaning. Here we see the log values. So this is, you are using a simple plot function. In R, you can also use ggplot. Now for that, we can install the ggplot package. It's already there in my machine, so I'll say no. I will access this by using the library ggplot2, and now I can use ggplot to plot. So the way you specify here, you can say my data 2, that's the data frame. I'm saying type as O, and when I'm saying line, I am basically going to use x-axis, which is year, y is consumption. And let's look at this plot. So again, we are back to the one which we were doing earlier. Really does not make any sense. It gives us some data, but then really does not give me enough information. I can, in my aesthetics, I can say X as year, Y as consumption. I can do a grouping, and then I can give line and plot. So again, we have some information, but really does not help me, right? Now let's look at other example. So I'm just doing the same thing here, and I'm looking at line type being dashed. I'm using the ggplots other methods such as geom_line and geom_point to give me more information. And if I look at the plot, it does give me data. It tells me what are the different values. It gives me some kind of pattern, but I would still prefer the way we were doing with plot. Now we can change the color and obviously add details to it. So what we see is, when you use the plot method, which I did earlier, it was choosing pretty good tick locations, that is every 2 years, and labels the years for the x-axis, which was helpful, right? But with these data points which we were seeing here, or say for example this one, or say this one, or say this one, we are looking at some data, but then that really is quite crowded and it is hard to read. You can look at the values, but then it really does not give you enough information. So we can go for plot method, but then we will see how we can consider different data. Now, if I would want to plot the solar and wind time series, so let's see how do we do that. So wind column is what I'm interested in. So first thing is, it was always good to find out the minimum and the maximum values in every column. So I'm saying minimum, I'm saying let's put in here my data 2, and then let's look at the values. So we are looking at the columns. We know consumption is the second column, wind is the third column, and you have solar as the fourth, and this one is the fifth. So let's say, let's find out the minimum of each of these columns which we would want to plot. So let's say minimum of data third column. And here I'm also saying remove the NA values, because we do not want to consider the NA values. So let's look at the minimum. That shows me 5.7757. What is the maximum value? It is 826. So that also helps me in giving a limit. If I want to plot wind on y-axis, I can give a y limit from 5 to 850. Consumption wise, let's find out the minimum from second column and maximum. And similarly for solar, find the minimum and maximum, and wind plus solar, minimum and maximum. So this will be helpful when you would want to plot multiple graphs, or give some limits. So that's fine. Now for multiple plots, as I said, instead of having one plot, let's plot consumption and wind and solar and try to see a pattern. So I can say par function, and I will say 3 rows and 1 column. So now when I start plotting, you will see you will have multiple plots in one single window. So let's see how we do it. So here, let's look at plot 1. So this one is consumption, as we did earlier. And let's look at the data. So that gives me some data. You can always do a zoom and you can look at the data. You can basically expand this graph, or you can reduce this graph to see what kind of pattern we have in consumption. Similarly, we can basically choose date being x-axis, my consumption being y-axis, right? So this is being more specific, because here we have a range, but it really does not give me enough information. So I will basically give x-axis, y-axis. I will give the name, that is daily totals, and then I will basically give consumption, color, and y limit based on my minimum and maximum limits. So let's do this, and now we can look at the data here. So let's see, this data makes a little more meaning because we are looking at the dates. And let me do a zoom. So it shows me all the dates, it shows me the data points, it shows me how the data pattern is changing for consumption. Now this is for consumption. So what we can do is we can also extract specific data. So if you see here, I have done some testing where I'm saying, okay, I would want to get a date specifically. I would want to extract some value. So we are looking at the date column, but if you remember, we did not change the data type. We just changed the data type of date column. We extracted year, month out of it. It would be good if we can convert a column into date time format and put that in our data frame. Now, let's look at the plot 2. This is mainly for your column, which should be consumption and wind and solar. So here I see it is solar data, and I can plot this one to see how it looks like. And that tells me from 2006 onwards, we have some pattern. I can be more specific where I say I would be giving date and then the column for solar, x-axis, y-axis, what is the type, what is the y limit, and what is the color. It is always good to specify your x and y axis, give a name, rather than let it automatically pick up. Now this makes more meaning because it shows me some dates. Similarly, we can do for wind. So either you do it just by giving the column, or you give your x and y axis. So let's look at this one, and this shows me the data. So we can choose plot 3, this one, we can choose plot 2, we can choose plot 1, and we can put all that data in one graph. So that's when you are putting in multi plots in one particular graph. You can always do a zoom, you can always look at the data, right? And this is usually useful to look at the pattern, what kind of pattern we see, what data we have, and so on. Now, moving forward, so we have seen how you are creating these plots all in one window. Let me reset this back to one plot per window, and let's basically plot time series in a single year. So what we have seen is that when you look at the plot method, it was quite crowded. Then we looked at solar and wind, and if you compare that, you will see your consumption pattern, your solar pattern, your wind pattern, and basically we can see from this particular data some kind of pattern. So electricity consumption is highest in the winter, where we will see what is the consumption. Is it highest in winter or is it in summer? We can see that by breaking a year further into months. We can see that, but we see a pattern which goes for every year or every 2 years being highest at a particular point of time, and then it drops down. So electricity consumption is highest in winter, and that might be due to electrical heating and increased lighting usage, and lowest in summer. Now when you look at electricity consumption appears to split into two clusters. We can always look at the consumption, one with oscillation centered roundly around 1400 gigawatts. So you can always look at 1400 gigawatts and you see all the values here which are in that particular consumption. Another with fewer and more scattered data points, centrally roughed around 1150. So if you really expand this, you can see you will have a lot of data points at this point. Now, we might guess that these clusters correspond with weekdays and weekends, which we can see if you break that data into yearly, monthly, weekly, and so on. Now, if you look at solar production, that is highest in summer when sunlight is most abundant and lowest in winter. So obviously when you're making or gathering some insights, when you're looking at the data, you are also using your domain knowledge, your business knowledge, your knowledge of business to understand how this goes. If you look at wind power production, that's again highest in winters and drops down in summer. So due to stronger winds and more frequent storms, and lowest in summer. So there is some kind of increasing trend in wind power production over years, which we can see here over the years. And all the time series data what we are looking at is referring or showing us some kind of seasonality. That is, we are looking at seasonality in which a pattern is repeating again and again at regular times, at regular intervals. So if you look at consumption, solar, and wind time series, that oscillates between high and low values on a yearly time scale, which we can break down and see. I'll show you that. It corresponds with the seasonal changes in weather over the year. So seasonality does not have to correspond with meteorological reasons. For example, if you look at retail sales data, that will show you yearly seasonality with increased sales in particular months. So seasonality, when we say, can occur on other time scales. So the plots what we are seeing here, they are fine, but if you look at those plots, they might show some kind of weekly seasonality also. So in your consumption corresponding to weekdays and weekends. So let's plot for one single year. Now, how do I do that? So first is I will look at my data 2. That shows me the structure. It shows me date, which is factor, other columns, which are all numerics. Now, like we did earlier, I'll repeat this step where I'm going to convert the date column into date type. Look at head of it, look at class of it, look at the structure of it, right? And then what I want to do is I want to add this to my data frame. So I will create a variable called mod data, and this one will have as data, and I'm formatting the value of X, which is date time, into month, day, and year. So let's do that. And now you look at the mod data, which I created, like modified data. So this is the format I have. It is in date type, if you carefully see here. And then I can look at the head of it. So it says me mod data. Now what we did here is when I said my data 3. So my data 3, we did a cbind and I did a mod data, which is going to add this column to my other columns of my data 2. So my new data frame is my data 3. Let's look at the structure of it. And you see there is this date column. I can delete it, I can remove it, I can let it be, right? So that depends on our choice. Might be we want to, once our analysis is done, we want to remove the mod data, right? So we can keep both of them. Now let's basically extract data for a particular year. Now how do you do that? So this is some wrangling. So I will say my data 4, let's call it my data 4, and I will use subset function. So subset will work on my data 3, that's the data. And what I'll do is I will do a subset. How is the subset found? So I'll say take the mod data column, the value should be greater than or equal to 2017 and should be less than 2017 December 31st. So I'm getting data for 1 year and I'm storing it as my data 4. Let's get the head of it, and you see we are specifically looking at 2017 related data. Now let's do a plotting of this where I will only create a plot for 1 year. So I'm saying my data 4, that's my new data what we got. So here I am going to take the first column, which is mod data. I'm going to take the third column, which is consumption. So I'm looking at the date format for 1 year, consumption values for it, and then rest of the things as we have done earlier. Let's look at the plot, and this makes more meaning, right? So when you look at this plot, it tells me Jan to Jan. It shows me some kind of pattern where I have divided the year into months, right? And it is broken down into say 2 months, so Jan and March and May and July and so on, but we still see a pattern, and that gives me good understanding of pattern where I've broken it down into months. So this is where you have taken time series in a single year to investigate further, and this is what we see, right? Now we can clearly see there are some weekly oscillations. What one more interesting feature is that at this level of granularity, that is when you're looking at yearly data, there is a drastic decrease in electricity consumption in early January and late December during the holidays, or probably we can assume that this is holidays. Now I can zoom in further and look at just Jan and Feb data. Let's see how we do that, and let's see how we work by zooming in the data further. So to zoom in the data further, let's see how we do it. Now here we have this my data 4, which is basically having a subset, right? So let's work on this one. So I will say my data 4, which earlier I was taking data 3, I was doing a subset and I was giving the date, but this time I will make it more narrower. So I'll say my data 4, I will say subset from my data 3, and I will choose mod data column, which we have modified with the date format. I will choose the starting date as 1701, that is Jan, and then let's go till Feb and let's create this. Now let's look at the head of this. So it shows me we have the data which is Jan, and then you can basically look at more on this. Now again, as I said earlier, let's find out the minimum of this from the first column. So that is basically your mod data. So let's look into this one, and that basically will give me minimum and maximum. Let's look at the values. So this one tells me Jan 17, January 1, and maximum is your Feb 28th, second month 2017. So we are actually looking at 2 months data here. Let's look at the Y minimum. So this is, I will look at column 3. Now what is column 3? Consumption. So let's look at the minimum value for consumption, maximum value of consumption. Let's look at the values which can be given as our limits. Now this is the minimum and maximum. Now let's do a plotting for this data which has been narrowed down for consumption based on my data. So I'm saying my first column, which is mod data, and then third column, which is consumption. I'm giving some naming convention for, namings for your x-axis, y-axis, what is my consumption, or what is my title here, what is the color, and then you see I'm using X limit to give the minimum and maximum limit and Y limit. So let's look at this data. And if you look at this data, it is specifically for 2 months. And again, I can look at the pattern here. What I can also do is I can add some grid here. So I can basically look at this data and make more meaning out of it. So it is bi-weekly data, you can see. Now I can add a line here using ab line, and then I can basically choose what lines I would want to add horizontally. So that basically allows me to dissect the data and look at data in a more meaningful way. I can also add vertical lines. So vertical lines is, I'm saying sequence will be minimum, maximum, and I'm saying an interval of 7. So let's do this, and this basically has added some lines every week, And you can see at the end of week it is dropping, and then it is starting again. It peaks somewhere in the mid of the week, and again it drops down. So this is, you're looking at your consumption data, right? Now what we can also do is we can create some box plots. So when we looked at zooming in data for Jan and Feb, you can add some data points like this. So consumption is highest on the weekdays, as I showed you here, and lowest on the weekends. So this is what we are seeing when we are breaking the data or zooming it further for a couple of months. So we have vertical grid lines, and we have nicely formatted tick labels, that is Jan 1st, Jan 15th, Feb 1st, and so on. So we can easily tell which days are weekdays and weekends with use of these grid lines and basically breaking it down. So there are many other ways to actually visualize your time series data depending on what patterns you're trying to explore. You can use scatter plots, you can use heat maps, you can use histograms, and so on. Now, moving further, we would want to explore the seasonality, right? So when you further explore the seasonality of our data, we can use box plots basically to group the data by different time periods and display the distribution for each group. Now, how do we do that? Let's come here and let's see how box plot works. So I can just do a simple box plot, and I can choose my consumption column, and that gives me just the consumption data, but this really does not give me any meaning. I can look at solar data, I can look at the wind data, and we can also see some outliers here. So we can create box plots, but if we would want to do a box plot, what is box plot? It is basically a visual display of your 5-number summary. That is, you want to look at your mean, median, you want to look at your 25th percentile, 50 percentile, or 75th percentile. So we can use a quantile function, use the consumption column, and then you basically give a vector which shows you 5-number summary. So that's your quantile. And then let's do a box plot. So if you are looking at quantile, it tells me what is the minimum, what is 25th percentile, 50, 75th, and 100. That's from my consumption column. So let's create a box plot for consumption. Let's give it a name as consumption. Let's give y-axis as consumption and a limit for y-axis. Now that's my consumption graph. So I can look at yearly data. Now that will make more meaning rather than just looking at the complete consumption data. So how do we do it yearly? So we will say consumption, and then I will say the year column. So it is consumption, but grouped based on year. So here I can give x-axis, y-axis, and I can give y limit. So let's create this, and this makes more meaning. We can give some coloring scheme here, but now I'm looking at 2006, 2007, 8, 9, and so on. And we can look at the data, what is the range, right? It gives me 5 percentile, or sorry, 5-number summary of the data per year, and it basically allows me to look at the seasonality of this. Similarly, we can create box plot by just giving consumption, yearly grouped, and here I'm giving the title as consumption, y-axis, x-axis, and y limit, wherein I can also use las. So this is one more feature which you can do, and that basically will give me the tick points. If you compare this one to the previous graph, so when I created this previous graph, I had 2006, 2008, and I had from 600 to 1800. And if I go for the next one, I am basically seeing more useful information. Now let's look at monthly data. So I would want to group it based on months, and let's create that. So this gives me the monthly data where I'm looking at months, and I could select a particular year, or I can just do a grouping based on months. So I can have multiple plots to see a difference here. So let's do this. Now let's create a box plot for consumption, which is monthly data, and let's give it a color. Let's look at the wind data, which is again grouped monthly, and let's look at the solar data, which is grouped monthly. Now if I zoom in, it basically gives me the seasonality of the data. For your wind, for your consumption, for your solar. So what we are doing is we are creating these box plots which are giving us values. Now what I can also do is I could look at the day wise also. But before we look into this, how do I infer some information from these box plots which are being created? So this is what we have done, where we are looking at the data for month, and these box plots give me year seasonality, which we were seeing in earlier plots, but give some additional insights. So if I look at the data here, it tells me the electricity consumption is generally higher in winter. Now this is based on months, so we can see consumption is higher in winters and lower in summer. So we can obviously look at our plot, we can see where it is lower, where it is higher, and then we can look at the median and lower two quartiles are lower in December and January compared to November and February. So that is, you look at the quartiles and you will see that the median and lower two quartiles are lower in December and January. Here Jan and December, so you can look at from my plot. Now this is giving you some idea on seasonality. Now that might be due to business being closed over holidays. Now this one we were also seeing when we looked at time series for 2017 only, and box plot basically confirms that there is this consistent pattern throughout the years. Now when you look at your solar and wind power production, both will give you a year seasonality, what we are seeing here. And if basically I look at the data, so it depends on what parameters you are choosing, but if you look at solar, it will reflect the effect of occasional extreme wind speeds associated with storms and other transient. And since we are grouping it based on months, we can see this pattern is quite evident every year. Now, what we can do is we can group the data day wise. So here, let me again reset this to one plot per graph. Now I'll say box plot, I'll say consumption, which is grouped based on day. Now we know that there is a day column, and let's give a while limit and let's look at the data. So this is where I'm grouping the data day wise. So you look at 31 days and you look at the box plot. So this is where you are plotting it on a daily basis. So you can look at the data, you can break it down to a particular week. So here I have given day and I have chosen all the 31 days, but I can break it down to a week and I can look at the data. So if we look at the data per week or per day, we can basically infer that electricity consumption, where I'm doing a consumption group by day, is higher on weekdays than on weekends. So time series with strong seasonality can often be represented with models that can decompose signal into seasonality and long trend. Now this is an easy way. Now how do we look at the frequency of the data? That could be interesting to see. So let me look at, say, the yearly data which we were seeing here. Now let's go further, and here we have looked at data. So what we will do is we look at the frequency. Now when you look at the frequency, when you talk about frequency in your data, so we have the modified date column which gives me a frequency, and if we really look into the data, that will tell me that the data is on a daily basis. So for that, let's look at my data 3 again, which gives me data, and you can just see all the data or dates are in sequence. So your 22, 23, 24, 25, 26 and so on. I can access a dplyr package that is basically allowing me to work in a better way. Now I can look at the summary of this, and for all my columns I'm seeing what is the minimum 5-number summary, date and consumption. So date does not show me anything because this is not in a date format, it is just a factor, but other things have the 5-number summary. So we are looking at wind plus solar, We are looking at year and month and day and all these columns. Now what we will do is we will want to find out the sum of each column. How many entries does it have? And we will say the value should, NA value should not be considered. So let's look at this one. So it tells me for my particular columns. So let me run this again. And that shows me for each column how many values you have, and these counts do not include the NA values. Now similarly, I can find out specifically for consumption. I can find out, is there any NA value? So I'm saying is.NA, and let's find out if there is any NA value or missing value in consumption. It says 0. Okay, that's good. If you look in wind, it tells me there are 1463 entries which are NA. Similarly solar, similarly wind dot solar or wind plus solar. So it gives me a count of NA values, that is missing values, and also values which are not missing. So to understand frequency, what we can do is we can find out the minimum on the date, that is the first column, and I'm saying RM na.rm is true, that is get rid of NA values and find out the minimum. And let's look at the minimum value. This is the minimum from my modified date. Now if I would want to get the frequency, I can basically use sequence function. So I can say from X minimum, that is the minimum value, I want to look at the frequency, that is day wise, and let's just look at 5 entries and see if there is a day by day frequency. So let's look at the value of this, and obviously it tells me there is day wise frequency. So that allows me to look at the frequency, look at the type of it. It is an integer, class is a date. So similarly, we can say from X minimum, we can basically look at the frequency month wise, and I can again look at 5 records. So that shows me monthly data, right? So I can extract the data for frequency, similarly yearly data, and that's also very useful. Now we can select data which has NA values for wind. So how do I do it? I would want to find out the wind column, and I want to find out where the values are NA. So I will create a variable, and here I will say my data 3, and then I give a conditional where I say is NA in the column. So let's do this. Now once I've done this, I have said that my selected wind data from my data 3 where we said NA values, and I will give the names to this. So names should be in my data 3. I'm interested in mod data, consumption, wind, and solar. So these are the 4 columns I'm interested in. Let's look at first 10 records here, or first 10 rows. So that tells me these are the values where wind has NA or missing values. I can always do a view, and that gives me the complete data. So it basically shows me 1463 entries, and here it shows me all NA values. So you can look at all the way to the end, and it shows me wind has NA. Solar does have some value here in the last row, but then also if you see the numbers have a difference. So you have 1461 and then you have 2174. So there is a difference. So there is some data in between where wind has some values. So we have found out NA values. Now what we will do is we will select data which does not have NA values. So I will call it cell selected wind 2. I'll again use my data 3. I will say which, but now I'm saying not NA from this column, and I will select the data for the columns. So I'm interested in looking at 10 records, and this shows me not NA values, so no more missing values. So if I really look at this data as I saw earlier, which has NA, and if I look at these values which are not NA for the wind column, so looking at these two results, we will know that in year 2011 wind column has some missing values. So let's focus on year 2011. So how do I do that? Let's call it a different variable. I'll say my data 3. I will say here, when I say which, where we were saying NA, here I will say the year should have a value of 2011, and I want all these columns. Let's look at the data here, and this is showing me 2011, but we are not seeing all the values. So there are some values, but then there are some missing values also for 2011 based on whatever analysis we have done. So let's look at the class of this. It is basically a data frame, do a view, and this one will help me in finding out where are the NA values. So if you just scroll down, looking at all the data, let's search if wind column has a NA or a missing value, and I will see if there is any missing value, in which column or which row it is for the wind column. So we have all the values which are existing. I could select and search for one specific value, and I'll show you how we can do that. So here, let's scroll all the way down. So it's like you're exploring your data and seeing, is wind column having NA or missing value for a particular row. And let's scroll here, and here you see there is a missing value for one particular row. So 13th December 2011 has wind value, 15th December has wind value, but your 14th December does not have, right? Similarly, we can search. So there was only one entry which was missing. Now that could be for some reason, might be it was not calculated, might be it was not tabulated. So we have a missing value, and that can affect my plotting, that can affect my analysis. So let's look at the number of rows in this, which will tell me how many rows we have for 2011. So it tells me 365. So that is basically the number of days in a year. Now we will find out if there were NA values. So we earlier checked total number of NA values per column. That is in your row number 265 to 269. We can see here 265 to 269. So this is where we were seeing, are there any NA values, right? So let's go back here, and we want to find out the number of NA values for a particular year. How do I do it? So I can just do a sum. I will say is NA. Now I'm interested in my data 3 wind column, and I'm saying my year has to be 2011, but I'm finding out the NA values. So let's do this, and it tells me 1, and that's right. That's what we saw when we did a view. Let's see how many non-NA values you have, and that is 364. So that basically satisfies my logic. So it's 364 plus 1 missing, so there are 365. Let's look at the structure of this. It tells me you have modified date and date format, you have consumption, wind, and solar. Now let's create a variable, selected wind 4. I will say wind 3, that is which was having all my NA and non-NA values for 2011. I will say let's find out the NA value, because I'm interested in finding out that particular row. So I'm saying find out where the value is NA, and I want all the columns. Let's look at this one, and this is my specific row which has a NA value. Now we know that data follows a day-wise frequency, which we have clearly seen. Now let's select data which has NA and non-NA values. So let's call it test 1. I will use wind 3, which has NA and non-NA values. But now I will say I want the modified date, which should be greater than 12/12/2001. Now remember, we had, when we were doing a view, we saw that one particular day, or what we see here, 14th of December, there is no date. So I will select a subset of data which includes this NA and non-NA. That is, might be I can take 13th of December and 15th of December. So let's start from 12/12. So the date should be greater than 12/12. That means 13th, and it should be less than 16. So that is 15th, and the columns, right? So now we have some data. Let's look at this. So I have a I've selected a subset of data. I could have done this using subset also. So I have NA and non-NA values. Now, why are we doing this? So sometimes you might have some data for a particular column and you may want to find out if there are any missing values. Might be you want to fill them up or replace them with something. So that is usually useful when you are doing a trend detection. So say for example, you have data for every month and might be in one of the months you have missed, or might be you have data for every year collected monthly, and then in one of the years for a couple of months you don't have the data. Like I can say 2016, I have data for all 12 months, 2017, all 12 months, 2018, might be I don't have data for March and June, 2019, I don't have data for same months. So I can forward fill or backward fill them using the previous year's same month data. So we can do that. So here I have test data where I've extracted a subset of data. I can look at the class of this. It is a data frame. Structure of this, it has the columns. Now let's use the library and function and use the tidyr package. And what we will do is we will fill it up. So I will use test1. I will fill the wind column which has a missing value. Now once you do this, if you notice, it has done a forward fill. So it has taken the previous value and it has just filled up that. So you can fill up the data using different directions such as up and down, left and right, and so on. So we can take care of missing values in our frequency data, which allows us to basically analyze the data in a better way. Now, here we will want to also look at some more data. So this is to deal with frequencies of fill column, wherein you can take care of missing values forward filled. So filling values can be done in different directions, as I said, and you may want to first convert your time series to specified frequency if your data does not have a frequency, but we had. Now, if you do not have a frequency, might be you can convert it into a frequency such as weekly, daily, monthly, as I showed you, and then basically you can do a forward fill for the values. So for example, if I have my data, I can break it down into weekly and then look at the values, and if there are any values missing for weekly data, I can use a forward fill. So that can take care of my frequency data. Then let's look at the trends of the data, which is the last part of this project. So basically, let's look at the trend. So when you say trend, what does that mean? So in time series data, you always have some kind of trend. So that will exhibit some slow, gradual variability in addition to higher frequency variability, such as seasonality and noise. Now, to visualize these trends, what we do is we use what we call as rolling means. So we know how our data is spread over year or month or day. But how about looking at a rolling average and see what is the difference? So a rolling mean will tend to smooth a time series by averaging out the variations and frequencies. So this can be higher than the window size. So there is something called as windowing, where you can choose a set of time frame. You can also average out any seasonality on a time scale equal to window size. So this will allow you to look at lower frequency variation in the data. So when we are looking at electricity consumption time series, we already saw there is a weekly pattern, there is a yearly seasonality, which we saw using box plots. So we can also look at the rolling means of the time scales. How do we do that? So for this, you can use some package like Zoo, and then you can basically use a rolling mean using the Zoo package, and you can say what is the frequency with which you want to calculate the rolling mean. Now, how do we do this? Let's look at this data. So here I'm going to look at my data 3, which we have been using so far. Now let's call it a 3-day test. You can give it any name. I'm going to use my data 3. I'm using the pipe-in function. Now I will use dplyr and I will arrange the data descending in year. Now you can always break it down step by step and you can see the result of this. So I'm going to arrange this data in descending order of year. So obviously my last one, 2017 or 2018, will be on the top. You want to group the data by year. So it depends on how many years we have, we'll see. So you can group the data by year. Now this data is then used to basically mutate. So mutate function is going to allow me to use this rolling mean. So I'll call it as says 03 day. So I'm going to calculate a rolling mean every 3 days for my consumption column. And basically let's ungroup this. So let's see how this works. Sorry. Yeah, let's look at this. And here, when I'm doing a 3-day test, let's look at the result of this and then I'll explain this. So if you see here, we have the test 3-day column. Now this has the rolling average. Now what does that mean? So first value here, what we see is 1367 is the average consumption in 2017 from the first date with a data point on either side of it. That is, you can look at this date, so 1130, then you look at, you're looking at the value 1367 here, so you look at 1130, 1441, 1530. If I take a mean of these, so for example, if I would just do this part, and that is giving me mean, okay, because I have a comment, so let's basically add anything as comment, and then let's do this. So it says me 1367. That's what we are seeing here, right? So you're getting a rolling average every 3 days. Similarly, if you want every 5 days, it takes the 5 values and it gets the mid value, right? So you can always find out the mean, rolling mean for a particular frequency. Now, let's do that for 7 days, that is weekly data, and yearly data, that is 365 days. So how do I do it? Same logic, my data test. Now I'm using my data 3. I'm arranging it in a descending order. I'm grouping by year. So when you do a group by year, so earlier when we did a grouping by and when we looked at the data, it was telling me how many rows we had, right? So let's do a grouping by year. And let's say test 07. So that's a rolling average every 7 days. And I'm also saying take care of the NA values. Similarly, I'm getting rolling average every 365 days. Might be you can do quarterly, might be you can do half yearly. And let's do this. So let's create this, my data test. And let's look at the result of this. So I will use my data test. I will say arrange based on modified date. Now we know there is a column called modified date. I want to just look at 2017 data. So I'm doing a filter, right? And then I will choose what are the columns I'm interested in. So I will look at the 7 and 365 day. And let's look at, say, first 7 records. So let's do this. And that basically gives me the consumption value, modified date, year, and my rolling 7-day average or the 7-day mean, which is for first 7 days. And then 365, you will not see the data here, but if I do a view on this, I can basically see the values. So you can always select a particular column to see the values. These are the values for every 7-day rolling average. This is for 365 days, every 365 days. So you see all the values are missing, but every 365 entry, you will have basically some data. Now, let's do a plotting of this and basically visualize this data which we are seeing rolling average. So let me first do a plotting, one plot per graph. And let's do a plotting. I will take consumption data, x-axis, y-axis, color, and give a title to this. So let's create this, and that's my consumption data, which is spread over a period of time, and that's fair enough. But now let's add some more plot to this. So I will add the 7-day rolling average to this. So for second plot to be added in the same one, in R you can use points. So I will say points. I will choose 7 data column. Type is line, width, X limit, Y limit, and color. So let's do this. And that's my pattern 7-day rolling average, which basically gives me some kind of trend. Similarly, I can add one more here, and this time I will choose the 365 day and look at the pattern lines. So now you see some dots here. Well, you could do it in a different way. So I can just add legend to this, and I can say legend will be where in x-axis and y-axis. So I'm saying it will be 2500 and y is 1800. So my legend will come in somewhere here. I'm saying my legend will have consumption, test, and this one I can give some names. I can give what is the color. I can say what kind of legend it explains, what is for each color, and then basically a vector. So let's add a legend to this, and I've added a legend. Now you can do a zoom and look at the data, and here I see that my x-axis is fine, but y-axis is going a little out of my plotting area. So I can actually change that. So here I have 1800. How about making it 1600? And let's look at this one. So we can basically go for this one and start again here, plot and points and line, and then add a legend, right? And you can basically place your legend anywhere in the plot. So this basically is giving me the trend, what I'm looking at, my rolling average. So similarly, you can look at the trend for wind and solar data. So what we are seeing here is when you look at trend, this is one more way of looking at it. You can always create plots in different ways. So 7-day rolling mean has smoothed out all weekly seasonality, which we were seeing here in my graph, where you look at every 7 day, preserving the yearly seasonality. So 7-day will tell that electricity consumption is typically higher in winter and lower in summer. So better is you break it down yearly. So here, if you look at every year, you can see when is winter, when is summer, what is the seasonality, what your trend, what you're seeing here, and if there is a decrease or increase for a few weeks every winter. So similarly, if you look at 365, now as I said, rolling average basically reduces the variation. So if I look at 365 rolling mean, we can see long-term trend in electricity consumption is pretty flat. Now that's what we are seeing. It's kind of pretty flat. There is not much variation over years if you really join these dots. So we can basically see some highs and lows, and that gives me a trend. Now this is how you can do a trend detection, and similarly we can do plotting for wind and solar. So this is a small project which I demonstrated using R. Now all this code which you have here in the form of a project.r file, you can find here in my GitHub page. This is the document which explains some things. Feel free to download this and you can add details to it. This is the sample data set, which you can also find in my repository in the datasets folder. So continue learning and continue practicing R.
So who is a data science engineer? Are you a data science engineer, or are you going to be looking for a different field? What exactly is a data science engineer? Well, a data science engineer is someone who has programming experience in Python and R, expert level knowledge, ability to write proficient codes. And we have Python and R. I'm going to say Python or R. Once you become really proficient at one language, transferring those skills into another one is usually fairly easy. Now, R is a little different because it is an analytics platform. So going from Python to R, if you already know the data analytics in Python, moving to R is pretty easy. Now, R doesn't have all the other code that you can access with Python. There's so many things you can do with Python that are not data analytics. So that's important to keep in mind, that you should probably be pretty well-rounded in Python and really have a solid foundation in R, or have a solid foundation in R and be well-rounded in another programming language where you really get the programming side of it. Strong SQL and big data experience. So you have to have a strong coding skill with hands-on big data experience. And of course we're showing SQL here, most commonly used, whether you're using a Microsoft SQL server or MySQL server. You can also start thinking Hadoop and Spark and big data access. Hadoop file system is not a huge jump. If you've already learned your SQL and you've already learned your basics in coding, Hadoop sits on top of all that and does a wonderful job creating huge clusters of data. But you really need to know your SQL because that is so common in most of the large companies now accessing their data. And an ability to visualize models and troubleshoot code of the models. This is a kind of an interesting one because these models can get very complicated, so you got to be able to break them down into something that you can put the pieces together and digest each of the pieces. So being able to visualize these models is very important, and then being able to drill down and troubleshoot the different models or the pieces in those models. You need to be a versatile problem solver, equipped with strong analytical and quantitative skills. A self-starter with a strong sense of personal responsibility and technical orientation. This is an interesting one because when you talk about data science engineer, it's such a new field that most companies don't have it well defined. They don't know what they're looking for. You might not even know what you're looking for. You might have an idea and you're looking for patterns, but where do those patterns lead you? So you really need that self-starter side to jump in there and figure out where to go and be able to communicate that back to the team. And there we go. We have a strong product intuition, data analysis skills, and business presentation skills. And this is what I was talking about is you got to bring that back to the team. So if you don't have a strong product intuition, if you don't know what's going on with the company, what they need, and where you're going with your analysis, it's going to be a dead end. And you got to be able to present that to the shareholders, to your coworkers, which leads us to great teammate with excellent interpersonal skills. And this is kind of a strange one because you spend so much time behind your desk, so you have to be able to kind of float between you're studying all the data and being able to explain this to people in simple terms that they can understand. No one wants somebody to come up and say, yeah, the P score and the F score is this, that, and the other thing, and you might have two people in the room understand you. You have to be able to sit down and explain what that means and why. So let's take a look at the data science skill set. When we talk about data science engineer skill set, we're talking about database knowledge, statistics, programming tools, data wrangling, probably the least favorite and most used, machine learning, data visualization, and then to touch on big data. And so we'll start with database knowledge. The most common databases, of course, your SQL, structured query language. Think rows and columns. It's an essential language for extracting a large amount of data from data sets. So knowledge of the SQL is mandatory for data science engineers. And you can see there's tools required. There's the Oracle database. I mentioned MySQL Server, Microsoft SQL Server, Teradata. There are so many different forms of SQL. And it'll just keep coming back and coming back. So if you don't have a solid basic understanding of SQL, go get it. Very important because it will come up. If you don't know it, it's going to bite you. And statistics, of course, that's what this is all about, is figuring out and predicting things. So you need to know your statistics. Statistics is a subset of mathematics that deals with collecting, analyzing, and interpreting data. Therefore, data scientist needs to know statistics. So you need to understand your probabilities and what that means, and what the p-score means, and the f-score, and means, and mode, and median, all that information, standard deviation, all of those you need to be aware of. And then we get into the programming tools, and I mentioned this earlier a little bit, but you need to master any one of these specific programming languages. Programming tools such as R, Python, SAS are essential to perform analytics in data. And again, you can move in there and you can be an expert in just R. You can be an expert in just SAS and a little bit. You can be an expert in Python because most of these, when we're talking about data science and data wrangling, you really kind of get down to the point where you really need to have a full programming language, at least the basics. And if you're going to be working in data science, Python right now is the main one. But there's also Java, C++. So you need to know a solid language, at least the basics of it, so you can understand how to do basic iterations and things like that. I always found that interesting that my sister, who runs a university data analytics center, that's the first question she asks her candidates who come and work for her is, how do you iterate through data? You'd be amazed at how many people don't understand that very basic concept in programming. So when we look at R is a free software environment for statistical computing and graphs, supports most machine learning algorithms for data analytics like regression, association, clustering, and etc. Python. Python is an open source general purpose programming language, and there's our general purpose I was just talking about you need to know a little bit about. Python libraries like NumPy and SciPy are used in data science. NumPy and SciPy are very central to Python, and I'd throw pandas in there also, that module. Those are very central to working with Python and data analytics. And then SAS. SAS can mine, alter, manage, and retrieve data from a variety of sources. It can perform statistical analysis on the data. So where R is the open source platform, SAS is more like the paid for platform. And so it has some things more automated because people are paying for it, developing it, but it's also, if you really start using it as a company, you're going to have to pay for it, where R is free software. Python's also open source and free to use. So we're going to talk a little bit about data wrangling, and I mentioned earlier that is both the probably people's least favorite aspects of data science, and also probably one of the places you spend the most time. So when we talk about data wrangling, it is a process of transforming raw data into an appropriate format to make it useful for analytics. And it involves cleaning raw data, structuring raw data, and enriching raw data. And this gets interesting because you'll get stuck on something like, in Python, you might get stuck on something that is a date time based on an integer 64 NumPy set. You might not know what all those terms mean because you work in R or something like that. But you get the point that it's all one particular format, and then you have to figure out how to switch it so that the computer can see it correctly in whatever format you're using or whatever analytics platform you're using. Knowledge of machine learning techniques such as supervised machine learning, decision trees, linear regression, KNN, etc. is useful for few job roles. So this is kind of interesting because sometimes that's the center of the job role of a data scientist, and sometimes you just have to be able to apply the programming skills to it so you can get the answer and let somebody else fine-tune your machine learning techniques. So it really depends on what it is you're working with. And you can see here we have our nearest neighbor set up where it groups things together that look alike. Linear regression, you're drawing a line through the data, or a curve, so you can predict what the next value is going to be. And then our nice decision tree, which starts splitting things up and says, you know, it's sunny out, yes, let's go swimming. No, it's raining, we're not going to go swimming. Yes, it's sunny out, we might go swim. It's raining, we'll stay indoors, yes. We'll walk the dog, no. So you have a decision tree that helps figure out how you get to the end result. So decision trees can be pretty powerful. And data visualization. Data visualization is the study and creation of visual representation of data. Data visualization uses algorithms, statistical graphs, plots, information, graphics, and other tools to communicate information clearly and effectively. This one you really have to master as a data science. This one you really have to master as a data scientist. And there certainly are so many different tools to use to visualize it. But when you're communicating, a picture is worth 1,000 words. When you can put a picture up and people can look at it and go, oh, I see what's going on, that's worth a lot more than saying, yeah, this is good. People hear that and they just kind of go, okay, it's good, but why? And you might say, you know, okay, these numbers make it look good. No, people want something they can see. And there certainly is, Tableau is probably one of the most popular ones out there. View, Power BI, Google Data Studio. In Python, there's the PyKit and Seaborn. There's all kinds of different options for visualization. You need to master probably at least one or two of them so you understand how they work and how they're different. And then big data. Big data is a massive amount of data which cannot be stored and processed using traditional methods. Big data has various benefits like access to social data can enable organizations to tune their business strategies. Big data can improve customer experience. And so we're usually, when you say big data, we're almost always talking about Hadoop and Apache Spark. It used to be Hadoop is your file system, so that's how you store all your data going across the nodes, and there certainly are other ways to store it. But when we talk about Hadoop, we're usually talking about at least 10 terabytes of data when you're dealing with a Hadoop file structure. And then you can use Spark, where Hadoop processes on and off the hard drive. So it's continually reading and writing to the hard drive. Spark is running in your RAM. And so when you're doing a very intensive data process, you'll run a Spark setup, which will spread those processes over multiple computers. And of course, now the two combine, and Spark sits on top of Hadoop, and you get your big data. There's also Talend. Tableau has its own server set up. There's Splunk. Cassandra, you'll hear the Cassandra database. Pintaho, I'm not even sure how to pronounce that one. It's not one I've worked with. Certainly there's a lot of options for big data. The two big players are, of course, Hadoop and Spark. And even your SQL servers and MySQL servers will spread across 5 different servers. And you can be talking about big data across 5 servers with those, pulling them into, say, Apache Spark to do your high-end processing. And then there's non-technical skills. Probably the most important one in data science and any of our data analytics is intellectual curiosity. Updating knowledge by reading contents and relevant books on trends in data science. There's so much going on in this field, and it's exploding now that it's hard to keep track of it all. So you really need to have that curiosity in the data science, probably even more so than a lot of other fields. But I would say in just today's world, you need intellectual curiosity because things are changing so rapidly in today's world, the way that's going with our technology. Understanding how the problem solved can impact the business acumen. This is the one where a lot of people kind of skip over. You have to have a little business sense. If you don't know how it's going to impact the business, you're going to be in trouble. Why do they want to even pay you to be there unless they know what's going on and they're getting something in return? So this is your bottom line for your paycheck, is what's going on with the business. How is this going to impact the business? What are you doing for them? And communication skills. Companies look for someone who can clearly and fluently translate technical findings to a non-technical team. And I've talked about this a bunch, and I can't even iterate this enough. If you are struggling with your communication skills, work on building them. They don't have to be, this isn't rocket science where you have to know all these complicated terms. What you need to do is take the complicated terms you know from data science and reduce that down to something that anybody can understand. So when you come up and you have, KNN, no one knows what KNN is, unless they're in data science. Nearest neighbor, looking for things that match together. You got to explain that to people who do not have the technical skill in the data science arena. And a data science engineer needs to work with everyone in the organization, including customers. So it's teamwork, and that's always one that throws people for a loop, but ultimately you are analyzing your customer's information. And so sometimes getting in there and rolling up your sleeves, if let's say you're doing data analysis for a sales team and you're backing a sales team, you might have to get in there and go start making some sales and making some phone calls and see what it's like. What is that team doing when they call 15 people in cold calls? And then they do a follow-up 2 weeks later or 3 weeks later. Which one works better, 2 or 3? Does it work better to call and send a fax, call and send an email? When should you show up in person if it's that kind of business? So working with everybody, including the customer, is very important with the data with this kind of setup and non-technical skills for a data scientist. So let's take a look at some of the roles a data science plays in the job market. Let's drill in there just a little bit here. So when you have a data scientist, they're going to perform predictive analysis and identify trend and patterns that can help in better decision making. Companies hiring data scientists include Apple, Adobe, Google, Microsoft. I would say that's even expanding down to smaller companies, where you're talking about only 100 employees or something like that. They're starting to look at data scientists because they need them to come in and be a part of that team. And the role is understanding challenges of a system and offer best solutions. This should always be the goal of a data scientist, is to be looking at the whole system and then trying to find those patterns that are going to best enhance the company or the business or the whatever group. Maybe you're working with the sales team or the marketing team. And you can see languages. Pretty important to have these are a number of different languages, and again, it depends on your own specialty. There's all kinds of different variations, but we have R, SAS, Python, MATLAB, SQL, Hive, Pig, Spark. You should have at least a knowledge of all of these. Maybe a Python programmer never used R. Download it and go through the basics so at least you know what's going on in R versus Python. Because R is pretty powerful for doing a very quick display. And then, of course, there's a lot of things you can do in Python. You have to be able to do queries on database from time to time, create and modify algorithms which can be used to reduce information from large databases. And usually this is one of those things you do at the beginning, you set it up, and then you kind of let it go until it breaks, and then you have to go back and fix it because your query isn't working. That certainly is a very common thing to have happen, especially if you're pulling data off the web and the internet. And then we have some more companies that are hiring data analysts like IBM, DHL, HP. And so we're talking about data analyst. The role is responsible for a variety of tasks such as visualization, optimization, and processing large amount of data. And so when we talk about a data analyst, we're still talking a lot of the same stuff, but you'll see we now thrown in JavaScript and HTML in here, because that's pretty common with a data analyst versus a data scientist. And you can see that SQL is still pretty solid, and also C++ is pretty big. So some companies also use Java, so I'd put Java in the languages also on that for a data analyst. And then you have a data architect, ensuring that data engineers have best tools and systems to work with. And so companies hiring a data architect are like Visa, Logitech, Coca-Cola. They create blueprints for data management with the best security measures. I cannot highlight that a data architect really spends a lot of time with security measures. That's big. How many hacks have we seen in the last year on large companies that have lost data for millions of their customers and how badly that affects them? And we're looking at languages. You see that SQL is pretty solid across all of these. Under a data architect, XML. That's one that a lot of the data science jobs you don't see as much, but you're going to see more XML with a data architect because there's a lot of XML files that have your security measures embedded in them. And of course your Hive, Pig, those are Hadoop systems for doing some basic queries. So instead of doing the high-end queries, you now have these simplified query systems built into Hadoop and Spark. So if you're using big data, you're going to want to know your Spark also. And then we have our data engineer. The data engineer updates the existing systems with better version of the current technologies to improve the efficiency of the databases. Think admin here. A lot of work tracking down what version you're in of the different programs. What version of Python are you using? What version of R are you using? What version of C++? So companies hiring data engineers are like Amazon, Spotify, Facebook. And they develop, construct, test, and maintain architectures such as databases and long-scale processing systems. And here we have our languages, our SQL, R, MATLAB, SAS, SPSS, Python, Java, Ruby, C++, Perl, Hive, Pig. You pretty much as a data engineer at this level, when you're talking about admin and updating all these databases, need to know all the different stuff that's being used in the company. And you're testing out these structures to make sure they work. And so you really are talking admin level kind of setups. If you like spinning up an admin onto a Google Cloud service or Amazon Cloud service, now you start to get an idea what we're talking about, because then you can test it out up there and then you can bring it back and update it to the company. Statistician creates new methodologies for engineers to apply. And so when we look at this is where we're digging into the math of which models to use, what setup's going to work, what kind of activation do we have on our neural network. These little tweaks are going to make a big difference. And we look for methodologies at a large level. What kind of data are we going to be looking at and how are we going to pull it together? Companies hiring a data engineer, or we're talking about statisticians, we're talking about LinkedIn, PepsiCo, Johnson & Johnson, and of course these companies probably hire a little bit of everything, but they have a lot of statisticians working for them. And so we look at the role, extract and offer valuable reports from the data clusters through statistical theories and data organization. And the languages across the board, we're still seeing SQL, R, MATLAB, SAS, SPSS, Data. That's a new one that we haven't seen in some of the other roles. Python, Perl, an older version. And that shouldn't be a surprise because a lot of these companies probably built a lot of the original packages on Perl. If you go look at Johnson & Johnson. And of course your big data, Hive, Pig, and Spark. And then our database administrator. I mentioned the other one is an admin. They're more an admin level for the software itself. So administrator is another level. Some of the tasks involved are monitoring, operating, and maintaining databases, installation, configuration, defining schemas, training users, etc. And this is interesting, training users, because when you build a database and you define all the different tables that are embedded in that database and how they're all connected, the end user's got to have that information, otherwise you're in trouble. And we have companies hiring data engineers, of course Tableau, Twitter, Reddit. The role ensures that all the databases are available to all relevant users. Again, a little security in there. What role do they have? Who is allowed in and not? And is performing correctly and is being kept safe. And you better be ready to spend some time in security, because again, that's a very big thing nowadays with the number of people who hack into these databases. And the languages are going to be covered. You have your C#, your Java, SQL, Ruby on Rails, XML. Again, there's that XML because a lot of your security is embedded in XML files. Python, all the main players, depending on what the company's using. Data and Analytics Manager. So when you see manager, that means that somebody's going to sit on top and organize the people underneath. So they're going to improve the business process as an intermediary between business and IT. Oh, you better have some really good communication skills for this one. Some of the companies hiring data engineers are Coursera, Motorola, Slack. And of course, these companies are hiring data scientists in almost all of these fields. So the role oversees the data science operations and assigns the duties to the team according to skills and expertise. So that's a big one. You better be able to communicate what's going on, help your team members come out and be able to communicate with other people. So sometimes your job is just being able to get people to talk to each other. The big thing on that is the whole communication line going from one end to the other, because you can't communicate all the information that everybody's working on. You have to pretty much come in there and help people communicate what there's going on, and also know what they're up to without being micromanagement, because that will crash a company if you micromanage everybody. But if you just let them do whatever they want and they never talk to each other, that will also destroy the company. You got to find that nice middle ground. And you really have to have an overview of everything as a data and analytics manager. One of the things, it's good to have at least one or two solid bases of programming under your belt for a data analytics manager, but you do need to have a very general understanding of all the different tools being used so that you know what's going on with your different team members. Of course, SQL, R, SAS, Java, Python, MATLAB, all of those are big. Business analytics. So this is when you're talking about your BI or your business intelligence and your business analytics. Very important to know this is kind of a subdivision of a lot of the other stuff we've talked about, a lot of the other roles we've looked at. So you possess specialized knowledge of their business domain and apply that knowledge and analysis specifically to the operation of the business. So you might be a specialist in banking. You might be a genetics engineer, so you know about genetics. You might just be general business, helping the marketing. So a lot of companies hiring data engineer are Oracle, Uber, Dell, and the role acts as a link between the data engineers and the management executives. So it's very similar to when we go back up here and we look at data analytics manager. A business analytics is going to also kind of fill that role in between, but they're more specialized in business. And you better know SQL, because when we're talking about business specifically, most of the large companies are storing their data that's up and running right now that people are accessing to purchase something on the Home Depot website or the Uber. They're logging in. You better know your SQL. It's very central to business analytics. So let's go ahead and take a look at the data science engineer salary trends. And you'll see that our source is Glassdoor. That's where we're pulling a lot of our data from. Average base pay is around $117,000 in the U.S., the average salary. And when we look at India, we're talking about $950,000 a year. And those are based on, some of them you need to go ahead and dig deeper to find out what education level versus entry level. But those are a pretty solid base once you're in the industry and once you created your career in there. And we look at the job titles. The most common job title is data scientist. Business Intelligence Manager is the second greatest one. That's kind of good to note. That's why they put that up there as being its own little subcategory of data science manager, as a business intelligence manager, because it's such a high level of jobs. And then we looked at some of the other ones: data architect, business intelligence architect. Again, your BI, your business intelligence, gets its own ranking because it's such a high level, it's a business. People want their businesses to make money, so that's who's hiring. Of course, data engineer, business intelligence developer, business intelligence consultant, business intelligence analyst, business analyst, and data analyst. So you can look at the data analyst as being the general one that doesn't go specific to business. So if you're looking just for your career as far as getting a job, probably should have some kind of business understanding in the background. And again, your companies want to make money, so they're going to hire someone who knows business. If banking business, if you specialize in banking, or retail, if you specialize in retail and marketing. And you can see here on the data science salary trends and the growth in data science job listings. It's continually going up. It's since 2014 to 2012, we've gone from 400 to 600. That's a pretty big increase. So, huge growth in this market. It's one of the biggest growing markets right now for jobs and careers. So let's go ahead and take a look at building a resume. Always exciting, putting ourselves out, selling ourselves. And if you looked at some of our other videos dealing with resumes, you'll see a trend here. The top part is so different than what resumes were in the 90s, in the 2000 to 2010. They've evolved. They've really evolved. It used to be 2000, 2010, maybe LinkedIn, maybe one other reference. Now you're going to see that we want those references. This is a sales tactic, which now has come into resumes. It used to be that if you were a real estate agent, every real estate agent I knew, I used to deal with real estate software for the real estate industry back in the 90s. Every real estate agent wanted their picture on their business card. They wanted their picture, if they could, put on their contracts. They wanted people to see the face. So that's really a big change, is to make sure that it stands out. You stand out. Here's a picture of somebody, so you're more than just a couple letters and a name. And of course, you need your contact information, should always be at the top. You have your summary. What are you focusing on? Be a little careful with your summary, because if you have everything in your summary and then they scroll down to experience and education and skills, they're going to stop. The second you repeat yourself in your resume, that usually means to the reader, hey, this person doesn't have anything more to offer me, I'm done. So be a little careful how you word your summary. Most companies appreciate when you come in here and you've adjusted this summary to be both about you and how you're going to serve that company. So it's worth researching that company to find out how those connect and put that in the summary. Take some time to do that. That's actually a pretty big deal. And the references are huge also, especially in data science. When you're talking about any of the programming or data science, data analytics, having a place to go where they can look it up and scroll down and see different things you're doing, whether it's LinkedIn in this case, which is the business profile most commonly used, GitHub where you have stuff published, Facebook. I'm always hesitant because that tends to push more towards social media type jobs and other jobs. But certainly there's people who have Facebook who do marketing and stuff like that. But these links, having these basic links here is important. People are starting to look for that for some other setup. Maybe you have a personal website. This is a good place to put that so that they now have a multitude of links that go back to you and highlight who you are. And then the next part, or next 4 parts, so for the next 4 parts, we have a combination of experience, education, skills, certifications. And you can see they're organized. If you have, a lot of people like to see what kind of degree you have. They want to know where it came from. And if you just got out of college, you're going to put education at the top. And then maybe you'll put skills after that, and then your experience at the bottom. If you've been in the field for years, my degree, just to give you my age, goes back to the early 90s. So I usually put education at the very bottom. And then because a lot of the stuff I'm trying to sell myself on right now is my skills, I actually put that at the top. And I'll put my education, my certifications at the bottom, my skills, and then my experience is, since it's a huge part of my resume, goes next. You can organize these in whatever order you want that's going to work best for you and sell you. So remember, you're selling yourself. This is your image. Probably don't wear an old tie-dye t-shirt with holes in it. Something nice because it is professional. And of course your summary. And then what do you have to offer the company? And again, when I put out resumes, and I haven't done a resume in a while, you go in there and you can take this and reorganize this. So if the company's looking for something specific, you might put the experiences specific to that company. You might even take experience, if you have like a long job history like I do, I've gone into a lot of different things, you might leave out those companies or those experiences that had nothing to do with data science because it just becomes overwhelming. Resume should only take about 30 seconds to glance over, maybe a minute tops, because after that point you've lost the person's interest. And if they want to dig deeper, they now have links, they have your website, they have LinkedIn, and they can now take this and they come back to it and they go, oh, okay, let's look at this person a little closer. So quick overview, this is your sales sheet selling you to the company. So always tie it to the company so that you have that, what am I going to give this company? What are they going to get from me? We've covered a lot on data science engineer in general, and we've gone over a basic resume. Remember, keep it simple, short, and direct. That is so important with that resume.
Thank you all for watching this video tutorial on R for Data Science full course. I hope you liked it. If you have any questions, then please put them in the comment section of the video. Our team will help you solve your queries. Thank you for watching. Stay tuned for more from Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.